is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data. And most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to them, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The known Simulia solution is probably Abacus, which is the dedicated structural finite element, and solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Land Railway System, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity.
Presenters, participants, esteemed colleagues, and distinguished guests, it is with great pleasure that I welcome you to the 2024 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, or ICRAME 2024 for short. I am Ardita Septiani, the host for this event. The theme of this year's conference is Accelerating Digital Transformation, Cultivating Electronics and Telecommunication as Open and Innovative Technologies for a Sustainable Future. ICRAME 2024 lasts for 2 days, covering 4 keynote talks, 1 patron talk, and 69 paper presentations. We have accepted for publishing 69 studies that will be delivered as oral presentations coming from 7 conference tracks. The first track is remote sensing and radar system. Second, antenna devices and techniques. Third, radio frequency and microwave theory and devices. Fourth, electronic materials, sensors, devices, components, and circuits. Fifth, wireless and wired communications. Sixth, signal and image processing techniques. And 7, control system, robotics, and mechatronics. We convene to explore the challenges and breakthroughs in the aforementioned areas. We look forward to 2 days filled with fruitful discourses. I hope these 2 days will culminate in a networking session, providing a unique opportunity for us for collaboration and seeding the innovations of tomorrow. Also with us, from Indonesia's National Research and Innovations Agency, or BRIN, I would like to welcome the Head of Research Organization for Electronics and Informatics, Dr. Budi Prawara. Also, Head of Research Center for Telecommunication, Dr. Nasrullah Armi. Head of Research Center for Electronics, Professor Yusuf Nurwijayanto. Head of Research Center for Computing, Dr. Rifki Sadikin. Head of Research Center for Smart Mechatronics, Dr. Yanwandri Putrasari. Head of Research Center for Data and Information Sciences, Dr. Esa Prakasa. Head of Research Center for Artificial Intelligence and Cybersecurity, Dr. Anto Satrio Nugroho. Head of Research Center for Geoinformatics, Professor M. Rohis Komarudin. Also, I would like to welcome with us from our technical co-sponsor, Professor Linawati, as the Secretary of IEEE Indonesia section. Our keynote speakers, Professor Witawat Witayachumnanko from the University Adelaide, Australia, Professor Yoshiki Yamaguchi from University of Tsukuba, Japan, Associate Professor Jiafeng Yao from Nanjing University of Aeronautics and Astronautics, China, Dr. Chief Aminullah Fatnan from National Research and Innovation Agency from BRIN Indonesia. Also, I would like to welcome the speakers from our patron, Mr. Muhammad Gulam from PT Nusantara Sekom Infotech and Mr. Rijin Sasendran from Dassault Systems. We also welcome our esteemed patrons representatives, Dr. Yusi Perdana Saputra, STMT IPM Asian Engineer, APEC Engineer from PT Radar Telekomunikasi Indonesia, Ms. Parisa Mariana from PT Nusantara Tech, Mr. Isman Latif from PT Mars System Integrasi, Mr. Enjang Ruyat from PT Serviam Abadi Murni, Ms. Vivi Intania from PT Young Dinamis Indonesia, Mr. Bilal Chan from PT WAP Andalan Indonesia, Mr. Arif Rusyana from Bank Rakyat Indonesia, and Ms. Nisa Awalia from PT Land Railway System. As well, I would like to welcome all presenters and participants. Please allow me to briefly outline the program for the first day of ICRAME 2024. The first agenda, shortly we will have the opening ceremony, then followed by a patron session from PT Nusantara Sekom Infotech and Dassault System. And after that, we will have our first keynote talk from Professor Witawat Witayachumnanko. After a short 10-minute short break, we will begin the parallel sessions of 1 and 2. Then we will have the lunch break. After that, we will have our second keynote talk from Dr. Aisha Patnan, and the ICRAME Day 1 will end after parallel sessions 5 and 6. Before we proceed to the opening ceremony, let us hear the Indonesia's national anthem, Indonesia Raya. Now we are commencing the opening ceremony. We will have 4 remarks, begin with Dr. Pauline Octaviani as the chair of ICRAMI 2024, followed by a remark from the representative of our co-technical sponsor, Professor Linawati, the Secretary of IEEE Indonesia section, Dr. Nasrullah Army as the head of the research for Telecommunications of Indonesia's National Research and Innovation Agency, BRIN. And last, we will have the remark from Dr. Budi Prawara, head of research organization for electronics and informatics of BRIN. Okay, now let's start with the first remark for today. I would like to welcome Dr. Pauline Octaviani.
Thank you, Ms. Ardita, distinguished Head of Research Organization of Electronic and Informatics, Dr. Eng Budi Prawara, Head of Research Center for Telecommunication, Dr. Nasrullah Army, Head of Research Center for Electronic, Professor Dr. Yusuf Nurwijayanto, IEEE Indonesian Section, Professor Linawati, distinguished guest, keynote speaker, distinguished patron, presenter, participant, ladies and gentlemen. Good morning. Assalamualaikum warahmatullahi wabarakatuh. I'm Pauline Octaviani as a chairman of ICRAMI 2024. On behalf of organizing committee, it gives me a great pleasure to extend a warm welcome to all participants to the 13th International Conference on Radar, Antenna, Microwave, and Telecommunication ICRAMI 2024, which will be held virtually for 2 days during 12 till 13 November 2024 from Bandung, Indonesia. This year, the conference is hosted by Research Center for Telecommunication BRIN, technically co-sponsored by IEEE Indonesian Section and supported by IEEE Indonesian TTAP Joint Chapter. The theme of ICRAMI 2024 is Accelerating Digital Transformation, Cultivating Electronic and Telecommunication as Open and Innovative Technology for a Sustainable Future. The conference offers an excellent opportunity to exchange technical information and build connection between participants involved in education, research, development, and manufacturing in field of communication and electronics. The topics include remote sensing and radar system, antenna devices and technique, RF and microwave theory and devices, electronic materials, devices and component circuit, wireless and wired communication, signal and image processing technique, mechatronic, and related areas. We are honored to feature 4 distinguished keynote speakers to discuss current development in electronic and telecommunication aimed at ensuring a sustainable future. Our keynote speaker, Professor Witawat Witaya Chumnankul from the University of Adelaide, Australia. Professor Yoshiki Yamaguchi from the University of Tsukuba, Japan, Associate Professor Jiafeng Yao from Nanjing University of Aeronautic and Astronautic, China, and Dr. Asif Aminullah Fatnan from BRIN, Indonesia. We also have a distinguished patron from the South System NSI, Mr. Regine Sasendran. This year, 141 papers were submitted to the conference for more than 15 different countries. Of these, 69 distinguished papers were accepted, corresponding to acceptance rate of 59%, which is spread across 7 conference tracks. The participants of ICRAMI 2024 come from Indonesia, Malaysia, Saudi Arabia, USA, Iraq, Qatar, Turkey, India, Japan, Austria, Canada, France, Philippines, and United Kingdom. Once again, we would like to express our sincere appreciation to all keynote speakers, reviewers, session chair, supporting organization, and all the committee members who contribute their time and effort to organizing the conference. I warmly thank to the IEEE Indonesian section as the technical sponsor of this conference and other parties that cannot be mentioned here who have helped and support this conference. In addition, I would like to extend a special thanks to our valued patron, Nusantara Sekom Infotech, Radar Telekomunikasi Indonesia, Mars Sistem Integrasi, Young Dinamis Indonesia, WAP Andalan Indonesia, Serviam Abadi Murni, Bank Rakyat Indonesia, and Lens Railway System. Their support and contribution have been instrumental in making ICRAME 2024 possible. Above all, I thank to authors and presenters for their vital role in making ICRAME 2024 a great success. Once again, a warm welcome to ICRAME 2024.
Thank you, Dr. Colin Octaviani. Moving on from our technical co-sponsor IEEE Indonesia section, please join me in welcoming Professor Linawati.
Okay, thank you, MC. So good morning, everyone, dear distinguished guests, colleagues, researchers, professional ladies and gentlemen. A warm and spirit greeting to all of you. First of all, please allow me to extend my warm greetings to the Honorable Head of Research Organization for Electronic and Informatics, the National Research and Innovation Agency, Dr. Eng Budi Prawara, Head of Research Center for Telecommunications, the National Research and Innovation Agency, Dr. Nasrullah Armi, Head of Research Center for Electronic, the National Research and Innovation Agency, Professor Yusuf Nur Wijayanto, and of course, General Chair of ICRAME 2024, Dr. Colin Octaviani, as well as the distinguished keynote speaker, Professor Wita Chamunangkul from the University of Adelaide, Australia, Professor Yoshiki Yamaguchi from the University of Tsukuba, Japan, Associate Professor Jia Feng Yao from Nanjing University of Aeronautic and China, Dr. Asif Aminullah Patan from the National Research and Innovation Agency Indonesia, Regin Sasindran from the Salt System Nusantara Infotech Indonesia. And last but not least, to the conference committee members and all participants. Ladies and gentlemen, on behalf of the IEEE Indonesia section, I would like to extend our warmest welcome to all keynote speakers, presenters, and participants of the 13th International Conference on Radar, Antenna, Microwave, and Telecommunication, or ICRAME 2024. The conference is held today and tomorrow in Bandung, in online mode by the Research Center for Telecommunication, National Research and Innovation Agency Indonesia, with the IEEE Indonesia section as co-sponsor. In 2024, the IEEE Indonesia section co-sponsored many international conferences held in Indonesia, including this conference. But co-sponsoring conferences is not the only activity we do. The IEEE Indonesia section has carried out a large variety of activities since its formation February 1988. The IEEE and the IEEE Indonesia section share the same mission, namely advancing technology for humanity. But for us, it is within the scope of Indonesia. However, at the same time, contributing internationally. As an example, we have started to work together in the Asia Pacific region in promoting clean energy technology for climate sustainability under the guidance of the 2023 President of IEEE, Professor Saiful Rahman, and in supporting the role of women in engineering and industry with the 2024 President Dr. Tom Coughlin. In line with the mission, we maintain good and mutual relationship and networking with the Indonesian government, industry, university, professional, and scientific organization, and various communities in Indonesia. IEEE Indonesia section is very proud to have had a cooperation agreement with the Directorate General of Higher Education of Indonesia since 2021, which allow us to directly participate in the development of engineering higher education in Indonesia. Our contribution are the following. Firstly, the IEEE Indonesia section presently have 22 technical society chapters and joint chapters covering the field of interest of 27 IEEE societies, widely ranging from power and energy to communication to oceanic engineering to education and to social implication of technology. Those chapters support various scientific and academic activities in Indonesia, including technical co-sponsorship of international conferences. Secondly, as of now, we have IEEE student BRIN chapter in 38 universities in Indonesia, which supports educational activities, early career development, and international networking for university students. We would like to invite all universities in Indonesia to form IEEE student brands in their campus and maximize the potential benefit of talent and skill developments for students through the IEEE network. Aside from that, we also hold workshop on STEM for high school students in our attempt to attract the best talent into the field of science and engineering. Up to now, a number of IEEE student brands in Indonesia section have won international grants for humanitarian technology and several IEEE members have received national scholarship from IEEE. IEEE Indonesia section technically co-sponsor more than 70 international conferences annually. As the co-sponsor of these conferences, we strive to assist them to maintain the quality of the papers at the highest level and within the scientific scope of the IEEE. In terms of international publication, as of July 2024, there are more than 36,000 scientific papers in total, with at least one author coming from Indonesia published in the IEEE Explore, which consists of those published in IEEE conferences and others in IEEE journal. However, out of those 36,000, there are only around 1,000 papers that have been published in IEEE journal, with at least one Indonesian author. Accordingly, we would like to encourage Indonesian researchers to publish their research work in IEEE journal, which have been widely recognized as high-impact journal. To conclude this remark, we highly appreciate the commitment shown by the organizer of ICRIMET 2024 to keep the quality of accepted paper at the highest level, focusing only on paper within the scope of the IEEE. We hope that such a strong commitment be sustained through the coming years. Finally, we wish all participants an enjoyable and valuable experience during this conference by sharing your best knowledge in the research area of your interest. Please make ICRIMET 24 a memorable event. Thank you and have a good day.
Thank you, Professor Linawati. Now, please join me in welcoming Dr. Nasrullah Armi as the Head of Research Center for Telecommunications of Indonesia's National Research and Innovation Agency, or BRIN.
Thank you, MC, and Assalamualaikum everyone. Distinguished guests, speaker, and participants. It is my great pleasure to welcome you to the 2024 International Conference on Radar, Antenna, Microwave, Electronic and Telecommunication, and we know is ICRIMET. This annual gathering has become a vital forum for research industries, expert and academic around the world to share knowledge, and explore the latest advancement in this critical. The field of radar, antenna, microwave, electronic and telecommunication are the foundation of modern communication and information technology, empower our societies in countless ways, from enabling global connectivity to supporting innovation in healthcare, transportation, defense, and environmental monitoring and other applications. As we witness the rapid evolution of technology, the work being presented and discovered is essential to driving progress and shaping the future of how we communicate and interact with the world. This year, conference promises an exciting lineup of presentation, discussion, and knowledge sharing. We are privileged to host some of the brightest minds and most accomplished professionals in our field, all here to share groundbreaking research, emerging trends, and practical applications that are defining the future. Over the next few days, we find radar system, cutting-edge antenna design, innovation in RF and microwave technology, processing, material sciences, and revolutionary application in the electronic and telecommunication. As we embark on this journey together, I encourage you all to take full advantage of the opportunities for collaboration and knowledge sharing. iClimate is not just a place to learn about new research. It is a community where ideas can flourish and where partnership can be formed to tackle the complex challenges that lie ahead. Finally, thank you to all the organizers, sponsors, and volunteers who have worked tirelessly to make this event possible. And thank you to each of you for your dedication and passion, your contribution to push the boundaries of what is possible. Once again, welcome to the 2024 iClimate Conference. Let us make the most of this day to drive innovation, foster collaboration, and contribute to a future where technology serves as a powerful force for good. Thank you all the committee, and let's have a successful conference. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Nasrul Armi. And now for officially opening the 2024 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, please join me in welcoming Dr. Budi Prawara as the Head of Research Organization for Electronics and Informatics from Indonesia's National Research and Innovation Agency.
Thank you, Ardita. Good morning. Assalamualaikum warahmatullahi wabarakatuh. Distinguished Head of Research Center for Telecommunications, Dr. Nasrul Armi, Head of Research Center for Electronics, Professor Yusuf Nurwijayanto, IEEE Indonesia Section Representative, Professor Linawati, and our distinguished keynote speakers, Professor Witaya Jumnankul from University of Adelaide, Australia, Professor Yoshiki Yamaguchi from the University of Tsukuba, Japan, and also Associate Professor Jia Feng Yao from Nanjing University of Aeronautics and Astronautics, China, Dr. Asif Aminullah Fatan from National Research and Innovation Agency, Indonesia, and also our distinguished patron from the South System NSI, Mr. Rijin Sasedran, distinguished expert and speakers, participants, ladies and gentlemen. First of all, allow me to welcome all participants of this conference. Let us begin by expressing our gratitude and praise to the Almighty God for His blessing, grace, and mercy, which have made it possible for us to gather here in this virtual room in excellent and good health. It is a great honor and privilege for me to attend the 13th International Conference on Radar, Antenna, Microwave Electronics, and Telecommunication, or ACREMET 2024, organized by Research Center for Telecommunications. And today, we are focusing on how digital transformation is rapidly changing our world. Electronics and telecommunications play a big role in these transformations, driving new ways for people and business to connect, share ideas, and grow. By fostering these technologies, open and innovative, we make it possible for more people to participate, collaborate, and create solutions that can meet today's need and prepare us for the future. This event offers a chance to share ideas, learn from one another, and explore how we can use technology responsibly to build a sustainable world. It is also provides an opportunity to present innovations and solutions that benefit industries in our fields. Through collaborations, we can discover creative, lasting solutions to future challenges. It's essential to remember that true innovation stems from research that is not only groundbreaking, but also considerate of society's needs. Our pursuit of knowledge should always prioritize the well-being of humanity. And yeah, I would like to take this opportunity also to acknowledge and thanks the Research Center for Telecommunications and the organizing committee for arranging this conference. I encourage all participants to fully engage with the knowledge and research shared by the speakers through digital platforms and to enjoy the inspiring season ahead. May this ICREMET conference bring you insightful discussions, meaningful connections, and enriching experience. I wish everyone great success and enjoyment throughout the event. Finally, with Bismillahirrahmanirrahim, it is my great pleasure to officially open the 13th International Conference on Radar, Antenna, Microwave Electronics, and Telecommunications, ICREMET 2024. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Budi Prawara. And next, to commemorate our events, I would like to invite all presenters, participants, esteemed colleagues, and distinguished guests to participate in the screen capturing session. Please turn on your cameras. We will capture the frame 3 times later, and I will do the 3 times of the signaling. Please get ready in around 10 seconds, as you may need to prepare and put our virtual background that our team also has uploaded the virtual background in the chat box. So maybe around 5 or 10 seconds to be ready. Okay, I think that we will do the first screen capturing. We're ready. I will count in 3, 2, 1. Okay, for the second screen, in 3, 2, 1. And for the last one, in 3, 2, 1. Okay, thank you for all your participation in the screen capturing session. We have completed our opening ceremony. I would like to thank all honorable guests, distinguished speakers, and all of our participants for the participation and attendance in the opening ceremony of ICRAMED 2024. Now, moving on to the first patron talks. Please join me in extending a warm welcome to Muhammad Gulam, a simulation engineer from PT Nusantara Sekom Infotech, and Mr. Rijin Sasendran, electromagnetic simulation expert from CST Dassault System. Thank you for joining us on this session. And this session will be moderated by Mr. Teguh Praludi. I will briefly introduce you to Mr. Teguh Praludi. He earned his bachelor degree in electrical engineering from Diponegoro University, Indonesia in 2001. And after that, he continued his master degree in telecommunication engineering from the Bandung Institute Technology, Indonesia in 2013. He is currently a researcher at the Research Center for Telecommunication within Indonesia's National Research and Innovation Agency, BRIN, and his current research interests are in antenna, filter, and radio frequency. Please welcome Mr. Teguh Praludi.
Thank you very much, Miss MC, this pretty woman, my friend, Miss Ardita Septiani. Okay, good morning, Mr. Gulam Reza. How are you today? Okay, are you still here, Mr. Rijin? Are you here?
Yes.
Okay. Okay, thank you very much. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, good morning, ladies and gentlemen. Welcome to ICRAMED 2024. My name is Teguh Praludi, and I will be your moderator for today's event. Thank you all for taking the time to join us. I hope today's session will be beneficial and insightful for everyone. Before the presentation begins, allow me to introduce the esteemed speaker for this morning. The first speaker may be from Mr. Rijin or Mr. Raja. The first speaker is Mr. Rijin Sasendran. He is from Nusantara Sekom Infotech or NSI. I hope I didn't mispronounce your name, Mr. Rijin. I'm sorry. Okay, Mr. Rijin is a highly accomplished professional with over 13 years of industry experience in the field of electromagnetic and has established himself as an expert in the field. Currently, Mr. Rijin serves as an industry process consultant at the Dassault System, where he applies his knowledge and skill in electromagnetic simulation application. Mr. Rijin's experience also includes working at the GA, General Electric, Global Research Center for over 2 years. During his time at the GA, he contributed to various electromagnetic projects and made significant advancement, resulting in a patent for wireless power transfer project. Today's event will focus on innovative design strategies for phased array antennas using CST Studio Suite. So, a topic that is highly relevant in today's context. And the second speaker is Muhammad Gulam Reza. He is obtained Master Science in Aerospace Engineering at Institut Teknologi Bandung. And his experience is simulation specialist at PT Nusantara Sekom Infotech from October 2023 until now. Also, is the technical support for various simulation software, including Abacus, Vesave, Tosca, iSight, Simpak, PowerFlow, GST Studio Suite, and the 3D Experience platform. Also, some skill use MATLAB. Okay, without further ado, are you ready, Mr. Gulam or Mr. Rijin?
Yeah.
Okay, without further ado, let's welcome Mr. Rijin or Mr. Gulam to deliver his presentation. You have 30 minutes for presentation. It is time for you.
All right, thank you, Mr. Teguh Praludi, for the warm introduction for us. So I'm going to share my screen now. Yeah. Is it visible, guys? Or okay, I think it's visible. So hello, good morning, everyone. Thank you for the warm introduction. It's an honor to us to be here today presenting such great and distinguished audience. My name is Gulam Reza, and I'm a simulation specialist at PT Nusantara Sekom Infotech. Today, before we dive deeper with my colleague here, Mr. Rijin Sasendran from Dassault Systems, our principal, let me start by giving a brief overview of our company and the solution that we can offer to you, which could bring value to your work in the field of electromagnetic research, especially. Okay, so PT Nusantara Sekom Infotech was first established in 1988, originally part of PT Industri Pesawat Terbang Nusantara, which is now known as PT Dirgantara Indonesia. As the only one gold partner of Dassault Systems in Indonesia, our expertise spans a range of industries, including transportation and mobility, aerospace and defense, marine and offshore, also infrastructure and architecture engineering. We deliver end-to-end solution in CAD, CAE, CAM, and also digital manufacturing, powered by special tools like Simulia and Katia, the name you might be already recognize, yeah. We are dedicated to support and empower engineers, innovators, and also researchers across those sectors, bringing advanced solutions to meet both today's challenges and also the demands of the future, including those in the electromagnetic field, which will be discussed further later by my friend. Okay, let's talk about Dassault Systems and its set of solutions. And it wouldn't be complete without mentioning its 3D Experience Compass. As you can see here, this compass captures the full spectrum of Dassault Systems capabilities, which organized into 4 main regions. Okay, the first one, on the east, we have the information intelligent apps. Next, on the north, there lies social and collaborative apps. And then for 3D modeling apps, there lies on the west region. And finally, Simulia, home the powerful simulation application lies on the south region. Okay, so let's going deeper into Simulia. Simulia supports simulation across a wide range of physics domain, and we call this capability as multi-physics domain simulation. Okay, first in the structures assessment, in the structures analysis domain, we have Abacus CAE that enables you to do a complex structural assessment. And then for fluid dynamic or computational fluid dynamic, CFD, there is PowerFlow. And then for the electromagnetics, which is the main topic for today's conference, is covered by tools like CST Studio Suite, Opera, and also Antenna Megas. Next, we have vibroacoustics. We have Wave6 that handles that simulation. And then for the multi-bodies analysis, there is Simpak. And finally, for the automation and also optimization process, we have iSight and also Tosca. Okay, next, let me give just a brief overview of each simulation from every domain, starting with structural simulation. With Abacus CAE, we can perform both static and also dynamic structural analysis. We can also conduct a fatigue assessment. We can also simulate a crack growth and even extract natural frequencies from model analysis simulation. And then in the fluid dynamics domain, we can analyze both aerodynamics and also hydrodynamic performance of a system. And even we can also assess the aeroacoustics performance of it. And our CFD capabilities also support fluid mixing process and also the cooling analysis or thermal management. And then in the electromagnetic domain, our tools allow us for diverse designs and also analysis, such as antenna arrays, feed systems, reflector antenna. We can also perform interference analysis, study lightning strike phenomena, and also electromagnetic immunity. Okay, so it would feel incomplete, right, to present solution without sharing a few success stories of how we have supported our customers. Okay, I'll start with the educational institution. We have partnered with several universities to strengthen both teaching program and also research through our tools, such as CST Studio Suite, Antenna Megas, and also Abacus CAE. And then for the commercial sector, we have supported also PT Energi Kreasi Bangsa, or we have known it as Electrum, in the development of their electric motorcycle using our latest tool that they have mentioned before through the Experience platform. This platform integrates multiple physics domains into a single cohesive simulation platform, so we can do a simulation seamlessly without any disturbance. And then for the governmental sector, we provide a critical support to the Dinas Penelitian and Pengembangan, or Dislitbang TNI Angkatan Udara, with tools like Abacus CAE, Xflow, and Karya Magic. And finally, our collaboration also extends to other government research institutions, including BPPT PTIPK, Lapan Pustekbang, and LIPI PPET, all of which are now unified under the umbrella of BRIN, Badan Riset and Inovasi Nasional. And here are some of our customers we have ongoing collaboration. As you can see here, we support a wide range of sectors, including manufacturing, educational institution, government, and also engineering consultancy. Okay, finally, we are reaching the end of my presentation today. As takeaway that you can get today for my presentation is that PT Nusantara Sekom Infotech, as a Dassault Systèmes Gold partner, is committed to support engineers and also researchers by offering the best and optimal solution to our certified technical experts with a focus on Simulia advanced multiphysics simulation capabilities, so that you can get the best possible design for your project or for your research. Okay, I think that's all from my presentation, and I'm giving back to Mr. Teguh as the moderator. Thank you.
Okay, thank you, Mr. Gulam Reja, about the presentation about the Simulia software. This is a powerful software. And now we go to the second presenter, or second speaker from the South System is Mr. Rijin Sasendran. And for Mr. Rijin Sasendran, it's time for you. Thank you.
Okay, thank you. Hope you see my screen here. Okay. Good morning, everyone. Thanks for the nice introduction, and thank you, Gulam, for introducing the company and portfolio. So here, my job is basically to introduce you to some innovative design strategy for phased array antennas. So I'm focusing on mainly the simulation strategies, how to come up with efficient phased array antennas for your applications. Before going into the depth of what phased array is. Let's understand what antennas are, or where do we use antennas. Can see in every communication sector, aerospace industry, manufacturing industry, and every other industry you can think of are all connected through different kinds of Internet of Things, as well as light connectivity, low latency connectivity with the modern communication systems. Basically, antennas are used everywhere, pretty much everywhere. The simulation is intended to help engineers to confront all the challenges you are facing in implementing these kind of designs. Those challenges are not really only the engineering challenges posed by the technology itself, but also by the consumers or ourselves, because we want any new technology immediately. We can't wait like a few years, but we want it now or even tomorrow, now itself, right? So you heard about the 5G or next gen research 6G or even AI technology. So we all want as a consumer to be implemented or to use this technology right now itself. So what that means is the design cycle are becoming pretty short. So there is very little time for you to iterate your design to come up with the working prototypes or the actual design itself. So that's where simulation plays an important role. You can really left shift or reduce the design cycle by using or leveraging the power of simulation rather than building the prototype, testing, failing, and again rebuilding. To be used effectively, the simulation must be used at a very early stage of your design. So during your concept stage itself, you should start thinking of simulation and start trying out things in the virtual world. We call it virtual twin, before developing any prototype. This will give you more options and time and more room to solve your problems in the process. So getting a robust working design very early will reduce the overall risk and cost. It will avoid the release cycle of your product. And that means is simulation is becoming very crucial to achieve your design goal. Right. Now, how do you start developing a design like an antenna? Right. Classically, it comes from your experience. It comes from your research, like the already published antennas in the literature, and you start iterating or optimizing the existing design for your design. Or probably from your experience, you might start from scratch. As a simulation technology vendor or a software company, we also provide toolkits or design templates of antennas, which is a library of customizable antennas that can be optimized for your design. It's called as antenna megas. So it's an alternative approach where more than 350 design algorithms are available, which can be picked and choose to come up with a design that suits your application. You can pick and choose multiple designs which satisfies your performance criteria, your antenna performance criteria, like the type of antenna, the antenna performance criteria like gain, bandwidth, polarization, radiation pattern type, etc. And the software will allow you to pick many different designs which satisfies these criteria. You can compare them. You can estimate the performance within the tool. And finally, you can explore a fully parametric model to a full-way solver, which is in CST Studio Suite, to do the further analysis, like putting this antenna on a platform like a phone or on an aircraft or even on a satellite, etc., etc. Similarly, we also have different synthesis tools, like the one called WaspNet, which is mainly meant for designing waveguide type of antennas and related structures. Like, for example, you can see on antenna design along with its power delivery networks, like waveguide couplers, dividers, light plexes, etc. All can be synthesized, meaning you define your required code to the software, and the software can come up with the 3D design through synthesis. And you can further optimize. So this kind of tools uses a technique called mode matching, which can divide and conquer or divide and solve each section of the design separately and combine. So these kind of complex designs solutions can be achieved in a matter of seconds rather than minutes and hours of simulation. That's the beauty of this kind of synthesis. But if you are designing your own antennas or your own, or maybe one from antenna makers which you want to further optimize, you have to employ one of the numerical techniques, which is a full wave technique or specialized techniques like time domain, frequency domain, or even specialized ones like integral equation or asymptotic set. So each different numerical technique has its own strength. What that means is, by theory, you can use one of the solvers like time domain to solve any problem. But that's not the whole point in simulation. We want to achieve the simulation with higher accuracy in least amount of time, utilizing least amount of hardware resources. That's the simulation. To do that, different types of antennas or different types of applications will have different challenges. And if you wisely choose the solver right for your application, you can achieve this simulation efficiency. Because each solver has its own strength. Like for example, certain ones are full wave, certain ones are specialized ones, certain one needs volumetric meshing, certain ones only need surface meshing, etc. Not going into depth of the numerical technique in itself, are all from the electromagnetics background and probably are aware on a high level what each technique is. But what I would like to stress is there is a thumb rule with which you can choose the solver efficiently. Like for example, if you look at this busy slide here, but let me break it down and help you understand. I have two axes. On the x-axis, I plotted bandwidth, going wider bandwidth on the left side and narrower bandwidth on the right side. And on vertical axis, I have electrical size. Suppose you have a problem which is of wide bandwidth, but electrically probably medium to large, then it's better to use a transient solver to solve the problem because that fits well to that kind of problems. Unlike if you have electrically smaller and also narrow band technique, it's usually the finite element based techniques will be most efficient. If you go larger in electrical size, the integral equation solver based on method of moments and MLFMM, as well as asymptotic solver becomes most efficient method. But these criteria or thumb rules are not really relevant in nowadays because the algorithms and the hardwares are so advanced that you can really make use of latest computing technology, like for example, HPC computing techniques, using GPUs to solve really large problems, even with full wave techniques like frequency domain or time domain. So, but if you are not having a big computing facility or you don't have access to really high-end GPU computing facilities, it's always good to understand these level of details within the simulation technology to make efficiently solve your problem, right? Even if you come up with an initial design of an antenna to satisfy your performance goals, you always need to employ a certain level of parametric study or optimization. Traditionally, what we do is called parametric optimization, where certain dimensions and material properties will be defined as a variable. And you ask the optimizer algorithm to change these variable values to meet your design goals. With latest technologies in the simulation, we also have non-parametric optimization. What that means is you just need the 3D model without any parameters or without any variables. The software can optimize it by adding or deleting certain structures or even optimizing the shape to meet your design goals. For example, there is something called topology optimization, where you can see the copper patch is being, deleted or etched away by the optimization tool to meet the performance criteria. That's at the planar level. You could come up with these kind of interesting shapes, which is not able to achieve through traditional parametric optimization. At the same time, you can also manufacture these because nowadays additive manufacturing is picking up and the trend is catching up to manufacture really complex design like the one you are seeing here. It's not always planar structures. You can employ this kind of technique in the conformal antennas as well as on different shapes like on antenna as well. Right. Now moving on to the real topic for today, which is the antenna array design. For array design, obviously you need to start with an element design first. Element has to satisfy certain criteria. So at the unit cell level or at the single element level, what you do is you do a unit cell analysis where you perform a simulation by defining a unit cell boundary condition, emulating as if this element is sitting in a really large array. Still, you can get certain performance factors like active element pattern, far field through array multiplication, and also different scanning performance. Once that is satisfied, that's the next stage would be to define or develop the full array. At the same time, you also need to probably develop the radomes or the protective covers to finalize the design. And you finally need to perform the full array scanning performance as well. This is the essential or a high-level workflow for the array design. So how do we achieve this? The simulation tool or CSD Studio Suite will make it easy for you. We have a well-established workflow. We call it array task. So in array task, what we do is we start with a layout. A layout is the canvas where you have the number of elements, spacing between the elements, and also the excitation. Like for example, if you want to beam scan, you need to have different set of amplitude phase combinations to steer the beam to different directions. So the software library has different kinds of layout, like for example, diamond shapes, hexagon shape, etc., etc. But sometimes you also need to come up with your own layout, right? That's also possible. So once your layout is defined, sometimes you have some missing elements or corner elements are not needed. You can remove it. Certain elements can be made passive, meaning the elements are present in the layout, but it's not excited. It's just a passive element dominated with its matched load. This is to reduce the edge effect of the array, but all the central elements are active, meaning it's forward, right? You also need to define the amplitude and phase combination. This can be coming from synthesis tool, which may be your own synthesis code, or you can get it from Antenna Maker's, the designer tool also. You can get it through our antenna array task in CSD automatically through import. Through a TSP file, what we call, which will have the position of the antenna, excitation, and rotation. This kind of arbitrary patterns and layout can come from different places, your own synthesis, or it could be from your partner vendors, or it could be generated from the tool like Antenna Makers. Once you have your canvas or the layout, you have two options. Obviously, first, we would recommend to go with the unit cell project to understand what's happening at the unit cell level. As a final validation or a final optimization, you have to build the entire full array to do that. Software will make it easy for you, because if you develop a unit or create a unit cell project, the software automatically creates all the boundary conditions, all the optimization setup, all the different scanning angles, everything is being set up automatically. You just need to press the button to start simulation for various use cases. For full array as well, from this click of a button, you can develop the full array automatically by the software and analyze the full array task. So let's look at what in each stage you have to do, or what kind of results you can expect at each stage. First of all, the unit cell analysis, we sometimes call it infinite array because that's like a single element terminated with a boundary condition, which is unit cell, emulates the behavior of an infinite array. You can see that the software automatically sets up a variable for scan angles theta and phi. And at the units level, it can really scan the wave propagation. You can see in normal direction how the wave propagation is from the antenna. But at certain scan angles, you can see whether the propagation is happening as expected, or is there some reflection or a blind spot, etc. For example, if you scan it to 45 degrees, you can see there is no real radiation from the structure. Actually, all the power is traveling through the surface, so it's creating basically a surface wave, but there is no real radiation out of the antenna. You can understand this by looking at the active element pattern. If you scan it at 45 degrees, if you look at the right picture, is the active element pattern. Active element pattern means how the gain typically looks like when you scan it at different angles. So if you scan it at 45 degree, you can see a blind spot. You can see the scale here, red being the highest value for the gain. But at 45 degree, you can see the value is quite low, meaning there is no real radiation, which is what we have seen in the electric field results as well. The same thing can be seen in S parameters. This is an S parameter plot plotted from 0 dB to almost minus 30 dB. Red color being 0 dB, meaning nothing is going in, but at high value of minus 30 dB means the antenna is well matched and the power is radiating. Here in the plot, x-axis I have different scanning angles in theta, and y-axis I have different scanning angles in phi. Right. Again, you can see at a scan angle of around 45 degree in theta, the S parameter is almost, all the power is reflecting back. It's all S parameter is almost 0 dB. That scan blindness, that's what we have seen in the active element pattern as well as this. Obviously, I mean, you're not going to achieve what you require in the first go. You have to do a lot of optimization even at this stage. Right, but the unit cell, since being only a single element analysis, this will be quite quick. You can see within the range of minus 20 to plus 20 scanning angles, the matching on this parameter is quite good, which is also seen in the active element pattern. Right. Now, to synthesize the full array, you need to get number of elements, the spacing between the elements, and what kind of excitation, etc., required to beam scan for the full array. To synthesize the full array, again, antenna megas can help you, which again consists of different antenna layout pattern. You can choose any of this ready-made pattern, for example, or you can customize this as well. So if you choose one of these and define what you want to achieve, like the gain and the unit element pattern, if you upload it to megas or use it in megas, it can give you the number of elements, spacing, and even the excitation pattern automatically for it. There are other more complex operations possible, like for example, if you want to develop a conformal antenna, you have the option to do Boolean operations on the basic layout, like translation, rotation, scaling, and also, putting your layout on a conformal shape like sphere, paraboloid, etc. As well as it also develops the magnitude and phase for excitation. Recently, we also have more advanced layouts, like for example, the one you're seeing here, sunflower with spatial distributed layout, which is quite efficient in suppressing side lobes. You can see the rectangular pattern has a quite high side lobe, which is in the orange color. But the green ones, the light and the deep or dark green colors, very less side lobes, which is achieved through this sunflower pattern. Right. And this is obviously also can be used for the reflector arrays, the metamaterial arrays, etc., etc. Not only for antenna arrays, but all the related the repetitive elements wherever you have this kind of application can be used. As I said, once you synthesize this layout from megas, you can read it in CST Studio Suite array task, where you actually automatically import all this information and can do full array task. But full array simulation can be quite complex because you are now dealing with a large array, which is an electrically large structure, and you need considerable amount of computing power to solve this. To help you with that, we come up with more smarter technique. One such is called simulation through simulation zones. What that means is you basically divide your large layout into different zones, and you have a reference element for each zone. Like for example, in this case, you can see all the inner elements are marked in green color, which is one zone, and you have a reference element there. But all the periphery elements are another zone each, and all corner elements are individual zones. You excite only the reference element in each zone and compute the individual far-field pattern called the embedded pattern, and reuse this embedded pattern for other elements in the same zone. Obviously, this kind of zoning is very coarser, you can expect some performance degradation or accuracy degradation here. But you can choose more smarter way to zone it. Like you can have more zones, like for example, or maybe 4x4 inner elements in one zone, and the exterior ones can be subdivided into multiple zones to achieve more higher accuracy if needed. But nevertheless, this will help you to reduce the total simulation time a lot and come up with exactly higher accuracy results in more efficient way or in shorter time. Right. The nowadays the arrays are not that straightforward. For example, 5G base station antennas require multiple different kind of elements for uplink and downlink. And even some kind of circular polarization needs to be achieved through something called subarrays. If you don't know or not aware of these kind of designs, what that means is if you have an array layout and each element in a layout will consist of another subset of 4 elements, which are basically rotated sometimes to achieve 90 degrees. You can mute yourself, will be helpful.
Itu antena.
Okay. So this is the subarray results coming out of those complex designs. So basically you have a large array where each element has a subarray of 4x4 rotated elements. And again, you achieve all this scanning through different scanning mechanisms, which I explained earlier. You can also expect this kind of complex port, like different scanning when it is scanned to around 30 degrees. How the power radiation, which direction it is flowing, this kind of UV plot can be seen. This is as I said, this is a circular polarized antenna here, and this is an RHCP antenna. That's why you can see in the RHCP plot the high power radiated. But in the cross pole, which is basically LHCP, in this case, nothing much is radiated. Right. When you design antenna or an antenna array, in reality, in a communication system, in the actual industry, it's also important to develop the microwave components like the power dividers, couplers, corporate feed networks for your array, as well as with filters, right? So software can also help you achieve these designs as well, right? For example, transmission line design.
Sorry, Mr. Regin, you have 2 minutes for your presentation. The time for you. Okay, thank you.
Till 10:30, right?
Okay.
Okay. So the filter designer tool, we have it, again, the filter synthesis tool. What that means is you can define your filter specification, pass band, stop band for your filter. And software can actually come up with this kind of complex design out of the design specification through a technology called coupling metrics, and can set up the optimization automatically for it. Right. In reality, you also probably want to check the actual antenna array-to-array coupling in the real world. For an example, if you have base station antennas, there will be multiple of those in the same mast or multiple poles within the same tower. And these can interfere with each other. So now this is really a large, complex simulation problem to solve. That's where we use something called hybrid simulation method, where we use multiple simulation technique or numerical technique combined altogether to solve subdomains like antenna array and the platform domain, which is the tower in itself, and hybridize through, say, time domain and integral equation solvers. From the user perspective, you must need to set it up, and the software will automatically do the hybridization. So software will do the subdomain division as well as the exchange of data between the domains. And finally, you can expect all the performance results like far-field array, S parameter, the array-to-array coupling, etc., etc. Lastly, but not least, you might also want to check the safety analysis of human body exposed to this kind of radiated fields. So all the electromagnetic devices needs to be complied with the industry standards, be it specific absorption rate or power absorption, etc., depending upon the industry you are or the communication technology you are using. The software tool, the CST Studio Suite, comes up with a library of body models, including voxel body models, to carry out these kind of bioelectromagnetic simulation and SAR studies. So this can be done at various scales and sizes, as well as for different body models, and also at different frequencies, including low and high frequencies. That brings me to the end of this talk. So in summary, the tools, a comprehensive set of solutions for various aspects of antenna design. So we are dealing with really large and complex problems, and basically a multi-scale problem where you need to employ multiple numerical technique like time domain, frequency domain, etc., to efficiently design and analyze the problem in hand. And of course, all these are available in our business platform called 3D Experience Platform, where engineers, different departments can collaborate each other seamlessly without breaking the connectivity and collaboration and the traceability for all the simulation data. Thank you very much for your patience and listening to my talk. I'm open to questions if you have any.
Okay, thank you very much, Mr. Rijin Sasendan and Mr. Gulam Reja. It is for successful presentation. Now I will move to the question and answer. For those who would like to ask question, please raise your hand if you will like to ask it live or write message at the chat room. Please mention your name and organization before asking your question. Also, your open camera and unmute. Oh, okay. The question from Mr. Widya Priawan. Please, Mr. Widya.
Okay, thank you, Mr. Teguh, for your chance for me to ask. So I am Widya Budiawan from Electronic Research Center. I want to ask to Mr. Rijin, is it possible to include environmental variable like wind, temperature, or building effect in antenna design using CST? Okay, thank you.
Yes, so it's the simulation tool or CST can do multiphysics simulation as well. So in general, all the technique I showed are basically only numerical or electromagnetic simulation solver, but the software itself has the capability to do thermal as well as structural mechanics simulation, and also coupled simulation as well. So for example, if you have an antenna system, antenna array, which is continuously operating 24/7 and maybe at high power because you want to communicate long distance, so there will be considerable heating problem, right? So software, when you do electromagnetic simulation, it will compute the power losses in the system, and these power losses can be read as an input for our thermal solver to calculate the temperature distribution. And sometimes if you have thermally linked conductivity or material property in electromagnetic domain, it can read back the temperature distribution and change the material property in electromagnetic domain and compute your electromagnetic results. So it can do from electromagnetic to thermal iteratively until a convergence reaches. So when you have like a heating problem, how it affects the electromagnetic performance can be analyzed. You can also extend it to structural mechanics problem, where if there is a deformation of the structure due to heat up, you can compute that, how the structure changes its shapes. And with the change of shape, if there is an effect or detuning in the electromagnetic performance, that kind of sensitivity analysis can also be performed in full multiphysics domain. Of course, you can also export it to standalone mechanical or thermal tool in our portfolio like Abacus also. But you can do this really within the CST Studio Suite environment itself.
Yeah, thank you, Mr. Rijin. How about Mr. Widya? It's enough for you? The answer from Mr. Rijin?
Yeah, it's good for me. Okay, thank you.
Okay, thank you, Mr. Rijin and Mr. Widya. And the others, audience, maybe will be give a question.
Iya, Pak. Saya boleh.
Oh, Mr. Yuyu. Mr. Yuwayu. Okay, please go ahead, Mr. Yuyu.
Okay, thank you. I have two questions. The first question is we have the CST for you have the CST how the features, yes, the features the any year is have the upgrade to the software for especially for the phased array antenna simulation, yeah, and the upgrade for the software for the GST.
Okay. Yeah, I mean,
Okay, Mr. Rijin, do you understand about the question?
Yeah, so basically, I mean, every year we
understand the question. Okay.
Yeah, every year we have a new software release with an upgrade, and antenna array is one of the topics where we research a lot, and we have many customers worldwide use software for this application. And what you have seen today are some of the latest technologies we implemented based on the industry requirements, like array task, subarray workflow, parallelly random design, etc. Even moving forward, we are also developing the solver extending to cater to the large design. Like, for example, finite element method, frequency domain method is traditionally works only for electrically smaller structures, right? But we have now new algorithms called domain decomposition method, with which you can still use frequency domain solver to solve really large, electrically large arrays, narrowband arrays, etc. So each solver or numerical technique is becoming more and more efficient. That's one thing. And also at the same time, we are developing many new workflows to make the array design efficient. Like, for example, simulation by zones, subarray simulation, etc. So our next release, CST 2025, is due for the release this month. We have a release cycle a bit early. So 2025 will release this month itself, this year. And we'll have a lot more technological advances in array. So we are launching a webinar as well. We are proposing a webinar soon, which will have a lot more details about the latest software and also array task.
Okay, so we must upgrade our software and not
necessarily
for the different.
The point is, if you obviously want to access the latest features, you might want to upgrade, but it's not compulsory that to do the array task or to do the array design, you have to upgrade, because these workflows were in existence for a really long time, right? It's not something we developed this year. So this is like a incremental process where each year you have certain upgradation. So if you are using an older version, still you can use it, but if you want to utilize the latest and greatest features, more efficient, what I have explained today, probably it's a good choice to upgrade it. We would definitely recommend you to upgrade, because you can access the latest advancement and latest workflows. And if you are a customer, all the application notes and the simple workflows are available for you to download from our website, our support website.
Okay, the second question, especially for the phased array antenna and the beamforming, the reality for the beamformer is by the TRM. Yeah? Do you know TRM? Transmit receive module. Yes. It is electronically. Yeah. It's the active devices there. So the simulation for the CST, it is the similar with the or to the gap for the reality?
Yeah.
What is it?
Okay. I don't know whether I understand it correctly, but to let me answer, try to answer that. So the presentation I showed you today are full wave simulation, full 3D simulation, which typically happens on the radiating element or the antenna. But you are looking at the system simulation, which including your transmit, receive radio module, including, say, for example, LNAs or PA, power amplifier, etc., to include also in your simulation. That goes into the system simulation. And we have our add-on tools or sister tools which cater to those. Like, for example, we have a new acquisition last year happened called MCAD. MCAD Engineering has a tool called Microwave Vision, which can really help you set up the full system. So that includes CST simulation of the antenna, and you can use the field pattern of the CST simulation along with the amplifier networks and other communication system networks to do a system simulation end to end. If you are interested, we would be happy to help you. Maybe one of our colleagues from NSI can reach you out and have a separate.
Okay, thank you. Nuhun Pak Teguh, thank you.
Okay, thank you very much, Mr. Rijin Sasendran, and see you. This time is over. Okay, thank you, and all of the participants. Thank you, Mr. Rijin Sasendran from the South System and Mr. Gulam Reja from Nusantara Sekom Infotech for the very interesting presentation as well as audience participant.
Welcome, and
okay,
thank you.
Before we close this session, on behalf of the Committee Ikramet 2024, we would like to thank and give the token of appreciation to Mr. Rijin Sasendran from the South System and Mr. Gulam Reja from the Nusantara Sekom Infotech, and recognized for the delivered Patron Talk at Ikramet 2024. We have learned about design antenna with the CST. I hope we can research together in the next time. Thank you, Mr. Rijin Sasendran and Mr. Gulam Reja. And now I turn back the time to the MC. Thank you very much, Mr. Rijin and Mr. Reja.
Yeah, thank you.
Thank you, Mr. Teguh Prarudi and Mr. Muhammad Gulam Reza and Mr. Rijin Sasendran. Thank you again for PT Nusantara Sekom Infotech and Dassault System for having brought to us the first Patron Talk. I hope you found this session informative and bring valuable insights. Moving forward, we will have our first keynote talk by Professor Witayachumnangkul from the University of Adelaide, Australia. This session will be moderated by Mr. Hanari Sesa. I would like to introduce you a brief profile of Mr. Hanari Sesa. He received his Bachelor of Electrical Engineering in 2009 from Gajah Mada University, Indonesia, followed by Master in Natural Science and Engineering from Gifu University, Japan. Currently, he is undergoing his PhD study in Electrical Engineering in University Teknologi Malaysia. Currently working as a research fellow at the Research Center for Telecommunications BRIN. His past work includes research in terahertz wireless communication based on EO sensor, also a part of project Horizon 2020 as a part of European project of PHOR. His current research interest is terahertz technology and more specifically in the frequency domain. Please welcome Professor Witayachumnangkul and Mr. Hanari Sesa.
Thank you, MC. Is my voice clear enough?
Yes, we can hear you.
Okay, Assalamualaikum. My peace and blessing to all of us. Good morning, ladies and gentlemen. Welcome to the first keynote talk today. I am Hanari Sesa. I am a researcher at Research Center for Telecommunications, the National Research and Innovation Agency. Today, I will be your moderator for at least maybe 40 minutes in the next. The first keynote talk today will be delivered by our distinguished speaker, Professor Witaya Chumnankul from the University of Adelaide, Australia, with the topic of subtractless integrated platform for terahertz communication and sensing. As we know that the terahertz technology is one of the promising technology from the future human applications. However, there are some issue and problem that need to be tackled. And here, the Professor Witawat will talk about a subtractless integrated platform that very can be used for the transceiver and compact system in terahertz technology. So before we proceed to the presentations, let me to introduce Professor Witawat. He holds a bachelor degrees and master degree from Electronic Engineering, King Mongkut Institute of Technology, Lat Krabang, Thailand in 2001 and 2003. And the PhD obtained from the Electrical Engineering, University of Adelaide, Australia in 2010. In 2014-2015, he was a research fellow of the Japan Society for the Promotion of Science at Tokyo University, Tokyo Institute of Technology, Japan. For 3 years, since 2017 and in 2020, he was a visiting researcher at Osaka University, Japan. Starting for 2023 until now, he is a professor at University of Adelaide, Australia. His research interests such as terahertz waveguides, meta-surfaces, antennas, radar, communications, metrology, and non-destructive evaluations. So before we proceed to the presentations, let me remind you to all participants who would like to ask questions, please use a raise hand function in Zoom, or maybe you can write your questions in the chat box. In the Q&A sessions, I will call on your name and please deliver for your questions. This presentation will be allotted for 40 minutes presentations, maybe 30 minutes for presentation, and the rest 10 minutes for Q&A. So please help me to welcome Professor Witayat. Professor Witayat, screen is yours.
Thank you, Mr. Hana. Thanks everyone for this opportunity for me to share our research activities here at Astromet online. So it's good that actually we listened to earlier talks from Dassault, because actually all my work that I'm going to present here was based on CST simulation. And so as you can see, the title is Substrateless Integrated Platform for Terrestrial Communications and Sensing. And yeah, let's dive into the structure of the talk. Oops, let me see. Yep. So the outline of this talk, I divide the talk into different sections. First, I give you a bit of background on terahertz technology, just that I'm sure that many of you here are aware of terahertz technology, but just to give you a background and motivation so that we are on the same page. And then, well, actually, the group capabilities, I removed that because the time might not be enough. And then we jump on right to the motivation of integrated platform, and then why we need such an integrated platform for terahertz applications. And then I'll move on to talk about existing platforms that were scaled either down from the microwave regime or up from the optical regime into the terahertz domain. And we can see what are the problems there that are not solvable by these adopted platforms. And then I introduce our own platform. We call it, sometimes we call it substrateless integrated platform, or we can call it effective medium clad dielectric waveguide platform as well. You'll see why later. And then after I introduce the platform, I'll show you some functional components and along with their applications, and then future plans and conclusion. Yep. So for terahertz technology, As you might have seen this diagram many times already, the terahertz domain or the terahertz band is sitting between the microwave and the infrared, and it is defined by the IEEE, ITU, and ACMA, is the Australian Communication and Media Authority, that this band is situated between 0.1 up to 10 terahertz. So essentially, it is sitting right at the transition from the electronics to photonics. And you can imagine it's quite difficult to access this band, as we will see in the next slides. But on the other hand, we can find a lot of opportunities to apply knowledge from the microwave domain and the knowledge from the photonic domain into this middle band here. And why are we so obsessed with this band? Right, so we can see that there are a lot of untapped opportunities, untapped applications that we can make use by accessing this band. For example, we can use it for spectroscopy. Many materials, they have unique fingerprints or spectrum signatures in this regime. So you can use this spectral signature to identify those materials, including those explosive materials or narcotics. And also because terahertz waves, they can penetrate like dry materials, non-metallic materials like clothing or packaging. That means we can use it for non-destructive evaluation, and we can use it for security screening as well. Well, you might think that microwave can do the same. The thing is that when you come to higher frequencies, you have higher spatial resolutions to give you more details about the hidden objects inside those packaging or inside those clothing. And further to that, because terahertz wave is very sensitive to a moisture level, that means it can be useful in medical diagnosis. Like in this case, you can see that people use it for detecting cancerous cells or tooth caries. And last and probably most important these days is that we can use terahertz waves to carry a large amount of data in a short range. So that is for 6G and beyond communications that we will talk more later on. So what's the problem there to access this band compared to the microwave or the photonics bands? So you see that there are a lot of challenges that we have to overcome, like including this terahertz generation and detection. So imagine if you want to use electronic circuits or microwave circuits to access this band. Right away, you see that the RC time constant will impede you from having such an efficient circuits in the terahertz bands. And also, if you work on metal, then you see that metal, the ohmic loss increase as a function of frequency. So it's not quite easy to overcome these losses. On the other side, if you try to scale those lasers, those LED to work in the terahertz band, the problem is that the energy gaps to radiate terahertz waves is too small compared to the energy gaps of those semiconductors materials, so it's not possible to lace directly in this band. And further to that, you have thermal noise that you have to overcome, right, when operating those photonic devices in the terahertz range. And well, people have resorted to this up and down conversion, like either you generate optical waves and then down convert to terahertz wave, or you generate microwaves and up convert to terahertz wave. This is the most promising routes to terahertz generation and detection. On the other side, like not only the generation and detection that is problematic, right? Manipulation of terahertz wave is not easy as well. So if you're familiar with those materials, like those microwave materials, you try to use them in the terahertz domain. You see right away that the loss, especially loss tangent, is not that low in the terahertz range. And I can say that there are only less than 5 materials that have very low loss in this range. And one of them that is most prominent is the float zone intrinsic silicon. The loss is very low. And that's why you see later that I'll stick so much to the silicon material. And some polymers, they have low loss as well, but not many of them. Right. Another issue with the manipulation of terahertz wave is tunability. Those varactors that you use typically in the microwave domain, they don't work as good in the terahertz domain because of the series resistance. And then also those tunable devices in the optical domain is not so effective in the terahertz domain, right? That's another issue. And also free space path loss and atmospheric loss, they are other key issues that we have to overcome, right? Then So far, like in the last 30 years, a lot of groups around the world, they have proposed many solutions based on different technologies. Either they borrow technologies from the photonic side or from the electronic side, and then they try to conquer this band. But at this point, we can see quite clearly that there's no all-round winners. Like it's not only one solution would conquer this band. So in my view, it is possible to tackle those challenges and conquer this band to access and to make use effectively only if we use hybrid solutions. And one opportunities or maybe misconception is that in the torus domain, atmospheric loss is too high. You cannot use it to propagate wave that far. You cannot use it for communication that far. The thing is that it's partly true. If you see this diagram, which I borrowed from my collaborator, so you see that this is the link budget that combine the atmospheric loss and the free space path loss and show it in the torus domain. The x-axis is from DC up to 1 terahertz, and the y-axis is the link budget. The dashed lines, they are for free space path loss, which basically is intrinsic, right? It's not related to the properties of materials. And the solid lines, they are for the combination of free space path loss and atmospheric loss at different distances. Say, if you see, for example, this blue line, light blue lines, that's for 1 kilometer's propagation distance. You see that the combination of those losses is very high, especially at 1 terahertz. You have a huge loss, right? It's beyond 240 decibel. That's not something practical. On the other hand, if you look at some bands, for example, between 200 to 300 gigahertz, you see that there's a clear atmospheric windows here. There's not much atmospheric absorption. So you see that there's a water vapor absorption at about 200 gigahertz and another line at about 300-ish gigahertz. But between that, there's nearly no water vapor absorption at all. So the only loss you have to contend with is the free space path loss. And in this case, for 1 kilometers, the free space path loss is about 138 decibel, which is still reasonable. It's not that low, but it's still manageable, right? Especially if you have high gain antennas and amplifiers, then this is something that you can manage to conquer. And that is the reason why the IEEE has recommended that this band between 252 gigahertz up to 325 gigahertz is good for wireless communications, point-to-point communications, right? So, and let's have a look why we need an integrated platform. What's the problem there? You see, so far, you see when you read those terahertz papers, you see that the demonstrations, they were based on tabletop equipment, something bulky as in these figures, right? This is good for lab demonstration. You can show fancy applications based on these gears. But the problem is that if you want to scale, if you want to take it out of the lab to demonstrate in the field, right, then it's not possible because those equipment, first, is very expensive, second, is very delicate. So what we need to do is that as in other frequency bands, we should put these gears into a portable platform, in this case, a handheld device, eventually. So this is the motivation that we want to work on the integrated platform. And then what we need in this platform, let's have a look. Right. First, we need broadband operation. That's important because we are talking about the bandwidth, like a fractional bandwidth of 40%. This is something that is uncommon in other bands, right? In the optics band, you talk about fractional bandwidth of only a few percent. And likewise, in the microwave band, maybe the fractional bandwidth is about 10% and so on and so forth. We need 40% fractional bandwidth to make use of broadband bandwidth available in this range. And broadband operation means low loss and low dispersion. And next thing is that the platform must be able to perform complex wave manipulation as well, right? Polarization, filtering, polarization, rotation, modulation, etc. So it should be possible on this platform. And the fabrication must be simple enough that it allows mass adoption for enterprise or consumer products, right? Otherwise, then if it's very delicate structures, then it's not worthwhile. And last thing is that it must, or it should be interoperable with existing terror sources and detectors so that we don't have to build everything from scratch. And in this case, this is a conceptual diagram to show how the platform might look like in the future. Like you can combine many devices on this platform, right? And well, let's have a look at the existing platforms or waveguides that people have implemented so far. So as I said, either you can borrow the techniques from the microwave domain or from the infrared domains and scale them to work in this range, right? That's what people have done so far. So you see, for example, on this page, they've scaled down those microwave structures, microwave transmission lines to work in the torus domain, including microstrip line. I'm sure that you're familiar with that. Coplanar waveguide, that's the substrate integrated waveguide, and that's the substrate integrated image waveguides. Well, they work in the torus domain, like 300 gigahertz or 90 gigahertz or even higher. But the problem is that if you look closely, all these guiding structures, they are made of metal. And if you remember earlier, I mentioned that metal at higher frequencies, they have higher ohmic loss, and the skin depth is shallower. That comes the problem because the loss of these waveguides, they are very high. I just checked last week, the waveguides, such a waveguide, the loss can be as high as 10 decibel per 1 centimeters or more. So that's like, you better use that as absorbers, right? On the other hand, we can do away with those metals. We can just adopt those photonic structures into the torus domains. Like basically is the dielectric waveguide, but then you need the substrate, right? For example, this I mentioned that high resistivity silicon, the loss is very low, but it cannot be hanging like that, right? So you need a substrate to support it. And the substrate comes with the loss, the additional loss that you have to take care of, right? It's not lossless, of course. And those cores and VCB, the loss is not that low. And one way to compete or contain the loss is that, for example, this work, they etch away the part of the substrate right below the guiding structure. So to reduce the loss, that's fine. But first, that increase fabrication complexity. And second is that they use these struts to support the waveguides. And the struts, they have the separation of about 1 wavelength. So these work as radiating structures, just like leaky wave antennas. The third one, again, they use a substrate to support the guiding structure. So it comes with the substrate is additional loss. And the last one is from my collaborator in Osaka University. They did not involve a substrate. It's just a silicon waveguide, and they perforate holes into a silicon wafer to create this photonic crystal waveguides. The problem is that, well, the loss is low, but if you work with photonic crystals, you know that the dispersion is high and the bandwidth is not good. Right, so those are the problems. Now comes those challenges that we have to conquer, right? So far, as I mentioned, people either scale those microwave platform into the torus domain or optical platform into the torus domains. But the problem is that they don't work as good as when they are operate in their own domains, right? It comes the problems of efficiency, bandwidth, functionalities, complexity, and interoperability. Those are all the problems that people face so far. And actually on this diagram, on its own, it suggests us already that, well, in the microwave domain, they have their own MMIC platform. In the optical domain, they have PIC platform. Why would we adopt those platforms given that the MMIC wouldn't work in the optics domain, nor the PIC would work in the microwave domain? That means it suggests us that, hey, actually, the terahertz domain should have its own platform that is created from the ground, right, to satisfy those requirements. And that comes this platform, we call it effective medium-class dielectric waveguide or substrateless dielectric waveguides, right? Let's see the structure. Now we start with a single silicon rods here. And as I mentioned, the silicon, it has very low loss in the torus range. The loss tangent is about 0.00005, something like that, which is very low, right? And in this case, of course, you can just use a single silicon rod and it can guide torus wave along the core through total internal reflection. The problem is that if you want to make a platform, this alone wouldn't work, right? You need a substrate to support the structure. Then comes the problem. Now we are back to square one. We have this substrate to support the guiding structure. Then we add more loss. This is not what we want, right? So what we do is that we perforate holes around the core, right, to create an effective medium. And there's no need for substrate. And let's have a look at the structure from the top view. Here you can see that we grab a single silicon wafer, we start perforating holes around the core, and then like these holes, the trick is that the periods or the separation between those holes, they have to be less than half the guided wavelength. Why is it so? Because by doing that, by satisfying this criterion, then the wave that is being guided by the core would see the site, these areas as a new material. We call it effective medium cladding, because the hole size, or sorry, the period, they are too small, so the wave don't see it as a separate material. They see it as a homogeneous material, and then that means the core has one refractive index and the cladding has a lower refractive index. It's an average between silicon and air. So that means the wave can be guided along the core through total internal reflection. And well, you might think that this looks pretty much like a photonic crystal waveguide. I assure you that it's not a photonic crystal waveguide. And this is the key. This is the key. Because with the photonic crystal waveguide, the period is about half the guided wavelength, right? By just reducing the period, the mechanism is completely changed from a photonic crystal waveguide to a dielectric waveguide. And another benefit that we can have from this platform is that because we can control the hole size, that means we can access an effective refractive index values that we want by just changing the diameters of those holes. Like in this case, the x-axis is the diameters in micron, and the y-axis is the effective refractive index that you can calculate from this 2D Maxwell-Garnet's approximation. You can see that by increasing the hole size, then the refractive index would start to reduce. And that means virtually you can have as many virtual materials as you want in this range, and the loss is still low, right? So this is a good thing. And to confirm that it's not a photonic crystal waveguide, then we perform field distribution calculation. So typically a photonic crystal waveguide would support only a single mode, right? And it's very dispersive. In this case, we check the dispersion is low across broadband, and we check it can support two orthogonal modes like EX11 mode and EY11 modes here. And you can see that one guided wavelength is much larger than the period of those holes, right? This is definitely the characteristics of a dielectric waveguide. Right, next, so we fabricate the sample, like a straight waveguide to begin with, the simplest thing to test. And what you see here is just a piece of silicon, and then we perforate holes into the silicon to create a straight waveguide, and we test it with just a standard French waveguide. Then we measure the loss to begin with, and you can see that the attenuation for EX is below or about 0.04 per centimeters, and for EY is even lower at higher frequencies. And at this point, I can tell that the waveguide still hold the records of lowest loss in the terahertz range, with a propagation loss of 0.01 decibel per lambda. Right. So we test the performance of this straight waveguide by injecting this video signal being carried by the carrier wavelength or carrier frequencies of about 300 gigahertz. So you can see that like the video that is displayed on the screen behind is uncompressed 4K video that is being carried on this 300 gigahertz carrier frequency across this straight waveguide. If you remove this connection, then the video disappears. And then if we reconnect this connection, then the video would reappear. So this confirms that such a waveguide can support broadband operation and with low dispersion and low loss. That's the first step to begin with. That's back in 2017. And then we move on further to implement many other devices on this platform to show that, well, it's not just a straight waveguide we can do a lot of things. The first thing is this Lundberg lens, right? You can see that, well, we can use the same platform. We create a Lundberg lens, or basically an antenna, to interface between waveguide and free space. So in this case, you see that we have 7 feet lines coming into this Lundberg lens, and the Lundberg lens, it behaves as a convex lens to collimate the beam into the far field. And, well, you have 7 feet, you expect that the beam would come out at 7 directions. And this is the simulation results. You can see that we have the feed here at this tip, and then the wave starts to diverge inside this lens, but then at the same time it gets rectified, and the wave front is sort of planarized at the output. Well, the structure was quite large back then, so the simulation from my memory, it took about 1 week to simulate one structure, so we did not do much optimization. So you can see that it's a bit over focusing, but that's fine. We did the measurement compared to the simulation. The gain is above 20 decibel across broadband, and then that's the measure radiation pattern. Well, we measured just half of the radiation pattern because the other half is symmetric, right? You can see that we have fan beam projected into far field. Furthermore, we implement another type of antenna on this platform, right? This is a leaky wave antenna. So that's the input port, right? You feed the wave, torus wave into this port, and then this waveguide start to leak into the slab. Depending on frequency, then the lowest frequency would leak first, but it would leak into this direction, and higher frequency would leak as well at some point in the waveguide into different directions. So you can see that this is the behavior of leaky wave antennas, and then that's the fabricated sample. We sit it in a 3D printed stage together with this convex lens just to increase the gain. You can see that this is the measure results. The x-axis is, of course, frequency, and the y-axis is the angle. You can see that by sweeping the frequency, we can sweep the angle of radiation from this waveguide. So what do we do with these leaky wave antennas? Well, you see this video. Hopefully it shows up. Yep. Should work. Okay, that's Harry, my PhD student. So the antenna is sitting there, the leaky wave antenna. So right now he's holding a metal rod in front of this leaky wave antenna, and you can see that we can localize the rod position in real time. Well, that might not be fascinating enough because, well, you can use a camera to do that. But the trick is that we know that torus wave, it can penetrate through opaque screens. And that's what he's doing now. He put an opaque screen in front of the antenna, and then he holds the rod, and you can see that the rod is still visible on the screen. Right. And another possible application is that we can use it for liquid sensing. So again, the same leaky wave antenna, but in this case, we have these 2 canisters. To begin with, they are empty, so they show some reflection signature in the radar, in the leaky wave antenna radar. Now that he starts to pour ethanol on the left canister, you can see that the reflection signature changed slightly because the ethanol has higher index than air. On the right hand side is pouring water, and you can see that water reflects stronger signature in the radar, right? Because water has higher index than ethanol in this range. Okay, now comes like we finished the application of sensing. Let me show you some applications in radar. Sorry, in not radar application, in communications. So in this case, what we do here is that we again grab a single silicon wafer. We start to perforate holes into the wafer. Then you can see that what we have is the input waveguides here, right? And we have 4 output waveguides. So how does it work here? For this frequency division multiplexing, the thing is that if you feed in a combination of waves with different frequencies into this port, then this device can separate those frequency components into different output ports. So you start with the lowest frequency. This is from simulation. So you can see that it leaks into the output port here for lowest frequency components, and then slightly higher frequency components, it leaks into the second output port, and so on and so forth. So this is exactly the operation of frequency division multiplexing. So you can see that that's the fabricated sample sitting in the measurement system, right? The top one is from the simulation. You can see that we have 4 output channels separating those waves into 4 output channels. And the bottom ones is the measure results. You can see that they can separate the waves into 4 output channels. There's a slight shift in frequency response. That's just because the wafer is slightly thinner than what we expected, so that's not much of a problem. And if we use this device for communications, then you can expect that it can support over 200 gigabit per second data rate in terrestrial communications. And next is this polarization division multiplexing. So in this case, we have this input port. Then just let me know if I'm running out of time, but I think it's nearly there. So we have this input port that combine 2 different polarizations, and then this device can separate these 2 polarizations into the 2 output ports. EX would go there, EY would go there. So this is the operation of polarization division multiplexers, right? And if you zoom in, again, it's just silicon and air, and there's nothing else. We did not include any other materials. It's just a silicon wafer, and we perforate holes there just to create this matrix. And that's the fabricated sample. Then we measure co-pole and cross-pole. Like co-pole is for EX wave appearing in the EX port. And then you can see that the transmission is very high and the insertion loss is low. Same for the EY waves that appear on the EY port, and that's broadband, right? And the crosstalk, meaning that the EY component that appears at the EX port or the EX component that appears at the EY port, they are below -20 decibel in broadband, right? And we did some demonstration with this polarization division multiplexers as well. We put them back to back to transmit the 2 video streams across one single channel. So that's the first one to combine EX and EY. That's the second one to separate EX and EY. So EX carry one channel, EY carry the other channel on the same frequency, right? So now, YJ, he was a PhD student here. He disconnect the EX part, and you can see that the video disappear. Now he reconnect the EX path. Then the video reappear, right?
Professor, apologies, but we have 2 or 3 minutes left.
Okay, almost done. Thank you for your reminder. Yep. All right. Then the same for EY. Yeah. So this is the first instance for integrated polarization multiplexers in the torus domain. Right, and I think this is almost the last. And then this is the switch application. So again, we can create a switch to direct the wave into different directions based on this resonator. So essentially, maybe let's have a look at the operation, the diagram here. The input port is here, and then if you excite this resonator, then the wave would bypass the first disk and it would couple into the second disk, which is not excited, and it would couple into this waveguide and project into the far field in this direction. So we just add this Lundberg lens to demonstrate that we can project the beam into different directions, and then that depends on the configuration of the light excitation. In this case, if there's no light excitation, then wave comes in, coupled to the first disk, come out at this port, projected into this direction. That's the measure results compared to the simulation. And in the second case, I just mentioned, so we excited the first disk, then the wave would bypass the first disk, couple to the second disk, and come out at this port, goes there. And when we laser excite both disks, then the wave would bypass both disks and come out at the N5 direction here. Right. And the last one is that we can integrate active devices on this platform as well, but we need to add this metallic structure on top, right? We don't want to use metallic structure, but well, without that, you can see that the wave is deep inside the core of the dielectric waveguide. So if we want to integrate some active device, then we need to bring up the wave to the surface, and that can be done by using this lattice structure metallic lattice structures. That's the fabricated sample sitting in the measure system, and we excite the waveguide with the light excitation just to show that how sensitive it is to the disturbance, right? Okay, the future plan then, well, this is too detailed, but essentially I envisage that it's possible to create those front ends like Torus communication front ends on this platform. And then the front ends would combine all the devices that are necessary for communications, including filters, multiplexers, modulators, and sources and detectors all together. And we can expect that the speed is very high, above 1 terabit per second, and the power is very high as well. And we can communicate over 1 kilometers point-to-point communications, right? So in conclusion, then I've shown the first integrated platform for terrestrial waves, and it can achieve broadband, low loss, low dispersion, and the effective medium is the key to the operation and versatility of this platform. And we can have various functions for wave manipulations, and we expect that this terrestrial IC in the future will be standing side by side with MMIC and PIC, right? And before I conclude, I'd like to thank my students, my collaborators, in different universities. And the last slide is that I happen to will be in Bali next week for APMC. If you happen to be there, there'll be 5 talks from our groups there. Like if you're interested, then let me know. And if you'd like to discuss further, feel free to tap me in the shoulder. I'll be there and happy to discuss with you. Thank you very much.
Thank you very much, Professor, for your valuable information and some insightful presentation in the terahertz technology, especially for subtrustless integrated platform. So I think we begin in the Q&A session. So I invite to all of you, all of participants would like to ask questions, please use a raise hand, and then you can directly ask a professor in this topic.
Please.
So I will, yeah. Okay, Mr. Ken Paramawida, you can ask directly to Professor. Please go ahead.
I don't think I can hear Ken. Does it work? Seems doesn't work. In the meantime, yeah, Ken is no stranger to me. He was my master student back 5 years ago. Yeah.
No?
Yeah, seems okay now. Can you speak again?
Okay. Hello.
Yeah. Oh, yeah.
Long time
Okay.
see. How are you?
Yeah. Good. Nice to meet you here.
Nice to meet you. I want to know about your opinion about the future of consumer terahertz device. Maybe in the near future, will be there? Can we like buy terahertz device and use it as a consumer device?
Yeah, at this point, my honest opinion is that it will be more for enterprise devices, like because you see that the main applications, if you talk about 6G or 7G, and it's point-to-point wireless communications. So when you talk about point-to-point communications, it's more like base stations for mobile towers, for example. But on the other hand, it's not like, okay, another example is the airport screener, like airport scanner. Yeah. Then in that case, you still, like, it's not for consumer. One example that is probably closest to consumer is that if you think about terrestrial device in your mobile phone, then again, if you want to use it for communications, it has to be for point-to-point communications. Maybe it's good for downloading a large amount of data onto your mobile phone, because like you see that the data rate is above 1 terabit per second. If you use it on your mobile phone, that means you can tap on a kiosk and quickly download a chunk of movies, like hundreds of movies, before you board the plane or things like that. And probably another applications could be that is for if you think about terror sources and detectors on mobile phones, maybe it's for some scanning capabilities, or hand gesture recognition, like use it for, I call this human interface device. When you wirelessly control your mobile phone. Yeah. But I think most likely it will go to enterprise devices or enterprise products before it reach consumers. Yeah, this is my view. Yeah. Nice to meet you. Yeah.
Thank you, Mr. Ken. We have several questions from the chat box. I think I can read
please.
for you. From the Professor Yusuf, is there any effect to human body by using terahertz band in the applications?
Yep, I think that's a good question. So far, if you read those papers, there are conflicting information about the safety to human exposure. But at this point, I would say, like with the radiation, with the power level that we use in the lab, is not harmful, right? Like for example, those demonstrations that I show you, the source power is only about 100 microwatts, or the best case is 1 milliwatts. So that's still very low. Like even though we have some higher power sources up to like 80 milliwatts, still quite low. And then we use it in the lab all the time. We did not even feel the heat in the lab. It's more like the heat is more from those like huge oscilloscopes and function generators, but not like by direct exposure to terahertz wave. I cannot say for sure that it's super safe to human exposure. I think there need to be more studies in this domain, right? But at this point, there's no indicator that it would be harmful to humans.
Okay, great. Maybe the last questions for the chat box, as regarding about the processing parts.
Yeah.
What kind of hardware did you use in the post-processing part for your terahertz 3D imagings?
I guess we mean radar imaging. Yeah.
I think.
Good question. That one, I believe, is just a lab computer. Actually, it's an office computer, because the student Harry, he did this in real time to display this information, and in the lab, actually, it's just the this mini computer. I just want to save space, so I have this tiny computer sitting in the lab, and then it seems to work fine. We don't need high processing power, and knowing Harry, I believe that he used Python for this.
Oh, okay. Maybe the last one.
Yep,
I'm sorry,
please.
but how to arrange for millimeter wave and terahertz? I don't know what you mean. I think how to arrange for millimeter wave and terahertz lab. Oh, the questions. Maybe you can ask one this simple or maybe briefly. How to arrange for millimeter and terahertz lab? Maybe you can answer or not. Just for.
I'm not sure. What's the question? I'm not clear.
How to arrange millimeter and terahertz lab? I think how we can build millimeter and terahertz lab. I think
to access. I guess I'm not sure if you mean to access my lab or to establish a new lab. I guess the answer would be quite long for both of them. So maybe if you're interested, either drop me an email and we can talk on Zoom at some other time. Or if you happen to be in APMC next week, then yeah, just feel free to tag me, and I'm happy to discuss with you further there.
Okay. Great, because we have a question time. So I think this is the session of Q&A is already finished. And again, thank you very much, Professor Witawat, for your valuable information. This is a great about the terahertz. I will sum up maybe the conclusion that terahertz technology is very promising, but there are some problem here. I think with the subtractless integrated platform and other applications such as liquid wave antenna, so on and so forth, we can maybe bring the terahertz technology into society, into reality in the next decades. I think so. We have a token appreciation for your presentations.
Okay, just stop sharing. Yeah.
Okay, good luck for your research, and thank you for the participant for the delightful presentations.
Yep.
So I will back to the sessions to the MC. Thank you very much all.
Thank you very much. Thank you very much, everyone, for your attention. Bye for now.
Thanks to Mr. Hanari Seta for moderating the first keynote talk, and thanks Professor Witawat Witaya Chimnankul for sharing his expertise with us. Shortly, we will have a short morning break, and we will rightly after commence the parallel sessions of 1 and 2 in around 7 minutes. Also, I would like to remind you for the presenter to keep the naming convention according to the guidelines to make sure presenters are in the correct breakout rooms. Also, I would encourage you to stay logged on during the short break. And for the presenters that are in their assigned sessions, please turn on the video for the whole session, including when you are not presenting. Please have your presentation slides ready for the Q&A sessions. And there are other 2 things for presenters to keep in mind during your presentation sessions. These 2 things are mandatory for your completion of publication with IEEE. First, to attend your question and answer session, and second, to fill in the attendance form as the presenter during your parallel sessions. For all the participants who want to ask some questions during the Q&A sessions, please use the raise hand menu or type in your question in the chat room. For the breakout rooms, the presenters will be directly assigned by our host according to the schedule. The breakout room 1 is for parallel session 1, and the breakout room 2 is for parallel session 2. And for the rest of participants, you can switch between breakout rooms to find presentations that interest you. I would like to thank again to all presenters, participants, esteemed colleagues, and distinguished guests for taking the time to be here today. Thank you, and please enjoy the conference.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation, and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability, and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience
Recording in progress. Good morning, everyone. In this parallel session, good morning, everyone. This parallel session. My name is Runik Nur Hayati from Research Center from Research Center for Electronics, National Research and Innovation Agency (BRIN). In this session, a half hours ahead, I will moderate to electronic materials, components, and circuits. In this session, we will have is Mr. Sorel Ivanov, the mic. The next presenter, the second presenter is Miss Nadia Larasati Kartika from National Research.
Yes, I'm present here.
Okay, let's wait. And for the fourth presenter, Miss Nel Fiani from National Research and Innovation Agency of Indo. Miss Nel Fiani. Okay. Maybe some presenters are not here yet. For the fifth presenter, Mr. Robert Victoria from National Research and Innovation Agency.
Yes, is here. Yeah, of course. Can you hear the voice?
Okay. Thank you. Yes, I can hear your voice. Thank you, Mr. Robert. Mr. Sorel, Mr.
Yes, I'm
Almas,
here.
and Ms. Nelviani, are you there?
Yes, I am here.
You are Mr. Almas, okay.
Yes.
Mr. Sorel
Okay.
and Ms. Nelviani. Ms. Nelviani. Okay, maybe while we are waiting for Ms. Nelviani, so before we start, I will remind you some notes for all the participants and presenters in this session. For all presenters in this session, number 1, please keep your video on until the session is finished. We will have a screen capturing session by the end of presentation or by the beginning of the presentation or when all the participants are present. Number 2, please fill out the attendance form during the session. Our co-hosts will send you the link in the chat room. And number 3, the time for each presenter total is 15 minutes, including Q&A session. Please make sure you are present during your questions and answer sessions. For the participants who would like to ask some questions, please use the raise hand function at reaction menu or on your Zoom, or you can write down on the chat box. Okay, let's go to the presentation. Maybe we will have a photo session later. Okay, it's time for the presentation. For the first presenter is Mr. Sorel Ivanov. The video presentation will be shown. Please, the time is yours.
Hello, everybody. My name is Sorel Ivanov, and I'm a master of engineering physics student at ITB or Institute of Technology Bandung, and I would like to thank the committee of the 13th International Conference on Radar, Antenna, Microwave Electronics, and Telecommunications, ICRAMET, for allowing me to present our paper titled Exploration of Indium Sulfide as an Electron Transport Layer for All Inorganic Cesium Lead Bromide Perovskite Solar Cells. What is a perovskite? A perovskite is a type of crystal structure which usually has a crystal structure of ABX3, where A can be a molecule such as metal ammonium from a medium, or a single atom such as cesium, and B is usually metal atoms such as lead, tin, bismuth, and etc. And X is usually a halide atom such as chlorine, bromine, and iodine. Usually, perovskite solar cells are methyl ammonium lead iodide, which is an organic halide-based perovskites, but it still has problems in stability, where it is unstable under high humidity environments such as Indonesia, and needs a special environment, nitrogen-filled environment such as a glove box to fabricate the methyl ammonium lead iodide. So we use cesium lead bromide because of its stability under high humidity, and it also can be fabricated outside the glove box. For the electron transport layer, we use indium sulfide or a sulfide-based electron transport layer because it is much more easier to fabricate or to deposit the layer, because it only needs 80 degrees and compared to other oxide-based electron transport layers such as tin oxide or titanium oxide, which needs a higher and more complicated method of depositing, because it needs to oxidize the material, such as tin oxide needs 200 degrees and titanium oxide needs at least 500 degrees, but indium sulfide only needs 80 degrees. And cesium lead bromide also has such a wide band gap of 2.3 electron volts, which is suitable for transparent and indoor photovoltaics. It is more stable. It can be fabricated outside the glove box, and is suitable for low-cost solution-based processing. That's why we use a cesium lead bromide as the absorber and indium sulfide as the electron transport layer. For the fabrication process, first we clean an FTO substrate with deionized water, acetone, and isopropyl alcohol under ultrasonic bath, and we dried it, and then we treated with a UV ozone. And after that, we deposited the indium sulfide by chemical bath deposition method with using indium sulfate and thiourea in water as the precursor, where the FTO substrate was dipped into the solution and heated until 80 degrees and was timed to determine the thickness, where the variations are 1, 3, 5 minutes. After depositing the indium sulfide layer, we deposited a cesium lead bromide layer using a multi-step spin coating process, where a 1 molar solution of lead bromide was deposited first and then annealed to 90 degrees, and then we deposited on top of the lead bromide layer a solution of 0.01 molar of cesium bromide, and we repeated the process 8 times until a yellow layer was formed. Then we annealed it at 250 degrees Celsius to create the cesium lead bromide layer. And after that, for the top contact, we use a carbon paste from Dynamo, which was doctor bladed on top of the cesium bromide to create the perovskite solar cell. After that, we did some characterizations for the electron transport layer or the indium sulfide layer. First, we characterized the morphology of the layer using a scanning electron microscope to see how uniform was it, and we can see from the image that it was homogeneously covered the FTO layer. And also, one characteristic of an electron transport layer, it needs to have a high transparency. So we use UV-Vis or ultraviolet visible spectroscopy to determine the transmittance of this layer, where we can see from the UV-Vis graph that it is 80% transparent and is quite transparent, which is quite good for an electron transport layer. We also would like to determine if all of the FTO was covered by using a cyclic voltammetry measurement using a ferro-ferri solution to see the oxidation and reduction reactions, where we can see that the oxidation reduction reactions are quite high on the bare FTO substrate, but when we deposit on indium sulfide layer, it was highly reduced, which shows that the indium sulfide layer was uniform on top of the FTO substrate. We also characterize the cesium lead bromide on top of the indium sulfide, where we can see all of the peaks on the XRD, which matches to a cubic structure of the cesium lead bromide, which means that we have created cesium lead bromide on top of the indium sulfide layer. And we also would like to see the morphology of the layer. So we use a scaling electron microscope to see the cesium lead bromide layer, and we can see that it has a relatively small grain size. We can see that some grains are 300 and some grains are 500. So we say that it's between 300 to 500 nanometers. And we also use a solar simulator to determine the characteristics or performance of the device, as we can see from this JV or current density over voltage graph, where we can see the efficiency of the indium sulfide layer is 0.7% and a short circuit current density of 1.3 milliamperes over centimeter square, a VOC of 1.165 volts, and a fill factor of 47%. For this sample, we also measured the indium sulfide thick, where we waited a little bit longer, around 5 minutes, to deposit the indium sulfide, where the sample labeled indium sulfide is only 1 minute, and we can see that the efficiency dropped to only 0.38%. And we also tried making a device without any electron transport layer, which is labeled no ETL, and we have an efficiency of 0.43%, which is more than the indium sulfide thick, but we can see that the voltage, or the VOC, the open circuit voltage, is quite less, only 0.6085, which means that an electron transport layer, such as an indium sulfide-based layers, is actually quite important for the solar cells. And we would like to do more research on this ETL and also more research on the cesium lead bromide absorber layer. And for the summary, a cesium lead bromide fully organic based perovskite solar cell using chemically bed deposited indium sulfide electron transport layer on top of FTO was successfully fabricated. And we have determined that the relatively small grain size of the perovskite on top of the indium sulfide may have a big part on why the efficiency is only 0.7%. But we would like also to do more research to figure out why it has such a less efficiency compared to other oxide-based electron transport layers. Thank you, and I'm waiting for your questions.
Okay, thank you for the nice presentation. Now it's time for question and answer session. We have 4 minutes for Q&A session. If any question, you can raise your hand or write on the chat box. Okay. So while waiting for the question from the audience, so maybe I will ask the question. So on if I'm not mistaken, on the slide 5 about the result of IV or JV, so it's shown that the efficiency of the device with electron transport layer is higher, right? But I see that the JAC or current short circuit is higher, if I'm not mistaken. For the device without ATL, the JAC is higher. So can you explain the correlation between the JAC and the efficiency, and why the JAC of the device with ETL is lower than the device without ETL?
Yes, thank you for the question. So why the JAC for the sample without is higher. Maybe we think that because the cesium lead bromide is on top of the FTO, the electrons are more easily transferred to the FTO substrate. So that's why the current density is higher than the sample with an ETL of indium sulfide, because the electrons cannot easily transfer in the indium sulfide layer. So that's why the short circuit current density is much lower than the one without an ETL.
Okay, thank you for your answer. But okay, I'm waiting for the question from the participants. Okay, maybe I will continue to the question. So from the parameters of JV, like efficiency, GAC, VOC, or FF. So which one is more influence the efficiency? GAC, VOC, or FF?
I think
in this
for
device.
the parameters that affect the efficiency, all of the parameters actually affect the efficiency, but I think the most influential one is the fill factor, where the fill factor has a big part in the efficiency, where a higher fill factor can lead to a higher efficiency in some devices.
Okay, but how about the VOC? I can see that the VOC of the sample with ATL is like 2 times compared to the device without ETL.
Yeah, because I think it's about the proportion about the JSC, VOC, and the fill factor. Because in the sample without an ETL, the JSC is much higher, but the VOC is much lower. But for the other samples, especially the indium sulfide sample, the VOC is higher, but the JSC is lower. And also the fill factor is much better at 47%. So it will have a higher efficiency.
Okay. Thank you for the answer. So I think no question from the participants, and the time also is over for the first presenter. So please give applause to the presenters. Thank you for your presentation and answer the questions. Okay, before we I will conclude later. So because all the presenters and all the audience have already been here, before we go to the second presenter, I will ask to all presenters and participants to open the camera. We will have photo session. There are 3 pages, so I will count from the 1 until 3 from the first page. So please open the camera. Okay, I will count. So our co-host will capture. Okay, ready? 1, 2, 3. Okay, now the second page. 1, 2, 3. And the last page. 1, 2, 3. Okay. Let's continue to the next presenter. We have Ms. Nadia Larasati Kartika, National Research and Innovation Agency. And the video of the presentation will be shown. Please, the screen is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. My name is Nadia. I'm from BRIN, and today I would like to present our study about material simulation for thermoelectric applications. This is the title and the collaborator in this research. I'm going to start with the introduction. Thermoelectric generator is a device that can convert heat divergence into electricity and vice versa. This is the thermoelectric materials which play an important role in the devices, and this efficiency is quantified by the dimensionless figure of merit, or ZT, as shown in these equations. Many materials have been used for the thermoelectric applications, especially those who have semiconductor behavior. In this study, we focus with the perovskite oxide with alkaline earth elements such as calcium, magnesium, strontium, and barium for the A side, and tin or stannic for the B side. These materials show high electron conductivity, abundance in nature, show stability at high temperatures, and environmentally friendly. There are a lot of prior studies about these materials. However, most of them mainly focus on the bulk structure. Meanwhile, we thought that the thin film thermoelectrics could offer better benefits than the bulk because they could enhance the performance through quantum confinement effect. To shed some lights in this area, we explore the materials under conditions that mimicking thin film environment. To be more specific, we examine these materials with 3 different strain treatments. The first one unstrained, compressive, and tensile, with uniaxial strain at B directions, in the hope that this approach model allowing us to give a preliminary design for experimental setups before synthesis. In this work, we use 2 methods as shown in this flowchart. The first one is density functional theory with these parameters to generate the bandgap structure, and then continue with the Boltzmann transport theory to generate the thermoelectrics performance. This is the result. The first one from density functional theory or DFT, we examine the bandgap under different treatment. The first one unstrained, and then the second one is strained. From the calculations, it reveals that this material show 2 types of bandgap. The first one is indirect bandgap, which lie between M and gamma directions and R and gamma directions. And then direct bandgap, which lie at gamma point. This material shows semiconductor behavior with energy gap from 3.4 until 4.5 electron volt and showing 92 until 98% accuracy compared to the experimental data. And this is confirms that our chosen parameters is nearly accurate. Besides that, we also observed that the A-side atom radii could affect the bandgap at gamma directions or at the direct bandgap. On the other hand, for the strain calculations, overall the tensile strain could decreases the bandgap. This is in a good agreement with the previous study on barium stannic oxide. They also state that the positive strain could reduce the bandgap. To be more specific about the impact of strain to the bandgap is shown in this figure, where the strontium stannic oxide have steeper slope, and this is indicating that this materials has the highest responsiveness to the strain other than materials. In contrast, magnesium stannic oxide is less impacted under the same condition. From the Boltzmann transport theory, we generate thermoelectric properties, and the first one for unstrained calculation. I'm gonna start with the Seebeck coefficient. Magnesium and strontium, they shifting the carrier value from negative to positive values around 400K, and then the share continue, however, only show a minimal decrease above these temperatures. In contrast, barium stannic oxide showing a moderate increase and also experience a shifting from negative type to the positive type. Meanwhile, for the calcium stannic oxide, this is quite unique because they experience a sharp dip below 400K and then started to recovering until above 700K, and they also shifting the carrier value from the negative type to the positive type. We suspect that this behavior are coming from temperature-dependent carrier activations in the band gap. For the electrical conductivity, this is very obvious that the purple one is barium stannic oxide displays the most significant rise in the conductivity. Then magnesium and strontium oxide show moderate increases at the same time. However, for calcium stannic oxide remains nearly constant. This is reflecting limited carrier activations in these materials. For the power factor, barium stannic oxide showed the highest peak at 440K and experienced a substantial growth about 700K. Following by the magnesium stannic oxide and strontium stannic oxide also show a significant increase above 700K. Again, calcium stannic oxide remains nearly flat across the temperature, and this is limited the thermoelectric power applications for these materials. For the strain calculations, for thermoelectric properties, summarize the result for all materials. We focus on the extreme strain condition due to the similar trends across materials. Except for the Seebeck coefficients for calcium stannic oxide, we suspect this behavior coming from the complex band structure, which potentially make a sudden shifting charge carrier. And the trend is quite random. However, this trend begins to stabilize at 3% strain until 5% strain due to the narrowing band gap. Anyway, for the magnesium stannic oxide and strontium stannic oxide generally show positive values above 400K, and both of them experience a sharp dip with minus 5% strain at different temperature. This condition is similar with the calcium stannic oxide with unstrained treatment, as I explained in the previous slide. For the barium stannic oxide, doesn't change too much under strain treatment, except for the minus 5% strain at below 400K, which show a significant increase, and this is suggesting that this electronic structure is quite stable to temperature changes above 400K. For the second row is the electrical conductivity, where the barium stannic oxide exhibits the highest conductivity under 5% strain, and the other material show gradual increases at elevated temperature with the same condition. But still, the value are far below the barium stannic oxide. Finally, for the last row, for the power factor, overall, negative strain decreases the power factor, while the positive strain increases it compared to the unstrained structure. And the highest improvement in the power factor is on strontium stannic oxide, which occurs under positive treatment, this one. And we couldn't found any peak for the compressive strain on calcium stannic oxide because the share is continuously rises, and all material experience a significant increase in power factor above 700K, except for the calcium stannic oxide with unstrained treatment and minus 5% strain on strontium stannic oxide, which they only show a small increase above this temperature. In conclusion, uniaxial strain significantly affect the thermoelectric properties of alkaline earth stannate oxide, where the positive strain narrows the band gap and negative strain widens it. Additionally, a larger A-site atomic radius results in a broader direct band gap. With applying 5% tensile strain could enhance the positive Seebeck coefficient at higher temperatures above 650K. Negative strand decreases the power factor while positive strand increase it compared to the unstrained structure. In a nutshell, positive strand offers a promising strategy to optimize thermoelectric devices, especially at higher temperatures above 650 K. That concludes my presentations. I will now hand it back to the session chair. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for the comprehensive presentation. So I'm waiting for the question. Now it's time for the question and answer session. We have around 4 minutes. So please, the audience, to ask the questions. Okay, as usual, while waiting for the question, so I will ask the presenter some questions. So the first question is, you did GFT calculation, but did you compare with the experimental data, or did you do the experimental data? Okay.
Yeah, it's of course we compare that to validate that our chosen parameters is nearly the reality of the materials. Actually, I have shown that in the table at the video presentations for each material. We compare that with the experimental result, and all of them showing 92 until 98% accuracy with the experimental data. So we can say that this quite nearly accurate with the experimental results.
Okay, thank you for the answer. So we have a participant who raised hand, Mr. Wilman Septina. Maybe you can open your mic and mute your audio. So please, and open
thank
your
you. Can you hear me?
Yes.
Yes. So it seems power factor is the most important parameter in thermoelectric. Could you explain what is that? Because maybe in solar cell it's efficiency, but probably in thermoelectric it's power factor, it seems. Could you explain that for me? What is that?
Yeah, thank you very much, Mas Wilman, for the question. Actually, the efficiency in the thermoelectrics, not only power factor, but also we always say that with the figure of merit or ZT, that is included the thermal conductivity, electrical conductivity, and also the Seebeck coefficient, like that. But in this research, we were not calculate the thermal conductivity due to the expensiveness of the calculations. So we take the power factor, which is strongly correlated with the Seebeck coefficient and also the electrical conductivity. So for the in this research, we just see it from the enhancement in the electrical conductivity, but we quite neglected the thermal conductivity. So start it up, or do you have any questions again?
Thank you.
Thank you.
Okay, thank you for the question and answer. So I think the time is over for the second presenter. Let's give applause to the second presenter. Thank you. So let's move to the third presenter. Let's move to the third presenter. So we have Mr. Almas Safwan from the Republic of Indonesia Defense University. The video presentation will be shown. Please, the screen is yours.
Hello, let me introduce myself. My name is Alma Safwan from the Physics Study Program at the Republic of Indonesia Defense University. And today I am presenting our research titled on cooperative study of tin peroxide deposition using spray and spin coating technique for electron transport layer of inorganic perovskite solar cells. This research was conducted alongside my co-authors Adi Kusumajati from the Physics Study Program at the Republic of Indonesia Defense University and Lia Yuliantini who research at the Electronic Research Center of the National Research and Innovation Agency. The outline include introduction, methodology, result, conclusion, and action knowledge. Perovskite solar cells have shown great promise due to their high power conversion efficiency. However, most conventional perovskite solar cells use titanium dioxide as the electron transport layer, which requires annealing temperature above 450 degrees Celsius. This high temperature limits the use of titanium dioxide in commercial scale production and flexible solar device, as it is unsuitable for temperature-sensitive substrate. To address this limitation, tin peroxide has emerged as a superior alternative. Tin peroxide can be deposited at much lower temperatures, making it more suitable for scalable and flexible perovskite solar cell production. In this study, we focus on the deposition of tin peroxide using two techniques, spray coating and spin coating. The spray coating method offers several advantages. It allows for large area, uniform deposition, making it ideal for commercial application. Additionally, it operates at lower temperature compared to titanium dioxide, making it compatible with flexible substrate while reducing energy costs. Importantly, the spray method produces thinner, more compact electron transport layer, which exchange charge transport and reduce recombination losses. Compared to spin coating, spray coating also reduces the time and variability of the coating process, making it more efficient for fabricating electron transport layer. In our research, we explore this technique performing detailed characterization of the tin peroxide layers and evaluating their performance in CAS PBBR3 based perovskite solar cell using SEM, UV-Vis, IV, and IPC analysis. In methodology, we deposit tin peroxide using both spray coating and spin coating technique with varying cycle count for each method. In this slide, you can see a schematic representation of the spray coating deposition process. The tin peroxide precursor solution is spread onto the FTO substrate using a high pressure nozzle. The distance between the nozzle and substrate is maintained at 10 centimeters, while the gas flow rate is set to 9 liters per minute. The substrate is heated at 40 degrees Celsius during deposition, and multiple spray cycles 3, 5, and 7 are applied to create a uniform and compact ATL layer. For spin coating technique, tin peroxide is deposited by rotating the substrate at 3000 RPM for 30 seconds. In this process, variation of 3, 5, and 7 layers are used, and annealing step at 200 degrees Celsius are repeated multiple times. After spin coating, both spray coating and spin coating substrate was heated at 200 degrees Celsius for 60 minutes. The perovskite active layer was fabricated using TS PBBR3, followed by carbon as the counter electrode. In our research, we explored this technique performing detailed characterization of the tin peroxide layers and evaluating their performance in CAS PBBR3 based perovskite solar cell using SEM, UV-Vis, IV, and IPC analysis. In result, first, SEM analysis revealed that the 7 cycles spray coat tin peroxide produce a more compact layer with a thickness of 153.34 nanometer compared to the singly thicker 162.55 nanometer layer from spin coating. This compactness enhances electron transport, reducing recombination loss and improving overall device efficiency. And then UV-Vis analysis showed that tin-4 oxide layers deposited via spray coating have higher light transmittance in the visible range, allowing more light to reach the active layer of the solar cells, which increase the potential for higher photocurrent generation. And then our IV analysis showed that the perovskite solar cells with 7 cycles spray coat tin-4 oxide electron transport layer achieve a higher power conversion efficiency of 2.21% compared to 1.70% for the spin coat counterpart. This improved performance is attributed to the compactness of the spray coat layer, which facilitated better electron transport and reduced recombination loss. The better electron collection reflected in high short-circuit current density and fill factor was consistently observed in spray coat device. Table 1 show detailed comparison of the photovoltaic performance between the different tin-4 oxide deposition method. In addition to the IV result, the IPC analysis further validated these findings. The spray coat device demonstrates superior IPC values across the visible light spectrum, particularly around 50, 120 nanometer, where they reach peak efficiency. These indicate more efficient conversion of incident light into electrical current, further highlighting the advantage of the spray coating method in improving the light absorption and charge collection capability of the solar cells. In conclusion, based on the data provided, the 7 cycle spray method is able to produce thinner 153.34 nanometer and more compact tin-4 oxide layer with SN concentration of 11.06 weight percentage compared to the 7-layer spin method, making it more effective in increasing the electron transport efficiency in perovskite solar cells. The study also showed that the use of CAS-PBBr3 as a stable inorganic material in perovskite solar cells can improve stability and efficiency with 7 cycles of spray coating, proving to be a superior technique for depositing tin-4 oxide as an ATL layer compared to spin coating, achieving the highest power conversion efficiency of 2.21%. The optical properties of tin-4 oxide, especially in UV absorption, are stronger with longer spray times. Same results show a wider distribution and accumulation of SN in the spray coating method, which also reduces the time and variability of the coating, making it more efficient for the fabrication of electron transport layer. Thank you for your attention. We would like to extend our deepest gratitude to management Tentang BRIN for their support of the MBKM program. Lia Liantini would like to thank Rumah Program ORNM BRIN 2024 grant number 23.10 HK 2024. The author acknowledge the National Research and Innovative Agency of Republik of Indonesia for the facilities, scientific and technical support offered by the Advanced Characterization Laboratories in Bandung and BRIN a Layanan Science. Once again, thank you for your time, and we look forward to contributing to the exciting future of solar energy research. Thank you.
Okay, thank you for the nice presentation. So now it's time for the Q&A session. So please, to the participant audience, if you have any question, you can write down on the chat box or raise your hands. Okay, maybe I have a question or some questions maybe. So did you measure the thickness of the film? So you did some experimental with spray coating and spray coating and spin coating. So, but did you measure the thickness of the film? Yeah, Mr. Almas.
Hello?
Okay.
Hello.
Yeah.
Okay.
Yeah. Okay.
Thank you for your question. Yes, in my study, the thickness of tin peroxide layer was measured for the spray pot layer with 7 cycles. The thickness was found to be approximately 153.34 nanometer. In comparison, the spin coat tin peroxide layer, also with 7 layers, was slightly thicker at 162.55 nanometer. These measurements were likely obtained through same cross-section analysis as mentioned in our presentation.
Okay, thank you for the answer. So I have another question. So if the participant you have the question, if you have question, you can raise your hand. So while waiting, I have another question. So you did 7 cycles for the spray coating, but did you do more than 7 cycles? Did you try more than 7 cycles for the experimental?
Okay, thank you for question. Additionally, the decision to use 7 spray cycle was based on the precursor's lower concentration than in other studies, requiring more cycles to achieve the desired thickness. Increasing the number of cycles beyond 9 was not pursued due to concern about the efficiency of material use and processing time, which would be critical if solar cell were to be mass-produced. Future research will focus on reducing the number of deposition cycles for tin peroxide without compromising the performance of the solar cells. Thus ensuring both the production efficiency and device effectiveness.
Okay, thank you for the answer. So I'm still waiting for the question. So if we have no question, so I think this is the time is over for the third presenter. Thank you, Mr. Almas. So give applause to the presenter. Okay, it's time for the fourth presenter. We have Ms. Nelviani from National Research and Innovation Agency. The video presentation will be shown. The screen and time are yours.
Good day, everyone. On behalf of my team, I'm Nelviani from Photonics Research Center. We'll present our study about optical fiber simulation, Corning SMF28 as a fiber grading or FBG with optic grading application. Fiber optics are known for their role in communication systems, but their applications extend far beyond just data transmission. And these versatile fibers can also serve as highly effective sensor systems, providing accurate, responsive monitoring across various fields. However, adapting fiber optics into reliable sensors requires considerable optimization efforts, and it's a process with promising potential, yet one that carries significant financial and technical risks. And to address these challenges, simulations are invaluable. And by simulating fiber optics, we can closely analyze and predict sensor behavior under different parameters and conditions, allowing us to refine designs before implementation. And this approach minimizes cost and risk while maximizing performance outcomes. So, the objective of our research is to investigate the performance of Corning SMF28 optical fiber, specifically when simulated as a fiber break grating, and by applying chirp and apodization functions, we examine how the fiber responds to various levels of strain and temperature. And through this study, we aim to understand how these functions influence the fiber sensitivity and accuracy. At its core, fiber optics is a technology that uses thin strands of glass or plastic to transmit data as light signals over long distances. And each fiber optic cable is structured in three main parts, which is the core, the cladding, and the protective coating. Now let's look at how fiber optics actually work. The light signals travel down a fiber optic cable through a process known as a total internal refraction. So, when light signals enter the core of a fiber optic cable, they must hit the boundary between the core and the cladding at a specific angle known as the critical angle. And this critical angle is determined by the refractive indices of the core and the cladding materials. If the light strikes the boundary at an angle greater than the critical angle, it reflects entirely within the core instead of passing into the cladding. And this reflection occurs because the cladding has a lower refractive index than the core, and allowing the light signal to bounce back and forth along the core. Conversely, if the angle incidence is less than the critical angle, some of the light will refract into the claddings instead of reflecting back into the core. And this lot of light reduces the intensity of the signal and can lead to weaker transmission. And this is the application of the fiber optic in the network and telecommunication system. It offers high data transmission speeds with large bandwidth capacity. And in sensor system, fiber optics are utilized for physical measurements such as strain, displacement, temperature, pressure, and more on structures of various shapes and sizes. And these sensors are compact in size, offering fast and sensitive responses. And additionally, fiber optic sensors are immune to electromagnetic fields, ensuring they remain unaffected by environmental disturbances. And one notable example of fiber optic sensor is the FBG. In this study, we will simulate a type of single mode fiber optic, and specifically the commercially available Corning SMF28 ultra optical fiber, which is widely used in telecommunications. Single mode fiber optics consists of a small core diameter that allows only one mode of light to propagate. And to analyze, also to simulate the performance of this fiber optic, we will utilize the opti-grating application. But how actually do we transform a fiber optic into an FBG? And to answer that, I will explain first what the FBG is. So a fiber break grating is a specialized type of optical sensor created by inscribing a periodic variation or grating within the core of an optical fiber. The key feature in FBG is the grating period, which is the regular spacing of refractive index variations along the fiber core. And this grating period is crucial because it determines the specific wavelength of light that FBG will reflect. And we know it as the Bragg wavelength. And by controlling this grating period, we can design the FBG to reflect only certain wavelengths, while all other pass through without interference. Now imagine we have a broadband light source like a white light passing through the fiber that contains the FBG. So the FBG will act as a selective mirror. It reflects only the specific wavelength that match the grating period, while all other wavelengths continue along the fiber. And this selectivity is why the FBG functions also as an optical filter, and it reflects a precise wavelength. If we zoom in on the grating, we see that this optical filtering capability allows the FBG to detect changes in the environment. And for instance, when strain or temperature affects the fiber, it slightly changes the grating period, shifting the reflecting wavelength. And by monitoring this shift, we can obtain accurate measurements of parameters like strength and temperature. In simulation, we will apply several key parameters to observe how the parameters influence the behavior of the fiber grating. First, we will examine the variation of the grating period, applying 4 different types of variation, which is linear, quadratic, square root, and cubic root. And each of these variation changes how the grating period gradually shift along the length of the fiber, which will affect the wavelength reflection profile. And then we will introduce the apodization in the form of Gaussian function, and the apodization is applied to smooth the grating's reflective profile and manage what's known as the side lobe secondary peaks that appear in the reflection spectrum. And the Gaussian apodization creates a gentle curve that minimizes the side lobes and reducing the unwanted reflections that can interfere with the primary signal. And finally, we will apply the sensor inputs, which is the strength and temperature, to observe how these parameters shift the reflected wavelength of the FBG. And this is the flowchart of our measurement. For the results, for the first data, we would like to test the difference in spectrum results for the FBG without chirp, or we call it as the uniform FBG, and FBG with chirp. And in this study, we use a reference wavelength of 1550 nanometers, and by applying chirp variation to the FBG gratings, we expand the reflection spectrum bandwidth as seen in the FWHM values. 0.624 nanometer is produced by the FBG without chirp, and 2.992 nanometers with FBG with chirp. And this broader bandwidth allows the FBG to accommodate more light signals and significantly increasing sensitivity and making it more effective for a wide range of tests. Then we utilize FBG sensors to measure microstrand variations, specifically in the range of 0 until 1000 microstrand range. And the simulation across the linear, quadratic, square root, and cubic root chirp periods, and it reveals that each grating period exhibited a linear wavelength shift with strength. Though the Bragg wavelength shift varied due to the difference in how each chip structure responded to the strain. And our result indicate a sensitivity of 1.208 pm per microstrand for linear and cubic root chirps, and 1.216 pm per microstrand for quadratic and square root chirps. The 1550 nanometer wavelength shift in response to strength, with the quadratic chirp period maintaining wavelength stability best, while the cubic root chirp period shows lower performance. In addition to strength testing, the FBG sensors were evaluated across a temperature range of -60 degrees Celsius to 85 degrees Celsius. Using the same configuration of the chirps, the study demonstrated a linear peak wavelength shift with temperature changes. And we got the sensitivity for 13.628 pm per degree Celsius for the quadratic chirp and 13.738 pm per degree Celsius for the other chirps. Further highlights of a consistent reflective spectrum is in the 20 degrees Celsius to 40 degrees Celsius range, indicating optimal sensor performance within this interval, especially for strand application. And following the initial strand and temperature test, we conducted simulations to evaluate FBG sensor performance under the simultaneous influence of both parameters. And as shown in the left figure, the 1550 nanometer reference wavelength shifts primarily due to the temperature changes, underscoring the need for temperature stabilization in strand-focused application. Additionally, in the right figure, it reveals consistent Bragg wavelength shift across all chips period, indicating similar sensitivity responses to combine strain and temperature effects. So this demonstrates how FBG sensors function in environments influenced by strain and temperature, with the Corning SMF28 FBG showing promising sensor potential due to its wider reflection spectrum and achieved through chip period configuration. To conclude, we can say that the Corning SMF28 is a potential FBG sensor with the parameter that we already input in the simulations. And for the sensitivity for the Corning SMF28 as the FPG sensor, we can say that the quadratic and square root chirps demonstrate high sensitivity to strength, and the quadratic chirp has lower sensitivity to temperature, while the consistent shift for wavelengths and similar sensitivity under both temperature and strength changes. And for the further research, we can try to evaluate FPG sensor performance at different strength levels and temperature to assess reliability across diverse applications. That is the end of my presentation. Thank you for the attention. Good day.
So, Ms. Nuni, your voice is still mute.
Okay, sorry. Okay, thank you for the nice and interesting presentation. As usual, I'm waiting for the presenter to ask the questions. We have 4 minutes to Q&A session. So I will ask the question. So for this is the simulation, right? Not experimental. But yeah, maybe as usual, I asked that did you do some experiment to confirm the data from the simulation?
Okay, thank you, Ms. Nani, for the question. Is it my voice clear?
Yes, I can hear your voice.
Yeah, actually, why we did the simulation for the fiber break rating, actually, I already mentioned it in the background of this research, which is because to create an FBG from the fiber optic itself, it has a lot of risks, and the method itself, it's not available in many places. So before we convert our fiber optic into the FBG sensors, then we need to simulate it first to see is it feasible for our fiber optic is it optimal for our fiber optic to be converted to the FBG? So we didn't do the experiment, not yet.
Okay. Okay, thank you for the answer. Now we have a question from the participant, Mr. Muhammad Yusuf Firdaus. You can open your mic. Okay.
Well, thank you for the moderators for the chance for me to ask the question. First one, I think this is the interesting topics regarding the FBG for sensing application, particularly using the chirp FBG.
Yeah.
The question is it possible to, I think it's the same question like previous one. Is it possible to produce or to apply the simulation to the realization of the FBG itself? Because I think the parameters that you had arranged in the optic rating, I think it's still not represent the real values to be manufactured in the real life for the FBG. I think, that's the question. Is it possible to be manufactured in the real life?
Okay, thank you, Mr. Yusha, for the questions. For the grading, for the chirp itself, it again depends on our needs. Actually, the simulation is to provide, is it the fiber optic or if the FBG will fit with our needs, like that. So the simulation is to simulate what chirp that can fit with our needs, and then maybe we can search for the manufacturer that can produce such chirp, because the commercial FBG now is it has uniform chirp, so the chirp is with the uniform period, then my mentor said that we can make it in Malaysia or in other manufacturer to make it. But then again, why before we did that, because we really need a very fixed plan for doing the convert of the fiber itself. So we have to see in what shape we want to produce and what the sensitivity that we need, like that. So maybe if we discuss it with the manufacturer, they can make it like that. For my experience, I haven't looking for that, for the manufacturer that can produce it, because I assume that the manufacturer could make it.
Right. Thank you for the answer.
Yes.
Okay. Now we have another question from Mr. Robert. You can open your mic.
Yes, thank you. Such a quite a presentation, very interesting also. Yes, because you said that this is the preliminary study for the simulation, right, for FPG. My question is it any specific fiber optic for the FPG sensor, or any kind of fiber optic you can use for that? And then could you give some example for the another application, because you already shown by the simulation to detect the strain and the temperature, right? So is it possible using for the biosensing or some kind like that? Okay, thank you.
Okay, thank you, Mr. Robert, for the question. For the first question is for the fiber optic itself, the one that I usually know, the type of fiber optic that could be converted to the FBG is the single mode fiber one, because it produces only one wavelength. And so because it produces only one wavelength, so maybe it will filter only one broad wavelength. So that's will, like, the sensitivity will be more sensitive. So yeah, the type of fiber optic is the single mode that usually I know made for the FBG. And then for the application itself, because the FBG is actually a sensor that detects for the physical detection. So actually the strength, the temperature, the vibration, it can be applied. And I think the field the field of application for the FBG is very broad. It's for the mining, especially also for the health. It can maybe someday it can replace, or it can be an additional instrument for heart detection or heart something with the health, like that, which can produce like vibration or something that we can detect with the FBG. For the biosensing, I'm not really understand with the biosensing. Do you mean with we can sense the protein with the
yeah, some kind like that, yes.
Yeah, as long as it's a physical detection, so the fiber break, I think, can detect it.
Or maybe you said that the type of the optical just due to the single mode, right? Why you choose the SMF20H?
The SMF, the Corning SMF is a single mode fiber optic.
Or maybe just we need a special fiber optic to make some manufacturing the grating itself. So why we need some kind of specific fiber optics such as SMF28? As long I know that this kind of the fiber optic is UV photosensitive, right?
The fiber optic itself for the Corning.
Yeah.
I don't really think so, but maybe yes. I don't have information about that actually, but yeah.
Okay. Thank you.
Yeah.
Okay, I think the time is over for the fourth presenter. So please give applause to the fourth presenter. thank you for the nice presentation and answer the questions. So it's time for the last presenter. For the last presenter, we have Mr. Robert Victoria from National Research and Innovation Agency. The video presentation will be shown. The screen and time are yours.
Hello everyone. Today I want to present our paper with the topic Preliminary Study on Development of D-shaped Polymer Optical Fiber-based SPR Sensor for Biochemical Application. My name is Robert Victoria Manurung. So this is our presentation outline. And then optical fiber sensor principle, actually the sensor operation is based on the interaction between the signal and the medium outside the core. The interaction occurs due to the difference between the value of the refractive index of two medium, as we can see here on the image. For D-shaped polymer optical fiber sensor, we construct the sensor based on the removal of the POF cladding. The process allows the optical signal to interact with the sensory medium. In this case, we deposit with the gold thin layer film. We can see in the graph over here.
Yang belum makan.
So it can be detecting the changing of the refractive index. So when the light incident of the metal coated surface of D-shaped fiber, it can excite the surface plasmon, which are collective oscillation of electron at the metal dielectric interface. The excitation of surface plasmon result in the sharp decrease in the intensity of transmitted light at a specific wavelength, and we can call that as a resonant wavelength. This is our POF D-shape profile. So we polarize the cladding, remove the cladding until the core is exposed. So in this case, we employ two kinds of fabrication technique, F1 and F2. After we construct the D-shaped POF SPR sensor, then we deposit with the gold layer on the surface with the various metal deposition time, start for 10 seconds up to 20 seconds. So we can get at least 6 model of D-shaped POF sensor with a different fabrication and different metal deposition time. And this is our measurement setup for our sensor. So the sensor connected with the light source, you are using a halogen, and the other side we connected with the detector. Thickness of cladding is around 10 micron. So this is the picture how we measure our sensor. So we try to evaluate our sensor in the two kind of the solution. For the control, we are using deionized water, and for the performance of our sensor, we employ the glycerin sample with the different concentration and the different refractive index of each of them. So this is the result of our fabrication for the D-shaped POF SPR sensor. On the left side, this is the microscope image, and we can see here for the A part is actually for our fiber optic without any removal cladding as our reference. For the B and C, actually we can see here that we employ the two kind of fabrication, F1 for B and F2 for C. And the right side, this is the optical microscope of the surface morphology after we deposit the thin gold film for F1D1 up to F2D2. And of course, we can see here the yellow part on the surface. It indicates that the gold has been successfully deposited. To confirm that, we are using SEM. And we can see here, for the shortest metal deposition time, the structure of the morphology of the layer of the gold is look like an island with the sharp shape as shown in these two kind of the SEM image. However, for the sample with the longer time deposition, so the layer is look like a thin film gold. So this is confirmed that there's a plasmonic event will be higher for the shortest time compared than the longer time, due to the hotspot can be obtained from the structural shape like this. For our initial evaluation, we are using a DI water to see our sensor performance, and among the 6 model, we get at least four model with the intensity in the specific wavelength, and the range is around 641 and then up to 644 nanometer. We evaluate also the 4 type of our D-shape BOF sensor using a glycerin, and then we get the delta transmittant versus to the glycerin concentration. So this is we can get here. So for the first time, the performance of each model. And for the F1D1 and F1D2, we select for the further evaluation, and we choose as the best the model compared than the others. Why? Because we see here that the linearity for the R-square is much better compared than the others. Also for the sensitivity and FWHM, including the transmittant loss. For the 2 model, F1D1 and F1D2, again, we try to evaluate for 4-time measurement the response of the sensor due to the glycerin concentration. So we can get here from the table that F1D1 has the better FWHM compared than F1D1. So this is indicate the better accuracy in the detection performance. However, F1D1 is better for the other aspects, such as the transmittant loss, the linearity R-square, and also in sensitivity and limit of detection, stability, and also penetration of depth. From that, we can use that F1D1 is the better model for our D-shaped polymer optical fiber sensor. As a conclusion, that we are succeed to develop some polymer optical fiber based on surface plasmon resonance that offer a promising alternative to the conventional SPR system. And F1D1 demonstrate better performance, such as sensitivity, stability, and detection limit. So this model is suitable for our goal to apply as a point of care. So the SPR sensor is our SPR sensor is compact and portable nature and ability to detect changings. For this case, we are trying to measure in the glycerin concentration, and for the future, we can also employ our sensor for another purpose, such as for detection of virus or also the bacteria using HPR phenomenon. So we all want also to thank you for the research innovation untuk Indonesia Maju RIM Fund Batch 3 for support of this research. So thank you very much for your kind attention.
Okay, thank you for the interesting presentation about the SPR fiber sensor. Okay, now it's time for question and answer session, Q&A session. So I have question actually about the application to the fiber sensor you applied in glycerin. But how about the bigger molecule, other carbohydrate in bigger molecule or protein? Is it possible?
Yeah, thank you for the question. the main reason why we are using a glycerin, because this is a most common substrate to detect to evaluate the SPR performance, because some reason for first, glycerin has the refractive index, so it's very easy and can get creating a different refractive index. That's the basic principle of our sensor mechanism. And then the other is this one is optical transparency. Yeah, it's a very glycerin is visible and near infrared region. So this is ensuring that it does not interfere with the light propagation of SPR phenomenon, and also chemical stability and non-toxic and safe. But we don't know yet if we try to another molecule with a big molecule as you suggest. But probably it is also as long as get some refractive index and also the transparency, not to hinder the propagation of light. I think is it possible also to that kind of the molecule to test and to see how the SPR react and detect for that kind of molecule. I think that's all the main reason why we are using a glycerin. But is it possible for another one for the future?
Yeah, it's possible as long as the transparency and it shows a refractive index, right?
Right, yes.
Okay, thank you for the answers. And we have a question from the participant. We have Mr. Komarudin. You can open your mic. Okay.
Okay, thank you. Can you hear my voice?
Yes, I can hear your voice.
Okay. Thank you for the explanation. I'm sorry if I missed the explanation, Mr. Robert. Can you explain how to fabricate the shape? How to fabricate the shape, like the shape, something like that?
Yes, because so sorry, because the presentation time is very limited, up to 10 minutes. So I just show in the previous slide, we apply two kind of the fabrication. But most of them we are doing manually. We are using a carving knife, doing manually, and then we smoothing with some kind of the chemical. So yeah, we admitted that our technique is very simple, yeah, using a manually. But in the future, we try to make some kind of polish machine, yeah, to specific to do that. So that's our fabrication technique.
Okay. Mr. Komarudin, is it okay?
Yeah, is it answer your question?
Is it answer your question, Mr.
Okay,
Komarudin?
maybe I just want to know because the dimension is very small. So something like that. We want to know how do you fabricate?
Well, we're doing a trial and error, and a lot of fiber optic is failed actually. But we doing this is by time, and then finally we
I
succeed
think
and
the
get
internet
some
connection is the
temper.
problem.
Oh, okay. Sorry.
Okay.
Yeah. Do you hear what I explained before?
Okay, you can continue.
Yeah, actually, it's not a very easy thing actually to cut off little by little the cladding layer by manually. But we try many times and then failure many times. But thanks, we get some prototype and some sample of our fiber optic, and then we make some further evaluation as we present in our paper.
I see. So do you use a microscope, something like that?
Yes.
Yes.
We are for the first data, you are saying optical microscope. During the process, we also confirm it with the optical microscope.
Okay. Thank you, Mr. Robert. Thank you.
Okay, thank you for the answer and also for the question. So I think the time is over for the last presenter. So before we close the session, but let me conclude the session with some summary. I hope I still have time to conclude. So Oh, maybe I forget. So please give applause to Mr. Robert for the presentation. Thank you for the presentation. Okay, let me make some summary. So from the first presenter, that's about the exploration of indium sulfide as an electron transport layer in perovskite, that it showed the efficiency of the material is higher than the device without electron transport layer. And from the second presenter, about impact of inaxial strain treatment on thermoelectric performance of alkaline earth standard oxide, the results reveal that the tensile strain treatment predominantly improved the electrical conductivity, contributing 6.5 times higher electrical conductivity value under an axial strain. And from the third presenter, a comparative study of SNO2 deposition using spray and spin coating technique. So it reveals that spray coating 7 cycles achieves higher efficiency. From the fourth presenter about optical fiber simulation, Corning SMF28 as a fiber break grating with opti-grading application. The study explores how the Corning SMF28 optical fiber can be transformed to a highly efficient fiber break grading sensor using simulation techniques. And the results show that quadratic and square root chirps provided the highest sensitivity, making the sensor more responsive to change in the environment. And from the last presentation, about preliminary study on development of D-shaped polymer optical fiber-based SPR sensor for biochemical applications, the results underscore the capability of the developed POF-based SPR sensor to produce surface placement resonance and provide a reliable SPR output in identifying fluctuation in glycerin concentration within the D-shaped sensing component. So I think the end of the session. So thank you for all the participants and presenters. Give applause for all the participants and the presenters. One more. And I will close the session. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Recording stopped.
Thank you, everyone. So now we are going to have the lunch break, and please join us again at 1 p.m. GMT+7. Then we will have the second keynote talk. Thank you.
Recording in progress.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Land Railway System, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity.
Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked at Center 2 in Kemendristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SIMPAC under multibody.
Land railway system. or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership. We deliver safety and capacity.
Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Tentang BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Land railway system. or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation.
Welcome back to Ikramet 2024. I hope you feel recharged after the lunch break and ready for the next agenda. Before we begin the second keynote session, let me take this opportunity to thank again our patrons, PT Radar Telecommunications Indonesia, PT Nusantara Sekom Infotech, PT Mars Sistem Integrasi, PT Young Dinamis Indonesia, PT Serviam Abadi Murni, PT WAP Andalan Indonesia, Bank Rakyat Indonesia, and PT Land Railway System. Your support and commitment have been crucial in bringing this conference to life. We deeply appreciate your partnership and look forward to future collaborations. Coming up, we will hear the second keynote talk by Dr. Asif Aminullah Fatnan. This session will be moderated by Dr. Fadil Habibi Danufani. Let me introduce you, Dr. Fadil Habibi. He received his BSc degree in Electrical Engineering from Bandung Institute of Technology, or ITB Indonesia, in 2013. His Master of Science degree in Computational Science from Kanazawa University, Japan, and PhD degree in Telecommunications from the Laboratory of Signal and System of Central Supelec Paris-Saclay University in 2021. From 2022 to 2024, he was a postdoctoral researcher at King Abdullah University of Science and Technology. Since 2014, he joined the Indonesian Institute of Sciences, or back known as LIPI, and now has transformed into Indonesia's National Research and Innovation Agency, or BRIN, in Research Center for Telecommunications. His research interests include wireless communications, stochastic geometry, and reconfigurable intelligent interfaces. Please welcome Dr. Fadil Habibi Danufane and Dr. Ashif Aminullah Fatnan.
Thank you very much for the organizer for inviting me and introducing myself. First of all, can you hear my voice? Is it okay?
Yes, we can hear you well.
Hello? Okay. Okay. So so today we have a second, I believe, keynote speaker, which is Dr. Ashif Aminullah Fatnan. His talk will be titled "The Recent Advances in Microwave and Millimeter Wave Metasurfaces." I believe this is going to be an interesting talk because he's one of the experts that we have here in BRIN in Indonesia, I believe. So before we go to the talk, let me introduce some background of Dr. Ashif. So next slide, please, if you have it. So, okay, so Dr. Ashif Aminullah Fatnan received his bachelor degree in electrical engineering in 2011 from Gajah Mada University, Indonesia. He also got his master's degree in computer science and information engineering from Asia University in Taiwan in 2013. And finally, he got his doctoral degree in electrical engineering in 2021 from the University of New South Wales, Indonesia. In 2012, he was an integration engineer in Taiwan Semiconductor Manufacturing Company, TSMC, in RF and Analog Specialty Division. And from 2021 to 2024, he was an International Research Fellow in Electromagnetics Laboratory, Graduate School of Engineering in Nagoya Institute of Technology, Japan. He was with BRIN since 2015 and until now. And since 2024, he also has been a lecturer at the Telkom University. Among his many research interests are metamaterials, metasurfaces, electromagnetics, wireless communications, and finally the antennas and the propagation. So without further ado, let's listen to the talk of Dr. Ashif Aminullah Fatnan. Dr. Ashif, the floor is yours.
Okay, thank you very much for having me, and thank you for a generous introduction. Let me share my screen. Okay, can you see my screen?
Yes, we can.
Okay.
I think it's better if you maximize the screen.
Okay. Okay, can you see that now?
Yes.
Okay. Okay, so today I'm going to present my talk. The title is Recent Advances in Microwave and Millimeter Wave Metasurfaces. So yeah, as mentioned by Fadil, my name is Ashif. I'm from Research Center for Telecommunications, National Research and Innovation Agency, Indonesia. I'm also affiliated with the Department of Electrical Engineering, Telkom University, Indonesia. So this is the structure of my talk today. So I'm going to present first some fundamentals of metasurfaces, including some introduction into metasurfaces, surface impedance modeling, and the theoretical limits on broadband achromatic metasurfaces. And then I will talk about the applications of metasurfaces, including realization of broadband achromatic microwave metasurfaces, also frequency independent beam steering using achromatic meta lens, and UAV mounted metasurface for IoT applications, and also cross frequency information relay using metasurface. Okay, so let me choose some pointers in here. Okay, so a little bit background into metasurface. So metasurface comes from metamaterials. It has been around since the year 2000. and the word meta itself means beyond. So metamaterials basically means materials that is beyond conventional materials. So typically metamaterials are created from small scatters, which are smaller than the operational wavelength, and they utilize continuous change of permittivity and permeability to implement a certain control or full control of electromagnetic waves. So for example, here we have a cloaking device in microwave operation, where it utilizes stretching optical path by varying the permeability of the materials. So therefore, it creates a void inside this material where everything which is inside this void will be invisible to the scattering of electromagnetic wave. And this is actually are created from split ring resonators. And if you see if you take a closer look into this structure, it's actually just split rings with variation of some size, and therefore we can have varying permeability effects implemented in the metamaterials. So and following this metamaterial research, we have metasurface. So basically, metasurface are two-dimensional version of metamaterials, and the methodology we use for designing metamaterials can also be implemented in metasurface. So this metasurface offering more compact and practical configuration for applications, and more importantly, it can replace conventional optics. So for example, here we have a flat lens created from metasurface where incident wave will be focused into a certain focal point. And this research topic is actually also very closely related to some topics in the microwave engineering. For example, long before 2000 or long before metamaterials are booming, we know that there are phase array, transmit array, reflect arrays, and frequency selective surfaces, which are in the field of microwave engineering. So these are the same, they have similar design methodology to the metasurface. Okay, so this is an example of how to design a metasurface based on wavefront manipulation. So metasurfaces in wavefront manipulation typically utilize resonance delay, or instead of propagation delay in the conventional optics. So if we see here a conventional prism made of a dielectric structure, we know that the dielectric structure will introduce a phase shift into the incident wave, and if we change the thickness of the dielectrics, we will have a variation of the phase shift, and therefore we can implement a certain anomalous certain refraction. And using the metasurface, we can also implement phase shift within the surface. But instead of using propagation delay, we use resonance delay. So we know that resonance has an amplitude and phase response, and if we engineer the resonator in such a way, we can implement the phase profile into this metasurface. And for anomalous refraction, we know that the phase response should follow this equation. So and it should cover 2 pi in one period of supercell. So this is an example of a metasurface made in 2011. So this is just made from a metallic I and V shapes. I believe this one is in the infrared regime, and you can see here that we can just create this one supercell and periodically repeat the structure throughout the surface. Okay, and so Other than anomalous refraction, we can also implement various other waveform manipulations, such as focusing for text generation. For focusing here, we should implement a phase profile with a hyperbolic function. And for text generation, we need to have a certain phase profile that is varying in 2 pi in the XY plane, just like this. And therefore, we will have a vortex generation. So basically, the design of metasurface can be summarized in this diagram, where we should have a phase delay profiles. And then from the phase delay profiles, we can implement structures to realize the phase. And this modeling, this simple methodology has been very useful for various applications, including for radar and imaging, wireless communication, sensors, and also wireless power transfer. Okay, and beyond waveform manipulation, we can also use metasurface for other applications. So metasurface has been also studied in various other contexts than waveform manipulation. For example, here we have metasurface for analog computations, where it implements a derivative of operations. So such a way that incident wave with a certain amplitude profile will be derived, will be implemented into the metasurface. Also, we know that the metasurface can also be used for imaging best sensing in this, such as this metasurface in the mid-infrared. We know that also metasurface can be used for power or waveform selectivity by utilizing some nonlinear components. And finally, we can also use metasurface for cross-frequency modulation, which if we have certain control, external control, we can, and we have meta atom which are time varying, reconfigurable, we can implement this cross-frequency modulation. Okay, so move on to the next topic, which is surface impedance modeling of metasurface. So surface impedance modeling is very important because it can simplify the design methodology of metasurface. And basically, the impedance, in the most basic terms, we know that impedance is just the ratio between voltage and current. And surface impedance here we can obtain from a metasurface if we have a small metasurface with thin configurations. So consider this structure made of metal and dielectric. And if we have an incident wave which are comparable to the operational wave to the size of the metasurface or to the size of these scatterers, we should consider full wave interaction between this incident wave and the structures. However, if we have structures which are smaller than the operational wavelength, or even much smaller than the operational wavelength, we can simplify the interactions and derive a surface impedance, which are ratio between the incident potential field and the surface currents that is implemented in the surface. So basically, we can then model this spatially engineered metasurface like this into spatially engineered surface impedance. And this is very important and has been utilized in various metasurfaces. For example, this metasurface in optical regime. So here, the size of the meta atom is in nanometers, and it consists of 3 metallic structures, cascaded metallic structures. So we can model these structures as 3 surface admittance or surface impedance. And therefore, we can the full structure will look like this, and we know that each of the metallic layer can be modeled as the surface admittance varying in x direction, and we can get the refraction, anomalous refraction operation from this meta surface. And if we go deeper into the analytics, we will see that we can actually make a pure analytical model of the meta atom by combining the surface impedance and transmission line in an ABCD matrix multiplication. So this is simple. This is the model of the meta surface. So this is the meta surface, consists of 3 metallic layers separated by dielectrics, and this is the model which consists of surface impedance and transmission lines. So ABCD matrix here is a mathematical form to perform ray tracing calculation in 2-port networks. So we can use this ABCD matrix and model this structure. So here, the meta atom here is modeled as MMA here as the ABCD matrix of meta atom. M1, M2, and M3 here is the ABCD matrix for the metallic layers, and MTL here is the ABCD matrix for the dielectrics layers. And we can have we can consider all the properties of the dielectrics, for example, the thickness, the substrate impedance, also in the ideal transmission profile, we can also implement in this part where we can get the phase and amplitude profile that we want. Therefore, we can derive the impedance. So the idea here is that we can utilize the ABCD matrix in this full and obtain the closed form solution for the impedance. So this is very interesting because then we can reverse engineer the meta surface to enable any wavefront control. So we have the phase profile requirements and then plug into this equation and we get the impedance profile that we want. So why impedance? So impedance is has physical meaning, has more physical meaning and easier to interpret physically and can be used for the design. And this is the example of the work utilizing this surface impedance modeling to design a refracting meta surface. So we now know that meta surface can be modeled as surface impedance. So this is slightly more advanced modeling where we have phase delay profiles, and then from the phase delay we have surface impedance profiles, and then what we need to do is to create the structures to realize the impedance, and then we have meta surface. So, but what we were interested in particular at that time was how to utilize this surface impedance profile to realize meta surface that is broadband. So we are interested in designing broadband and achromatic meta surface, and we want to utilize surface impedance profile. And then some questions then appears when we did this research, which some of them are: can we predict the bandwidth limit of meta surface using this surface impedance modeling? And of course, then we can have the second question, which is how to realize broadband meta surface based on the surface impedance model. So that brings me into this next topic, which is theoretical limits on broadband achromatic meta surface. So why broadband achromatic meta surface? So we are interested in this achromatic meta surface because we know that various applications of meta surface requires certain operational bandwidth. So for example, we want to realize short range terahertz communications or microwave communications or radars. And if we want to replace these bulky structures with meta surfaces, we need to consider operational bandwidth. And not only bandwidth, we need also to consider for wavefront manipulation, we need also to consider the chromatic aberrations. So chromatic aberration is just in conventional lens, we can see that chromatic aberration is the frequency dependent of the focal point. So this the focal point changed by frequency. So this is undesired properties of optical elements, and this is also undesirable in these applications. Therefore, in conventional optics, they typically what we typically use is double lenses that create consistent focal points across a certain bandwidth. And in metasurface, we can also design such a achromatic broadband operation by controlling higher order terms, such as relative group delay and group delay dispersion of the phase. And this has been done in various other works. So then we come up with these research questions. So is there any limit? So the question that we want to answer is that, is there any limit to broadband achromatic metasurface? And if there is a limit, what is the analytical expressions for that? And then we continue the questions by trying to realize the broadband metasurface. So in order to answer the first research questions, we revisit this Foster-Reactance theorem. So the Foster-Reactance theorem basically says that the reactance of passive lossless two-terminal one-port network always strictly monotonically increase with frequency. This is already written 100 years ago by Foster. So we know that for inductance, the reactance is positive and it's increased with frequency. For capacitance, the reactance is negative, but it's increasing with frequency. The combinations LC series and LC parallels are also increasing with frequency. So basically, this Foster-Reactance theorems is very useful to see that the structure or some other circuits are passive, lossless, and lossless. So then we, in order to maintain this passive causal realizability, we check our analytical calculations for each metasurface, or for each surface impedance of the metasurface. So for example, here we have three surface impedance profile of this metasurface, of this meta-atom, and then we can evaluate whether the reactance of this impedance are Foster compliant or not. And then we find out that there are some regions in this surface impedance profile or in this reactance profile that are non-Foster. And therefore, we can derive the, based on this Foster compliant region, we can derive the bandwidth limit. So this is the result for this analytical calculations. So, and we have the expression for the limit, the bandwidth limit, and we find out that there is a trade-off relation between the operating bandwidth and the metasurface size. So the larger the metasurface, the more difficult it is to implement broadband achromatic operations. So, and particularly for refracting metasurface, the angle of refraction also limiting the bandwidth. So the higher the refraction angle, the smaller the bandwidth will be. And also for the focusing metasurface, we will have the focal point as the limiting factor. And more importantly, for the dielectric metal configuration, the thickness of the dielectric also contributes to the bandwidth limit. Okay, so based on these findings, we want to realize the broadband achromatic microwave metasurface. And if we see again the impedance profile of this metasurface, we can check if the reactants that are Foster compliant can be implemented using LC series and LC parallel. So why we use LC series and LC parallel? Because we can then derive analytical solutions that to obtain the LNC of this structure. So basically, from the surface impedance that are Foster compliant region, we can approximate what L and C is needed to realize this reactance. And therefore, we follow up the design. So we find out that the LNC for the meta-atom can be derived, and this is particularly we are interested to design metal lens with a certain focal point, and the cell number is with a certain radius, and also the cell number for each radius is 10, and therefore we can derive the L and C profile for each meta-atom, so based on analytical calculations. And so we create the structure. So this structure is made of 3 metallic structures, and it is made of PCB layers. And we first experimentally confirm this by using 2D rectangular wave. It's a double plate waveguide, and so we have this monopole antenna as a source, and this we have a metasurface here, and then we scanned area in front of the metasurface, and then what we get is something like this, where we have the scattering profile in front of the metasurface. We compare achromatic metasurface with a narrowband metasurface. We see that the achromatic metasurface have consistent focal point over a certain bandwidth. So this is from 8.5 gigahertz to 9.5 gigahertz. And it has also acceptable level of efficiency. Okay, and then so as a follow-up to this research, we recently implement the design of achromatic metal lens for switch beam antenna operations. So if we have an omnidirectional antenna and place it in front of in the focal point of the metasurface, so consider this yellow part here is the metasurface. If we have an omnidirectional antenna and we consider the metasurface to be reciprocal, so we can have the planar wavefront in front of the metasurface. So this is and this planar wavefront in the far field would be will have a higher directivity than the omnidirectional antenna. And particularly if we make some lateral displacement of this omnidirectional antenna, we can implement or we can get a beam steering effect. So if we have, for example, we have certain some antennas in front of this metasurface, and we implement a certain switching system, the metasurface, the omnidirectional antenna will change from one to another. We can have beamforming, and we use this metasurface, particularly broadband metasurface, to realize this effect. And so this is the design metasurface. We consider a 2D metasurface. So the design methodology is the same as the previous slides, and we see here that we have a acceptable level of amplitude. So this is the simulation results using CST, and we see that the phase profile also consistent with the analytical calculations. And then we characterize the metasurface using 2D near-field scanner. So we just recently did this measurement using VNA and 2D scanning in our lab here in BRIN. And we can get some so basically this open-ended waveguide is the probe, the near-field probe that we use for the scanning, and we see that the focal point is consistent on from 9.5 to 8 from 8.5 to 9.5 gigahertz, and the phase profile also consistent. That means the metasurface, the meta lens is achromatic and broadband. And next, we want, as mentioned before, we want to use this as a switch beam antenna system. Therefore, we first simulate this in CST, and we get this near field profile from the CST when the antenna is in the center of the meta lens, and this is when the antenna is moved a little bit. And the far field profile from the simulation agrees quite good agreement with the measurement results. So this is just recent result that we obtained. Okay, so this is the last part of my presentation, which is about the UAV mounted metasurface for IoT applications and also cross-frequency information relay using metasurface. So basically, I will just explain a little bit background into this research, as this research is still ongoing in my current institution in BRIN. So this is the research scope that I'm currently focusing in the Research Center for Telecommunications. Particularly, I'm in the research. I'm a member of a research group of RF, microwave, photonics, and acoustics. And so some research topic that I'm interested to conduct currently is the metasurface for communication, sensing, and power transfer. So therefore, in order to implement this metasurface, we will explore some recent or up-to-date research topics, which are time-varying metasurfaces, nonlinear metasurfaces, and also metasurface with flexible and transparent substrates. And currently, we have also collaborators from Telkom University, also from Monash University Indonesia, also from Université Polytechnique Hauts de France in France. Okay, so this is one of the topics that I mentioned. So we are interested to realize a UAV-mounted metasurface for IoT applications. So the motivation behind this research is that we want to use a metasurface for wireless power transfer and data collection in IoT applications. So we know that IoT devices, particularly those used for environmental sensing, they are placed in remote and hard to reach areas. So it is difficult to change the batteries of these IoT devices. Therefore, they often face power constraints. And what we want to do is we want to use UAV or drones to deliver power into these devices. And therefore, we use metasurface mounted into these UAVs to implement beamforming, which can increase the efficiency and the implementation of the wireless power transfer. And also,
I just want to remind the speaker that we only have about 3 to 4 minutes before we go to the question and answer session, and then we close the session. Thank you.
Okay, no problem. So yeah, so basically, this is the one of the research topic that we are currently interested in, and so the UAV mounted metasurface will deliver power into IoT devices and also collect data from IoT devices. And so basically, there are plenty of research going on in here. For example, we need to know how to optimize the power, because we need to balance between the use of power by the UAV, the metasurface, and also the IoT devices that we want to deliver the power. So, okay, and the next research topic that we are also interested in at the moment is the cross-frequency information relay using metasurfaces. So the motivation behind this research is that we see the rapid expansion of IoT, and therefore many IoT devices will be available, and that will be difficult for the cellular networks because the demand for data will be increasing rapidly, and therefore the cellular networks, we know that they will change into higher frequencies in millimeter wave, such as 26 gigahertz. So we know that the 5G standard already include this 26 gigahertz. So then we face the next challenge, which is IoT devices typically work in low frequencies, and therefore they are incompatible with the cellular networks. And therefore what we want to do here is to create a cross-frequency information relay and facilitate it by metasurface. And so we are currently conducting this research on the metasurface with time varying and also nonlinear operations, and to enable seamless communication between low frequency IoT devices and high frequency cellular networks. Okay, so this is the last slide I wanted to present. So in summary, we utilize surface impedance modeling to derive bandwidth limits for achromatic metasurfaces. And also we use the surface impedance modeling to synthesize the broadband transmissive Huygens metasurface. We implemented for 2D rectangular waveguide, and also we just recently did experiment for switch beam antenna applications. And so I just introduced you to metasurface for cross-frequency information relay, and also for active beamforming in UAV platform. Okay, I'd like to thank our collaborators for generous support and helpful discussions. Also, thank you very much for your attention. Please, this is my emails. Don't hesitate to contact me if you have questions or want to do some collaborations. Thank you.
Okay. Thank you, Dr. Asif, for the very interesting talk. And I'm sure that we are going to have several questions about your work. So therefore, I'm going to open the question and answer session. If anyone has questions to ask, you can open your voice, or I think you can also ask through the chat. Yeah. So is there anyone who wants to ask to the voice? You can raise your hand. In the meantime, okay. So we have a question from Saida. Yeah. So can you open your mic?
Oh, directly now?
Saida,
Okay.
yes. Okay. Yes.
Thank you for the chance. I am Asaida. I'm from Physics Department, University of Sriwijaya. I would like to know about the last slide, I think. What is exactly metasurface function in the cross-frequency information relay? I just curious.
Okay, thank you. Okay, should I answer now?
Yeah, I think you can answer now. We will answer the question.
Yeah, thank you very much for very good question. So we know that the metasurface now has been implemented for frequency conversion. So that's what we are interested in. So I don't have many slides and time to present those results on time varying metasurfaces, but basically the time varying metasurface can modulate. So the metasurface, the meta atom, is reconfigurable, and when we implement the reconfigurability by modulating in a certain period very fast, so the modulation is fast, and then we can change the frequency operation of incident wave. So that's what the physics behind this. So we also see we also see that nonlinear metasurface can also implement this frequency change, because nonlinear elements such as diodes, if we implement the diodes into the metal atom, into metallic structures, it generates many frequencies. So it generates harmonics. So the current from the diode contains many frequencies, and therefore we can utilize these frequencies and maximize the certain frequencies, such that the reflection or transmission from the metasurface has different frequencies.
It
So
means
this is
the amplification of the signal, no?
It's the conversion of frequency.
You convert the frequency in the
Yeah.
telecommunication process.
It's in the telecommunication system, in wireless system, yeah.
For the modulation frequency, right?
Yeah. So certainly the incident communication signal has a certain frequency, right? So for IoT device, it's 900 megahertz or 1 gigahertz. When it hit metasurface, we can change the frequency operations without the conventional device. Like without, for example, we need to, if in conventional way, we need to use a local oscillator and change take the data and then transmit again in a different frequency. So that's the conventional way we can do. But
So
metasurface,
we do not need any other cellular tower.
No. So the cellular network's still there, but the frequency operation can change. So you know what I mean? So the IoT device works in low frequency operation, but the cellular networks may work in the high frequencies, like millimeter waves. So they are incompatible. So we want to make them compatible with some device, with some. So what we propose at the moment is to use metasurface with time varying operations.
Oh, okay. Thank you.
Thank you.
Okay, no worries. Thank you.
Dr. Asaida, for the question. I think there is another question in the chat, but I think you can answer it briefly, Dr. Asif. The question is how high is the data rate when streaming the bits through a metasurface? Is there any theoretical limit or anything that you know?
Yeah, that's a very nice question. So honestly, we don't have quite answer at the moment, because we are still working on this research, but certainly there will be some limits, because for example, the data rate for millimeter wave will be very high, and we still don't know whether the limitation is imposed by physics in, for example, the nonlinear device. Maybe the diodes has some limits in the switching process. So we don't know. So yeah, basically this is the question that we want to answer in the research. So
okay, thank you. I think we are running out of time a little bit here, so we still have some things to do. So thank you again, Dr. Asif, for the talk. Before we close this session, I would like to summarize, and we would like to give you something at the end of the keynote talk. So to summarize the title of the talk is The Advances in Microwave and Millimeter Wave. So Dr. Asif started the talk with the fundamentals of metamaterials, and especially the metasurface, which is basically the two-dimensional version of the metamaterial. He talked about how you can model the metasurface for the objective that you want to achieve. So basically how it works is you reverse engineer from the surface, from the one wavefront that you want to achieve, you derive the metasurface, which is basically deriving the surface impedance and the function of the metasurface that you want to achieve. And beyond the wavefront manipulation, Dr. Asif also mentioned some applications of metasurface, which is for analog computations, imaging-based sensing, wavefront selectivity, and cross-frequency modulation. So basically, it's not about manipulating wavefront, metasurface is a powerful device which can achieve many things depending on how you design it. And Dr. Asif also talk about some applications that we can make by using this powerful tool called metasurface. One of them is the broadband achromatic metasurface, which is basically one of Dr. Asif's work, I think, when he was doing his PhD and even after arriving at the BRIN. And the future applications include the switching beam antenna, where instead of and the UAV mounted metasurface, where you basically put the metasurface on the UAV, so it acts as the second point of relay. So basically a relay, but you use metasurface in the air. That's what I understood from it. So thank you again, Professor Dr. Asif, for the interesting talk. And lastly, as a token of appreciations, we would like to award to Dr. Asif this token of appreciation. Thank you very much for your talk, for participating in this conference.
Thank you for
and therefore we are gonna close this keynote sessions, and I'm gonna return the session to the MC, to the organizer. Thank you very much, everyone. Thanks.
Thank you.
Thanks to Dr. Fadil Habibi Danufani and Dr. Asif Aminullah Fatnan for having brought to us the second keynote talk. We are now ready for the parallel sessions 3 and 4. Our host is currently assigning presenters based on the program schedule. For the rest of the participants, you are free to move between rooms using the breakout rooms menu. Some reminders again for presenter to keep the naming convention according to the guidelines. Also, I encourage you to stay logged on during the short break. And please turn on the video if you are presenting in your sessions. And please have your presentation slides ready for the question and answer sessions. Also, another 2 important things to keep in mind during your presentation. This is mandatory for your completion of publication with IEEE. First, to attend your question and answer session, and second, to fill in the attendance form as the presenter during your parallel session. For all the participants who want to ask some questions during the Q&A, please use the raise hand menu or type in your question in the chat rooms. After the parallel session 3 and 4, we will have a short break followed by parallel sessions 5 and 6 at 3:10 p.m. GMT +7. May you all enjoy and have productive presentation sessions.
Hi, good afternoon, everyone. I would like to check who are already in this chat room, especially for
Recording in
presenting.
progress.
Good afternoon, everyone. I would like to check for the presenter if they're already here. Okay, let me call Mr. Samsudiat. Are you here?
Yes.
All right,
Hello,
thanks.
everyone. My name is Samsudiat from Department of Electrical Engineering, Universitas Indonesia.
Okay.
Today, I would like.
Wait. I'm checking everyone. Okay. Okay. So, Mr. Muhammad Hamdani, are you here?
Yeah,
Mr.
I'm here.
Muhammad Hamdani.
Yeah, I'm here.
Okay, I cannot hear you. Mr.
Yes.
Muhammad Hamdani?
Yes, he's here. He said that.
Okay. Mr. Dedi Irawan.
Yes, I am here.
Okay, we cannot see your face because of backlight. Probably you should change your
Sorry, sorry.
orientations. Okay, and then Mr. Fahru Rizal from Telkom University.
Yes, I'm here.
You're here? Okay,
Yes.
great. And Mr. Denny Kurniadi. Okay, I think he's in the break room one because he's the first presentations turn in the break room one. So hopefully he will be coming on time. All right. So now it's like 13:50, and I think we're already a little bit 5 minutes behind the schedule. So just let's start our talk session. Okay. Okay, good afternoon, ladies and gentlemen. Welcome to International Conference on Radar, Antenna, Microwave, Electronics and Telecommunications 2024 Indonesia, hosted and held virtually by National Research and Innovation Agency Indonesia, or BRIN. Thank you for your enthusiasm and willingness participating in this conference. Let me introduce myself. I'm Zorandi from National Research and Innovation Agency BRIN, and I'm delighted to moderate this Day 1 Parallel Session 4, which conveys the topic about wireless and wired communications. In the session, 5 presenters will give the talk. They are first Mr. Samsudiat from Universitas Indonesia, second Mr. Muhammad Hamdani from National Research and Innovation Agency Indonesia. The third is Mr. Dedi Irawan from National Research and Innovation Agency Indonesia. The fourth presenter will be Mr. Fahru Rizal from Telkom University Indonesia. The fifth will be Mr. Denny Kurniadi from National Research and Innovation Agency Indonesia. So the presentations is video recorded, but Q&A sessions will be live and will be done after the presentations. Okay, before we proceed to the first presenter, I would like to inform to all participants who wants to raise questions, please use raise hands function in the Zoom during and after presentations. After the presentations completed, I will call your name and you can start delivering your question by unmuting your video and audio. And also you can deliver your questions through the chat box. We strongly encourage all participants, including the presenters, to use English for the Q&A sessions. If any of you needed assistance, please let us know by typing in the chat box and we are happily to assist you. Okay, so let's get into the first presentation on the paper entitled Performance Improvement of Ad Hoc On-Demand Distant Vector AUDV Routing Protocol using K-means clustering in Flying Ad Hoc Network. Please welcome Mr. Samsudiat from Universitas Indonesia.
Hello everyone, my name is Samsudiat from Department of Electrical Engineering, Universitas Indonesia. Today, I would like to present our research whose title is Performance Improvement of AODV Routing Protocol using K-means clustering in Flying Ad Hoc Network. The outline of this presentation are introduction, proposed method, result, and discussion. Let's start with introduction. Unmanned aerial vehicles or UAVs or drone working together to achieve a specific task form Flying Ad Hoc Network or FANET, a group of mobility nodes that can communicate with each other directly without needing a centralized infrastructure. The application of FANET are surveillance, search and rescue, detection and tracking, managing wildfire, relay deployment, and traffic monitoring. The challenges of FANET are: in routing, FANET exhibits higher mobility compared to MANET or FANET, resulting in frequent topology change. In interference, 3D deployment may influence the number of links, hence interference among nodes, more link density compared to 2D deployment. In path planning, life change in course to adapt to varying conditions. In quality of service or QoS, support for data traffic relaying in addition to peer-to-peer communication, which may require prioritizing types of data. In variable scenario, urban and rural. There are three types of routing protocol in VANET, namely proactive, reactive, and hybrid. In proactive, the routing table are continuously updated among the nodes to ensure the routing paths are available when needed. Impact in pushy forwarding a large number of service messages, inefficiency in high networks or environment. The example of this protocol is OLSR, DSDV, etc. In reactive, a path between nodes is discovered when a node needs to forward packet. Requires time or delay to discover the route. The example of this routing protocol is AODV and DSR. In hybrid, combining proactive and reactive to solve the routing overhead problem of proactive protocol and the high latency problem of reactive protocol. The example is HWMP and ZRP. This is the preview study of an optimized routing protocol. Nair and Ray et al. Performed simulation of several routing protocol for VANET using NS2. The results show that HWMP and OLSR perform suitably well in node speed variation, varying in the number of nodes regarding throughput and packet delivery ratio parameters. Kurkina et al. Modify OODV in VANET routing protocol by clustering algorithms using K-means and Gaussian mixture model. The results show that K-means algorithm grouping the nodes reduce the number of service packets more efficiently than the GMM algorithm. Bautista et al. Customize the routing matrix of hybrid wireless mesh protocol by using square root frame time and comprehensive radio and power. Compared with the default airtime routing metric, the proposed method improved the performance of VANET due to the network throughput and end-to-end delay evaluation. In this study, we proposed an optimized AODV in VANET routing protocol by clustering algorithm using K-means. Next, the proposed method. We use ad hoc on-demand distance vector or AODV routing protocol. The routing path is discovered by broadcasting route request packet to all nodes. Then the destination node will send a route reply, which set up the path. This routing discovery process often causes an unnecessary transmission, resulting in packet collision and congestion in the network, so an optimized routing discovery is needed. K-means clustering is an unsupervised learning algorithm used to solve clustering problem in machine learning. This algorithm divides the data into key number of clusters. Each cluster is associated with a centroid, the main point of all the data points in cluster. The goal of this algorithm is to minimize the sum of square distance between each data point and its assigned cluster centroid. AODV with K-means clustering. AODV is a widely used routing protocol in VANET because of its simplicity and adapts efficiently in volatile network. K-means is a popular clustering algorithm because it is easy to implement and capable of faster computing. The proposed method is selecting the best cluster of route request packet broadcasting of ODV using K-means clustering. The goal is to reduce the unnecessary transmission in the network, reducing the congestion and the delay of the network. Parameters used in K-means clustering are distance to destination, number of transmission error, and free buffer space. This is a process of K-means clustering in AODV. Next, the simulation process. This study uses NS338 to perform simulation and measure the performance of VANET's routing protocol. First, simulation parameters are configured, whereas AODV with the K-means algorithm is set in the protocol library. Then the nodes are created with a proper configuration. After all parameters are well configured, the simulation is running. If the simulation is success, data is gathered. However, if they fail, recheck and reconfigure the simulation parameters. This is a simulation parameter. We use number of nodes and speed as independent variable. The number of nodes is 25, 50, and 100 in 30 meters per second in speed. In speed, we use 10, 30, and 60 meters per second. In number of nodes is 50. The performance analysis, we use 3 parameters. Throughput is actual data rate per unit time in kilobyte per second unit. Packet loss is the number of packet loss during the process of sending packet from the origin node to the destination node. Delay is the time lag between a packet being sent and the packet being retrieved at its destination. Next is result and discussion. Simulation result in throughput. The throughput of AODV with K-min is higher than the original AODV in varying in number of nodes by 17% and node speed by 24%. In AODV with K-min, increasing the number of nodes will increase the throughput. On the other hand, increasing node speed will decrease the throughput. The packet loss of AODV with K-min clustering is lower than the original AODV in varying in number of nodes by 4% and node speed by 14%. In AODV with K-min, increasing node speed will increase packet loss. In the delay of AODV with K-min is lower than the original AODV in varying in the number of 4% of node and node speed by 20%. In AODV with K-min, increasing number of nodes will increase the delay. On the other hand, increasing node speed will decrease the delay. This is the conclusion of this presentation. Based on the simulation, the results show that AODV with K-min provides better VANET routing protocol performance than original AODV in terms of network throughput, packet loss ratio, and end-to-end delay. For future work, another routing protocol, such as proactive or hybrid, can be utilized with another optimized routing protocol. This is the end of our presentation. Thank you.
All right, thank you, Mr. Samsudiat, for presenting your work. So I would like to invite participants to ask some questions. Due to limited time, we only facilitate limited number of questions. So let me check who has the question here. Muhammad Iqbal. Okay, Muhammad Iqbal, Mr. Muhammad, you can unmute your audio and deliver the questions.
Hello, good afternoon, everyone. Thanks, Mr. Samsudiat, for the presentations. I just wondering if you, in your related works, there are some publications that also use the same clustering method, which means K-means. Have you ever considered to compare your results with these previous results? And the second, may I know how you measure the end-to-end delay in your simulations program? That's all.
Okay, thank you, Mr. Muhammad Iqbal.
Yeah.
Okay, Mr. Samsudiat, you can answer the question.
Thank you, Mr. Muhammad Iqbal. From previous study, we use clustering method to 3D deployment in VANET. VANET is 3D deployment. In previous network, use MANET. MANET is two-dimension deployment. Next, the
answer. Okay, so you already answer the questions, Mr. Samsudiat?
Yes.
Okay. Anybody else who has any questions can raise the questions?
May I question to Mr. Samsudiat?
Okay, Mr. Dedi Iran. Okay.
Yeah. Thank you very
can-
much for
okay.
your time. I have a question. Have you compared the algorithm Cummins with an other unsupervised algorithm for finite scenario? Thank you very much.
Thank you for the question. In this paper, we not yet simulation and any method and clustering method.
So means that you have done only for K.
Yes, only K-means
K-means.
clustering.
Okay. All right. So I'm sorry to cut this Q&A session because we are very limited time. So we are gonna move to the next presentations, which will be given by Mr. Muhammad Hamdani. He's gonna talk about an extension of simulating spanning tree protocols in a dual landing station cable-based emitter with multiple ocean bottom units. Okay, Mr. Muhammad Hamdani, are you there? Apparently he has a problem. So
I heard he has a problem with his laptop.
Excuse me?
I
Who
heard
is
he
talking?
has a problem with. I'm Rio. I've heard that he has a problem with his laptop, but I'm not sure.
Yeah, I got notification from him as well. So to save the time, I think we will go to the third presentation and let him to present his work whenever he comes. Okay. So I'm sorry for this technical glitch. Let's start to the third presenters of this session. It's gonna be presented by Mr. Dedi Irwan. It's about mobile ad hoc network managed protocol performance with mobility and transmission power variations. Mr. Dedi Irwan, the time is yours. Mr. Dedi Irawan, unmute your the video, please. Okay, the video. Okay.
Okay. I share the video.
No, the video co-host, the third video should be played. Okay. All right.
Okay, thank you very much for your time. First of all, allow me to introduce myself. My name is Dedi Irawan. I am from Telecommunications Research Center at BRIN. And as a presenter, I will present about our research entitled Mobile Ad Hoc Network Managed Protocol Performance with Mobility and Text Power Variation. Okay, for starting, in introduction, what is mobile network? What is mobile ad hoc network? Mobile ad hoc network or MANET is a temporary network from mobile device without infrastructure, and each mobile device communicated with each other using radio frequencies. In MANET, each mobile device acts as node, and then nodes can function as host or router. Node needs a routing protocol to send or receive data each other, and we can see in the right of the slide, ad hoc routing protocols can be divided into two. There is flat routing and hybrid routing. Flat routing divided into two again. There is a reactive and proactive. MANET have For general F3 routing protocol, as we say before, there is reactive routing based on demand mechanism, and proactive routing based on table driven, and the hybrid routing based on combination reactive and proactive mechanism. So background of our research is change in topology in ad hoc network are frequent and unpredictable, making routing between nodes always need adaptation to those changes. Routing is the most active in a MANET, so there is a lot of research on MANET routing protocol, such as research on the performance routing protocol. Application on MANET is varied, such as for military communication, wireless sensor, and vehicle ad hoc networks or PANET. It is necessary to measure and test the performance of the MANET protocol that is suitable for the above application using variation of speed and text power in node. Okay, our proposed model and method, there are can be divided into two. The first is simulation parameter, and the second is flowchart. The simulation parameter we use are time of simulation. We start from begin 0 to 200 seconds. Data packet delivery we start at 50 seconds. Channel type we use wireless. Source of traffic we set UDP. Mobility model we set random waypoint. Number of nodes we set 25 and 50. Speed of node we set 5, 10, and 50 meter per second. Size of packet data we set 64 bytes. Dimension we set 1050 times 3000 meter. Text power we set 7.5 and 9.5 dB. And for flowchart, we can see we start from activated NS3 simulator, and then we create network file tracing, and then set adjust node velocity, size of the packet, and then we adjust Wi-Fi physical and channel, and then we create device for connecting node and channel, and then adjust dimension of the space and the mobility of node. And then we set setting protocol routing, and then we set IP address, and then we create file XML and flow monitor. After we set all of this, we can run a simulation. If simulation work yes, of course, we can capture parameter metric, and then we can analysis of data. If not, we go back to create network. We go back to beginning, create network, and file tracing. Okay, this is a result and analysis simulation of 25 nodes. We can see there is two parameter. Our measure and analysis, that is receive rate and packet receive. Okay, this is table on graph, starting with 5 speed of 5, 10, and with text power 7.5 and 9.5. Okay, this is a continue result analysis simulation of 25 nodes. We can see in the figure 5 in previous slide. showing at the speed of 5 meter per second with the text power 7.5 and 9.5 dB, our DV and DSR protocol much better on the receive rate and the packet received than the others. Same in the figure 6, showing at the speed 10 meter per second with text power 7.5 and 9.5 dB. The result same with figure 5. There is our DV and DSR protocol much better than the others. In the figure 7, showing at the speed 50 meter per second with text power 7.5 and 9.5 dB. Again, this protocol, our DV and DSR protocol, much better on the receive rate and the packet received than the others. And we continue to result and analysis simulation of 50 node. Same with the 25 node. This is graph result of simulation with 5, 10, with the 7.5 and 9.5 text power. And the analysis of 50 node, there is interesting. In the figure 8, we set text power to 7.5 dB, showing average receive rate out protocol reach until 20. We can see in the figure 8 with 5 meter per second with 7.5 dB, average of receive rate is reached on 20. However, between time of 120 and 140 seconds of the simulation, average receive rate decrease. If the text power is set to 9.5 dB, the average receive rate more stable at 20 for all. We can see in the text power 9.5 dB, the receive rate more stable compared with the receive rate with the text power 7.5 dB. We can see the difference. Okay, next in the figure 9, true that the DV and DSR protocol outperform the others. The figure show that the text power has an impact on the average receive rate and the packet receive for all protocols. And the last in the figure 10, showing at the speed 50 meter per second with the text power 7.5 and 9.5 dB. Again, our DV in the purple and DSR in the blue. Protocol much better on the receive rate and the packet receive than the other. Okay, this summary, we can say in the both scenario 25 and 50 nodes, modeling and simulation of MANET work well on the NS3 simulator. And two, it can be concluded that the variation of speed and power greatly affects the performance of the routing protocol on the receive rate and the packet receive. And three, from the simulation carried out, the AUDV protocol is much better compared with the others. And therefore, it can be concluded in this research that the reactive on-demand protocol type is better than the proactive table-driven. This study has not yet met comparison with the hybrid protocol type on the MANET. Okay, that is my presentation. Thank you for your attention. My time is back to the moderator. Thank you very
Okay, thank you, Mr. Deddy. So let's get into the Q&A sessions. Do we have any of participants who raised the questions? Probably nobody raised the hand. Let's check in the chat list if somebody raised the questions. Okay, so if nobody asks, let me ask you, Pak Deddy. Mr. Deddy?
Yeah.
Don't be nervous, okay? So you have your video turned on and audio. Okay, so my question is, it looks like your solutions reveals that AODV outperforms than the others. Do you have any justifications or analysis why this AODV is better than other scheme? That the first question. The second question, does your scheme consider acknowledgement packet flow? Means that in the reverse. I mean, this is like on demand, right? Does it also consider the reverse flow of the packet, especially for reply packet? Thanks.
Okay, thank you for your question. The first, I can answer the ODV is a proactive routing type. This protocol keep routing information up to date across the network, by having its not store routing information. The type of routing is the base for network with low mobility or where not transmit data frequency. Compared to the reactive routing like IODV, this protocol create route on demand when a packet needs to be sent. There are designed for environment where the network topology is constantly changed, such as wireless ad-hoc network made up of portable nodes like mobile phones. However, like you say, reactive routing can lead to high latency and lack of security due to time-consuming discovery process.
Okay, thanks for your answer. So apparently we have no other participant raising questions for this paper. If not, let's wrap up for this presentation. Okay, so let's get into the, actually it's supposed to be the second presentations, but because of some technical glitch, he's gonna be getting for the third turn. So let's hear for the presentation about performance, about an extension of simulating spanning tree protocols in a dual landing station cable-based method with multiple ocean bottom units. So Mr. Hamdani, are you there? Mr. Hamdani?
Yes, I'm here.
Okay, Mr. Lukman, you can play the video by Mr. Hamdani.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon to all attendees. Allow me to introduce myself. I am Muhammad Hamdani. I'm from the Research Center for the Telecommunications of National Research and Innovation Agency, or we can call it BRIN. Today, I'd like to present about our works, which is an extension of simulating spanning tree protocols in dual landing station cable-based method with multiple ocean bottom units. And this is our works. There are some co-authors, Pak Ananda, Pak Deddy, Pak Tahar, Pak Toto, and Pak Insan. Okay, we have known that tsunami is one of the big disasters with the giant waves caused by earthquakes or volcano eruptions under the sea, where one of the biggest tsunami that Indonesia experienced around December 2004 caused by earthquakes in Indian Oceans. On the other hand, some scientists predict that Indonesia will face mega trusts along Sumatra and Java Island in the early future, because Indonesia is having some volcanoes which part of the Pacific rings of fire. So that will have an early warning system innovation to mitigate this kind of disaster, which is tsunami. The mitigation system, it's called INA-CBT, or Indonesia Cable Indonesia Cable-Based Tsunami Attack. Sorry, that deployed from 2021, for example, in Labuan Bajo site. Yeah, this is the system where the INA-CBT system have the landing station on the island, and they laying the fiber optic cables to the seabed or seafloor. That's around many hundreds of kilometers, and along the fiber cables, it deploys some of the sensors that embed and covered by the canister, and it called the OBUs, or ocean bottom units. This is our related works. Actually, this paper is a continuation of our previous work, which look for the possibility of using open protocols on the INA-CBT system. This is our first papers around 2022, where we are trying to analyze whether the existing system that have deployed, we can use the open protocols. Yeah, because the deployed system, the existing system, is using the proprietary protocols for failover, and we know that the proprietary is not good because it's very dependent and very costly for about in terms of price. So the result is we can use the open protocol, which is STP or spanning tree, and RSTP or rapid spanning tree. And then of the works, whether we can deploy many OBUs, because the previous one we just analyze whether we can use 2 OBUs. But previously also we analyze whether we can scale up, until the 10 OBUs, and we do it through the simulation, which is OMNet++. This is our goals. That our works, we try to analyze whether we can deploy 2 sites of the INA-CBT. There are 2 landing stations that connected between 2 islands. In terms of the analyze, before we analyze the system, we divided the design of the 2 diagrams. First, the physical diagram is shown in this slide, and we can see that on the diagram, which is a logical diagram for topology, for ring topology, the OBUs are connected in serial way. Yeah, so that the usage of fiber optic cores is minimum rather than the mass. But if we want to deploy the INA-CBT system in mass topology, the core usage will be increases, of course, because the each OBU are connected to both landing stations. We noted that the blue circles means the root bridge, because on the spanning tree, we have to elect it, the one of the root bridge that on the spanning tree itself. Because this root bridge will be as the reference when we need to block or forward the ports. And in order to analyze the downtime, we use the discrete event simulator of the network, which is using the OMNet++ 6.0. Then we mimicking the topology and network settings. Then we create the scenario which are failover and failback. The figure 7 is a mesh topology, and the figure 8 is a ring topology of the simulations. There are two scenarios of each topology, which is the nearest point. We put the downtime. There is an incident, let's say. We put two downtime. We put two incidents. The first one is the nearest point with the root bridge, and the second one is the farthest point. As you can see on the figure 9, this is mesh topology. The farthest point is on this side because in each spanning tree in the mesh topology will have multiple spanning tree, but this is the visible points that we can analyze. But in ring topology, the farthest point, let's say this is the topology of the 5 obvious, and we put the farthest point is on the down B. Yeah, this one between the LS2 to the obvious 5. The failover downtime is that we need by the spanning tree to convergence the road while the incident occurs. Then the fileback is a downtime that was needed by the spanning tree while the network recover the spanning tree topology back to the original one. This is our results regarding the physical diagram. As the ring topology use less optical fiber, so the cost will be less than the mesh topology, of course. So the core usage and the cost is linear. Then we also measure the failure rate by calculating the network fail when the incident occurs in each hole. The result is ring topology have a higher failure rate because the ring topology is very dependent to their neighbors. So once the neighbors fail, it will impact the others. However, room space of the obvious is relatively similar. The obvious dimension is limited enough, yeah, because you know that we have also need to consider about how many devices that we can deploy inside the obvious, and according to our analyze, this is similar between the physical ring and physical mesh. And about the in terms of logical diagram results, after the simulation run, we could get the results. For example, as shown on this figure, it was the result of STP in failover and failbacks, which are exactly the same. We can prove that STP is not affected that by the amount of nodes inside the topology. Yeah, we try to simulate from the 2 obvious until the 8 obvious, and exactly the same, because their calculation mechanism is based on the delay timer in order to change its step, either from forwarding to blocking and vice versa. But when we see of the RSTP, rapid spanning tree, the failover and failback are different. The failover RSTP shows that when the total obvious are old, then the failover downtime are less than even obvious. This is happen only on the ring topology because the distance of the blocking port towards the toward to the road bridge is different between the odd and even obvious. This will affect the convergence time of the RSTP. However, in the fileback, the mesh topology seems stable of the downtime because the mesh topology is not complicated as a ring topology while performing spanning tree. Spanning tree will form multiple ring inside the mesh topology itself. So it was simplified. And our conclusion is the mesh topology is a lower failover time and failback time, but higher development costs. In other ways, in ring topology, higher failover time and failback time. However, it still meet the system requirements, the lower development costs, of course. Thank you.
Okay, thank you for Mr. Hamdani. Hopefully you are not so nervous about this technical glitch.
Yeah, hopefully. Thank you.
Yeah, apparently this is like echoing on your background sound. Is it possible to suppress the echo or it's not possible?
Okay, although because maybe I'm nearest from my second device. Is it okay now?
Okay, yeah, it's okay. Okay, so let's go to the Q&A sessions. Let's see if anybody of in this session raising the questions. I didn't see anyone. Okay, is there anyone to ask? Okay, Mr. Muhammad Yusuf, the time is yours. Please unmute your audio.
All right, thank you, Mr. Moderator, for the opportunity. It is interesting topics, by the way, Mr. Hamdani, for bringing the STP to the Indonesian cable-based sonometer. But I have a question about the protocol that you have implemented in your simulation. Is there any specific consideration, or is there any beneficial that you could elaborate why you choosing the spanning tree protocols, or maybe for the specific protocol is RSTP, or rapid spanning tree protocol? Is there any specific beneficial for the setup that you have built using this protocol?
Okay. Thank you very much, Mr. Yusa, for the questions. Yeah, actually, according to our first work last 2 years ago, actually we tried to find the alternative protocols that can use instead of the current one, because the current one we use the proprietary protocol from I cannot mention the vendor names, but it was the turbo ring protocols. As we have checked the turbo ring protocols, it's actually based on the spanning tree, so it works in layer 2. So we tried to find the similar protocols that can improve, not improve, I mean can use instead of this proprietary, and the spanning tree is the answer. The beneficial if we use the spanning tree or rapid spanning tree is because it was open, so you can use any network devices, and usually all the network devices, let's say for the switching mode, is already comply with the spanning tree protocols. Yeah, that's one the beneficial in terms of the price. Let's say you will not dependent on one vendors only, because once you depend on the one vendors, yeah, you can be like vendor lock-in, and so you cannot choose another brand or vendor device. So yeah, that's one my answer. Hopefully it answers.
All right, thank you, Mr. Hamdani. I think only one questions available will be facilitated from Mr. Muhammad Iqbal. Okay, you can turn on the audio and video for the questions. Thank you.
Okay, thanks, Mr. Muhammad Hamdani, for your presentations. I think it is interesting because STP is providing openness for everybody, right? So my question is, what is your next prospect future research after this? And my second question, do you ever consider to make your own or develop your own spanning tree protocols rather than using the default spanning tree protocols?
Yeah.
Okay, that is my two questions. Thanks.
Thank you very much, Mr. Muhammad Iqbal. He was my best friend. Okay, for your first question, our future works will be to deploy it in prototype, because we have worked in long time in the simulation phase, but next time we try to to make it semi-real. Let's say in the prototype using the virtual machine, we can know the behaviors if we deploy it in real system. And yeah, let's say once the institution have the budget to deploy it, so we have the references from our works to use that protocols. And to answer your second questions about is it possible to let's say create the customized protocols? Yeah, it's very possible. we also have to try to mitigate and try to research what kind of the TCP protocols that suitable for this disaster system, because this is a very critical missions. Yeah, you have now this kind of the topics. So we will try to find and try to customize the protocols for any securing the communication. So any other parties, let's say once we use the third party list line, so they will not knows about the communication inside. So for securing in terms of securing, we will try to create the customized protocols and also to accelerate the communication pace.
All right. Thank you, Mr. Mohammed. Sorry, I'm interrupting because we have very limited time. So, okay, thank you for your presentation. So I think we can go to the 4 presenters. It's going to be the presentation of a paper entitled A Single Parity Check Network Coding Based on Iterative Spatial Demapper by Mr. Fahrul Rizal from Telkom University. Please welcome Mr. Fahrul Rizal.
Okay, good morning to all honorable attendees. First of all, let me thanks to the organizing committee for this valuable opportunity. My name is Fahrul Rizal, and today I feel very honored to share our research result focusing on single party check network coding based on iterative spatial demapper. The outline of my presentation today consists of introduction, a single party check network coding system model scenario, network model, proposed system model, XC chart, result, and conclusion. The problem in my paper was the effort of wireless communication with many usage scenario and new capabilities. Reducing time slot is an established method to improve spectrum efficiency. It's challenging without modern signal processing and channel coding. In smart era, growth of telecommunication user by machine will result in a surge in network traffic, which may cause spectrum efficiency issue. To address issues of time slot usage, simultaneous transmission in multiple access channel and iterative spatial demapping can be utilized to reduce time slot usage. In this system model scenario, the SPC used as network model, where the real data block of SPC will be the sources and the parity bit will be the connection from the relay to the destination. In this simulation, we're using network model with 2 sources, 1 relay and 1 destination, with the assuming distance is D equal 1, where the source 1 to destination is equal to D, source 2 is set closer to the destination, which distance is equal to 0.8 D, and so on. The modulation we are using is a binary phase shift keying, and the channel we are using relay fading with noise component Z is sigma power of 2 per 2, where the source and relay have same power transmit. Due to the difference of distance to each node, relay and destination will receive the different power level, where receive power level obtained by the longest distance in the network divided by the path taken by the information followed by exponent path loss. The exponent path loss that we use in this simulation is for urban area. Due to the simultaneous transmit from 2 separated sources to reduce time slot usage and amplify and forward relay protocol, we got received superposition signal Y as below, where the symbols are determined how two signals simultaneously transmitted are mapped into spatial constellation with any value of theta possible. In this proposed system model, we can see the system block has three segments. The source segment will produce the bit information and transmit to the relay and destination. The relay segment will receive the signal from source and perform AF protocol to forward the signal to destination with amplifying. And the destination segment will receive the signal from source and relay to do to ESM to decode the received signals and perform error correction, where the source segment will generate binary bit randomly. And then in the block C, the symbols are repeated 3 times with red 1/3 in matrix G. Then the symbol array sequence scrambled in P block with random interleaver. And the information bit will be mapped into BPSK symbols and modulated into a signal carrier on block M and transmit simultaneous into relay and destination. On the relay section, relay only perform an AF protocol, which is only receive signal information from sources and forwarded to destination with amplifier. This amplifies or used to prevent signal from losing the powers. On the destination, the signal both from sources and relay received and perform ESM decoding by using LLR. LLR will use to group the grouping of the possibility of grouping special constellation to calculate the extrinsic of the received signal. The decoding process receives signal from the relay and the source has difference depend on the path taken by the signal. Because the signal from relay pass to channels, the extrinsic LLR from relay and source will be perform channel decoding. And then the extrinsic LLR from relay and source will be perform channel decoder. After the extrinsic LLR are calculated, the array sequence will be restored by the interleaver, and the repetition bit will be restored as well with matrix H by summing all of the 3 extrinsic LLR into LFI. Then the LLR information will be calculated by subtract the LFI information with AI information, and then divided by 6, where the LA information will be used in SM decoder for next iteration to calculate the extrinsic LLR. After all the iteration ended, the LLR, LFI are from sources and relay will be summed into LI information, and the LI and LFI information will be used for SPC decoding, where the information of LI will be corrected using SPC with the help information from LFI RD from the relay. This corrected information of LI will be returned into binary form by using hard decision to calculate the bit error rate. In the F scheme, the received signal YSR relay will be decoded by SM and perform channel decoder by repetition code and the interleaver. The binary bit from decoder will be encoded again with repetition code and interleaver with new permutation index, then mapped into BPSK. Whereas the information from source 2 will be multiplied by imaginary number to gain diversity constellation and transmit to destination. The received signal ORD at the destination decoded by ESN using imaginary number in the process. The extrinsic LLR decoded again by repetition code and the interleaver with new permutation index. In this paper, XC chart is used to determine the number of iterations recorded by ESM, where the XC chart are obtained automatically through the trajectory simulation and shows the number of iterations of ESM for iteration. In this XC chart, you can see that indicates the error cannot be corrected when the SNR is at 0 dB or lower, as the two exit curve intersect before IE reach 1. This intersection occurs because the capacity of C is low while the rate is high. And then the from simulation that we have simulated in the network with two modes that compares between AF and DEF protocol relays, that the AF relay achieves the diversity order 2, while the relay DF protocol not achieve the diversity order 2 because the string error that due to the distortion during decoding process, words make the false information from relay that have strong power. This phenomenon might be prevented by using an update function on the destination decoder. And then in this simulation, we also comparing the SM with 1 iteration and 5 iteration, whereas the result that difference iteration indicates the minimal differences, while the performance of iteration 5 is slightly improved. In the simulation of efficiency with ASM, in this paper, we're using the IF protocol relay with 2 iterations, whereas the bare performance of efficiency with ASM achieved the diversity order 2, reaching a bare of 10⁻⁴ at an average SNR of 7 dB or higher. This outcome indicates that the efficiency simulation performed effectively, meeting wireless communication standard at this SNR level. And the conclusion of this paper are the simulation result for an SPC and C network using SM indicate that the IF relay protocol achieves better performance than the DEF protocol, which requires 3 ESM. The simulation also shows that iteration count minimally affect performance. Overall, SPC and C with SM efficiently reduce the time slot, blending with theoretical bare curves, allowing users to share one time slot. Further studies are suggested to evaluate the DF relay and consider increased user counts per time slot or more complex network to improve system performance. Thank you for your attention and time. We greatly appreciate the opportunity to share our research and hope this result can contribute to development in the field of communication. And that's all from me. Thank you very much.
Thank you, Mr. Fahru Rizal. So let's go to Q&A sessions. Is there anyone to raise questions? I don't see anybody here raising the question or using raise hand question. And I don't see also question in the chat box. Okay, let me ask you just one quick question, okay? Because we are running out of time too. So, okay, I have a question. So your network coding scheme looks like tightly coupled with the assumed network structure. So does it work with other structure, probably such as more than with one relay?
Thank you, Sir Serandi. Let me answer your question. My voice is clear?
Yes, your voice is clear. So go ahead.
So this work actually it can be extended to other network coding schemes. For mention it, when we adding numbers of relay, it will be represent the number of parity check.
Yes, go ahead.
Yes.
Also means that if we have more than one relay, means that there's
Yes.
gonna be more
More.
parity check there.
Yes.
Is it? Okay. So means that single parity check is only working with one relay. Is that correct?
Excuse me, can you repeat your question?
So the question is right. So the question is your scheme work with more than one relay. You said it can work with more than one relay, means we add more parity check, correct?
Yes, yes.
Does it mean that single parity check as you propose here is only for this type of structure? So it means that if it's more than one, then it's going to be double parity check network or something like that?
Yes, it can be double parity check.
I see. Okay. All right. Thank you. Is there anyone to questions? Okay. So before we conclude this fourth presentation, and before proceed to the fifth presentation, I think we would like to take some picture, especially for the presenters. All presenters are required to turn on the video. So Miss Yulia, you can start taking the picture.
Yes.
All right. So yeah, the time is yours to take the picture. 1, 2, 3. Let me know if you're done.
Wait a minute, sir. Wait a minute. Okay, we can start. I will be count. 1, 2, 3, 4. Second page. 1, 2, 3, and then third page. 1, 2, 3. Okay, then, sir.
All right, thank you so much, Mrs. Leah. So I think we arrived to the last presenter, Mr. Denny Permana. Is that right? Mr. Denny Permana, are you
Yes,
here?
I have. Yes,
So,
yes, I have.
so you're completed your break room 1 session, right?
Yeah.
Okay, so let's get into your presentations on the paper entitled as benchtop frequency selective surfaces using ring resonators, simulation, and 6G metal surface potential. Okay, please welcome Mr. Denny Kurniadi from BRIN. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you to the moderator for the time giving to me to present the paper titled Benchtop Frequency Selective Surface Using Ring Resonator, Simulation, and 6G Metal Surface Potential. This research involves several researchers at the Telecommunications Research Center, the Electronic Research Center, and Electrical Engineering Department, Faculty of Engineering and Industrial Education, Universitas Pendidikan Indonesia. I am tasked with presenting this paper. My name is Denny Permana. I work as a researcher at the Telecommunications Research Center of the Electronic and Informatic Research Organization at the National Research and Innovation Agency. Okay, I think this complete. Let's move on to the paper. In this presentation, we will divide it into 5 outline: introduction, proposed design, simulated result, parameter study for optimization, and conclusion. First, introduction, rapid advancement of communication technologies that led to development of 6G network, including more device connected to network, especially with the rise of Internet of Things. Development of material and structure to meet next generation equipment, denser urban improvement with the presence of large number of buildings, improvement of scheme between TX and RX. Increased device density as more device connect to network such as IoT that also compete for limited frequency band increase leading to congestion. Signal from nearby frequency band can split over and interface with the desired signal. Reflection and deflection of signal can create multiple paths for signal to reach a receiver, constructive and deductive interference. Potential of saturation of specific frequency band, causing increased noise and interference. By addressing this interference through technology like benchtop FSS, we can enhance signal clarity and improve overall communication system performance, especially critical for emergency safety application. This purpose design features the following: the one-stop FSS can effectively block specific frequency ranges while allowing other to pass, making it useful for applications such as blocking the electromagnetic interference. Ring resonator can achieve a compact size due to the geometric properties, making the overall design more space efficient. The resonant frequency of ring resonator can be adjusted by varying their dimension or material, allowing for adaptable performance based on specific operational needs. Can achieve super frequency response and improve ejection characteristic at the desired stop band frequencies. The design can be engineered to provide multiple functionalities, such as combining filter with energy harvesting or sensing capabilities, which enhances the versatility of the system. Second, proposed design. This study focuses on the design and simulation of the frequency selective surface ring resonator on an F4BMX substrate, recently tuned to the resonance at 3.5 GHz, where L represents the circumference of the ring, F is the resonant frequency, the mean is the mean diameter, epsilon R consider the effective dielectric constant of the substrate, and C is the speed of light in the vacuum. The dimension of the ring structure are defined by the outer diameter, the out, inner diameter, the in, and the weight of the ring resonator, WR. The detailed parameter of the ring resonator unit cell are illustrated on the figure. Will the optimized parameter value determined using CST software are present on the table. The design specific of the ring resonator include an outer ring with a diameter of approximately 31.26 mm and an inner ring with a diameter of 25.15 mm. These dimensions were carefully selected and optimized the active, the desired resonant frequency and performance characteristic. The optimization process involved adjusting various parameters such as the ring width, the thickness of the F4BMX 220 substrate, and the thickness of the copper layer, ensuring minimal losses and high efficiency and high frequency application. Simulation result, as in the 3D view image can be seen. The simulation result obtained using CST software as parameter S21 value to demonstrate the performance of the element from a unit cell perspective. In another picture, it can be seen. Based on picture above, the structure function as a band stop filter, blocking signal in the 3.5 GHz and allowing other frequencies to pass. In the Q factor value, dimensionless parameter that characterize the quality of a resonant circuit or filter. Called parameter study for optimization. Input parameter, optimization process, performance metric, and output. Optimize ring resonator design, improve efficiency and bandstop performance, and integration into safety communication system. In fact, of the structure parameter, specifically in the picture A, width of the ring WR on transmission response. It can be seen as the low WR increase, the bandwidth grows wider, which can be adapted to adjust the bandwidth. And picture B, different outer diameter, the out, a larger diameter typical, lower the resonant frequency. Will the smaller diameter succeed? Therefore, precise control of the ring resonator diameter is crucial for achieving desired performance in various applications. As so is figure C, thickness of the substrate influences the effective dielectric constant, with in turn affect the resonant frequency. The substrate thickness affect the resonant frequency of the ring resonator. The effective dielectric constant influenced by the substrate thickness must be considered. For figure D, it can be observed that where varying, the copper thickness might not significantly affect the result with the same value as 35 micrometer as the standard thickness of copper in regular PCB. The comparison among the FSS in the tiered in the show on the table, highlighting various parameters such as the metasurface, unit cell type, unit cell size, substrate type, and thickness. This comparison after insight into whole differential configuration of FSS vary based on the discrete crucial parameter, illustrating their impact on performance and applicability across different frequency and application. By examining this factor, researchers and engineers can be understand the nuance difference between various FFS design, aiding in the selection of optimal configuration for specific operational requirement and environmental conditions. Conclusion: the proposed ring resonator design as the reflecting element has been successfully simulated to operate at 3.5 GHz, comprising 35 micrometer thin copper layer deposit on a 1.5 millimeter thin F4 BMX 220 substrate. The simulating result demonstrating excellent bandstop filtering performance. The resonant frequency is precisely 3.5 GHz, achieving an attenuating of -50 dB, a high Q factor of 1315, and a functional bandwidth of 76%. The parametric study based on commercial data for the F4 BMX 220 substrate confirm that the transmission response can be fine-tuned by varying design parameter. With its simple structure, low cost, and easy of fabrication and integration, the proposed frequencies.
You hear? Oh, you hear my voice? I don't know whether the co-host.
Yes, we can hear your voice.
All right. Okay, thank you. I think there's a little bit technical problem. Okay, thank you for the presentations. Is there anyone to have a question here? Please raise hand or in the chat box. If not, I have a questions real quick, Mr. Denny.
Yes.
So sorry if it's a kind of a dummy questions, but I'm really curious why do you create a band stop filter at frequency center of 3.5 gigahertz? Is there something important to this frequency so that we need to block this frequency? Usually, we like to have 3 or certain frequency, and we like to get that, not to block that. So what's the interest? And then the second one, what is the basics material for this F4BM X220? Okay, probably it's maybe a simple question. Thank you.
Thank you very much for your question. Sorry, is my voice not good? The microphone is problem. I think from question will be answered by Mr. Rio. We still on the same team. So make the clear, Mr. Rio, please.
Okay, Mr. Serandi, I will try to answer the question. I would like to answer first the second question. The second question is why we are using the F4 BMX 220.
Excuse me, can you remove your avatar? Use your real face.
Okay. Sip. Okay.
Okay.
Yeah. I'm trying to first answering your second question. The second question, why we are using the F4 BMX 220. We are using the F4 BMX 220. It's first of all, the cost is quite cheap. The performance is if it's compared with the Roger Enduroid, it's more or less it's the same, but the cost it's the F4BMX is same as FR4 substrate. So meanwhile, so we are using the F4BMX for the substrate. And a second one, the first question, why we are using the band stop FSS, specifically stop in 3.5 gigahertz. Actually, why we are using over there, because the frequency is around the 3.5 gigahertz. It's unlicensed spectrum frequency, and actually 3.6 gigahertz it's unlicensed frequency, but 3.5 gigahertz this is only a study case. So we are using all the parameter from the sorry, can you mute for yeah. I mean, so we are using why we are we choose specifically the parameter. It came from the official website for the FOBMX 220. We use all the parameters, and which one are as you can see in the presentation. I will not share screen because yeah, there are in those parameters there are the thickness of the substrate and the electric constant substrate. It will band stopping at 2.4 gigahertz. As we know, in IoT device, mostly are using the 2.4 gigahertz. Sometimes it's lower, 800 or 900, something like that.
Yeah, I got your point. So usually we don't take that 3.5 gigahertz instead of using it. Yeah. Okay, thank you so much. So yes. I think we are already completed all the presentation here. Thank you for all our presenters for giving such interesting and valuable talks in the sessions. We hope all the works presented in this opportunity will give us valuable insight, knowledge, and the benefit in the future. And also great appreciation to participants who already engaged in an interactive discussion in the sessions. Okay, thank you. So I give all the sessions to the co-host. Thank you.
Recording stopped. Recording in progress.
Can we continue to the next session?
Yes, but sir, your video is still avatar now.
Oh, okay. Sorry.
Okay, thank you.
Yeah. I can start. Oh, ini. Oh, yeah. I thought there was a problem. Okay. Good afternoon, everyone. Welcome to session 6 of 2024 ICRAMET. My name is Priyo Hartono Aji, and I will be your moderator for this session, which focuses on remote sensing and radar system, as well as control system, robotics, and mechatronics. Before we started, I would like to check whether all presenter is already in the breakout room. Please turn on your audio and say that you are all in the room, please.
Hello, can you hear me? Edgar
Yes.
Jirosek report. Thank you.
Yes, thanks. Is there anyone? Let me check. I will try to check it first. Mr. Muhammad Putra, are you there? Mr. Zaid Cahya? Mr. Agus?
Yes, I'm here.
Yes, I'm here.
Mr. Sahru Hamidi?
Yes, I'm here. Hello.
Und Herr Edgar Jirosek, are you
Yes.
there?
Yes, I'm here.
Okay. Okay, today our presentation are pre-recorded and each video will play for around 10 minutes. After each video, we will have around 5 minutes for a live question and answer session with the speaker. We kindly ask all speakers to be on standby during the video and keep the video on. If you have questions after the video, you can type them in the chat box or raise your hand button. Let's get started. The first speaker, it is my pleasure to introduce the first speaker is Mr. Muhammad Putra Rasuanta from BRIN Indonesia. We will now play the pre-recorded video. Mr. Muhammad Putra, please be standby and keep your Zoom video on. Co-host, please start the video.
Good morning, colleges. I would like to thank you for all being here. My name is Putra, and I'm gonna presenting our research, which is entitled "The Robustness of LQR and LQR Tracker Cascaded with the Loss Guidance Law for Quadrotor to accomplish our mission." The outline of this topic, we will begin with the introduction that provide background information, outline the problem, and present an overview of the solution. And next, we will present our system design, and then our simulation setup, and we will see the results. And last but not least is the conclusion. This research is inspired by the potential of quadrotors to enhance SAR operation through their ability to search for survivor in specific area without the constant involvement of human personnel. However, we must consider several challenges, specifically to maintain stability and dynamically adjust the flight-path mission. From the problem, we deliver a solution to make an algorithm that cascaded LQR and LQR tracker with loss. Loss itself is widely used path-following method in marine navigation, and we're gonna try to use this method to see the impact in this field. As previously stated, the control strategy is designed as a cascade system. The system has been decoupled between the heave, roll, pitch, and the heading based on several assumptions. The operator input the desired position to the controller 1 as simultaneously receive a feedback from the quadrotor position concerning the earth frame. Furthermore, the output of initial controller will be fed in controller 2 and simultaneously get a feedback from quadrotor velocity respected to the rigid body. The same approach is applied to the bottom set as was used for the top set. However, the loss guidance loss was cascaded to communicate with control 1 in inner loop 2 to relay the desired yaw angle for reaching the path target. Technically speaking, every craft motion can be distinguished by two perspectives. The first one is north-east down, also known the earth frame, and the second one is rigid body. The correlation established using a relationship between the craft velocity and 6x6 diagonal transformation matrix, and this perspective are invaluable in ensuring the correct direction is being taken about the operation of the craft. For dynamic model has been derived using the Newton-Euler formulation. The equation is comprised of two factors. The first one is inertia of the rigid body, which is multiplied by the acceleration, and the Coriolis force, which is multiplied by velocity of the rigid body. Moreover, the equation will consider the external force or fault disturbance and the propeller force. Given that the quadrotor is an underactuated system, our attention will be limited to the controllable aspect, the heave and the rest of the attitude, like pitch, roll, and yaw. As mentioned before, we made several assumptions. The first one is the body fixed frame is defined as the originating at the body center of the mass, and then body frame are aligned with the principal axis of inertia of the body frame. Of the body. Additionally, the Coriolis assumed as a time invariant. Consequently, we can written the inertia as a diagonal matrix in equation 4, and the Coriolis expressed for like school symmetric matrix in equation 5. To reliably descend yaw angle for reaching the path target, line offset has been implemented in outer loop 2 to communicate with the control 1 in inner loop 2 using the geometrical principle. Furthermore, the objective of the loss is actually to assist the quadrotor in maintaining or reducing the perpendicular distance between the quadrotor and the waypoint, as known as the cross-tack error or the Y subscript E. To design LQR control system, we rearrange equation 3 into a state space representation, which allow us to obtain A and B matrices. After that, we choose the proper Q and R matrix depending on the desire. Then we will be able to use the provided information to find P using algebraic Riccati equation. This will allow us to determine the gain value for LQR. In order to calculate gain 2 for LQRT, we must use the following equation in equation 10. And it's important to note that find the gain 2 value will require the LQR gain or the G1. This simulation value employ a numerical approach based on our quadrotor specification, and the pattern of the SAR will implement its square pattern. And for disturbance, we use sinusoidal and implement in every state with amplitude 1, frequency 1 radian per second, and no phase delay. The time simulation set and 8300 second, and the local distance is 1 meter. Okay. The system is designed to assess performance in absence and presence of disturbance condition, while the quadrotor follow the square pattern. Okay. In this slide, we depicted the no disturbance response. The RMSE between the LQR and LQRT is identical for all variables except pitch and cross-track error. In terms of pitch, LQR is outperformed. Conversely, LQRT has better RMSE score for the cross-track error. In context of time domain, LQRT has demonstrated superior performance regarding settling time and percentage overshoot. On the other hand, LQR has more rapid response in time reaching the desired value. Additionally, the heading for both shows a comparable response. Now, let's dive into how both controllers handle the disturbance. As illustrated by the RMS score for this parameter, the LQRT shows no value change except for pitch. However, this change is not statistically significant. Furthermore, LQR performance show some change in RMC score for more than twice, and the cross-tack error. Apart from the time domain response, the LQRT shows minimal variation across all parameters except for the overshoot percentage. In contrast, the half response for the LQRT, this one, is end with marginally stable. Furthermore, both controller LQR and LQRT, with regard the pitch angle, end with marginally stable too. The LQR demonstrates a peak-to-peak range about minus 2.5 to 3.5 degree, while LQRT exhibit a range of minus 0.8 to 1.1 degree. From the result, the RMS value for LQR exhibits slightly similar to that of LQRT without disturbance and give better value to handle pitch angle position, while the value increase in the percent of disturbance. On the other hand, the value of LQRT tends to be stable in uncertain environment, maintaining the quadrature position perpendicular to the waypoint. Moreover, the time domain response for LQR has a faster rising time but produce higher offset and need longer time to settle and end with marginally stable to maintain a high position during the disturbance. On the other hand, the response for LQRT demonstrates a faster settle time, a lower percentage overshoot, and is more stable in uncertain environment. In terms of RMSE, the time domain response, where LQRT become the optimal choice for implementation in quadrature in submission, particularly in uncertain environment, and can potentially benefit for the practitioners. I think that's the whole thing. Thank you.
Okay, thank you for the presentation. I think there is one question here in the chat box. Let me read the question. All QRT is a kind of optimal controller. So what is the cost function that you optimize in this controller design? What's the essential differences between all QR and all QRT? Please answer the question, please.
Okay, thank you, Mr. Priyo. Am I audible?
Yes.
Okay, thank you.
Loud and clear.
Okay, thank you. Thank you for Mr. Aki for the interesting question. For the cost function, actually from the research we conducted, we do empirical study. We just injected some value to key and R matrices, and then we see the response like what, and we change it. We iterate until the response is quite okay for us, and that's for the first question. Sorry for and the second one is the essential between the idea of LQRT is quite similar with full step feedback with the gain in the input. Yeah, we add a scale to the input to reach our desired value. However, the difference between the full step feedback, there is some term to find the scale gain for the LQRT as presented in equation I forgot in my presentation. Meanwhile, in full step feedback, we got the DC gain from the scale gain from inverse in DC gain, if I'm not wrong. Thank you.
Okay, nice. Okay, thank you, Mr. Muhammad Putra, for answering the question. Before we move on to the next presentation, Mrs. Leah, are you standby? We will try to turn the video on. Everyone, please do turn video on to take a picture first of last capture picture. Okay, Mrs. Leah, everyone, every presenter, please turning on the video so we can take the picture and we can move on to the next presentation, please. Mrs. Leah?
Okay, for first page, 1, 2, and 3. And then for third page, 1, 2, 3. Okay, then you can continue the
Okay.
presentation.
Thank you, Mrs. Leah. Now we are move on to the second speaker. Our next presentation is by Mr. Zaid Jaya. Mr. Zaid Jaya, are you there?
Yes, I'm here.
We will now play the video. Yeah.
Okay, thank you.
Please be standby.
Hello, my name is Zaid from BRIN and University Polytechnic Haltefrans. I would like to present you about my research about evaluation of linear quadratic optimal control in automatic train operation during unplanned event. That's why we took these topics because unplanned event always occur during train operation. The most common procedure of automatic train operation is by planning the train speed trajectory, and the ATO will follow the speed trajectory for each distance. However, some unexpected event may happen during operation. So we have some objective in this work. Is first is evaluate the efficacy of the optimal quality control strategy in dealing with automatic train operation during unplanned event and the case of driver intervention. The second is by simulating various scenario and analyzing key performance indicators on the robustness, adaptability, and overall reliability of ATO system. And the last is to inform future developments and improvements in control algorithm, ultimately improving the resilience and efficiency of urban rail network. So in this work, we formulate the problem. The objective of optimization in ATO is to minimize the energy consumed while maintaining desired performance parameters such as travel time and passengers' comfort. This is the equation of energy that we will minimize from TA and TB. That's linear with the input and the speed. And this is a Langdon function. The linear quadratic solver is used to obtain optimal speed trajectory that's a function of speed in distance. This is the example of the speed trajectory you can see in the graphic. And then we do some simulation in this work. First, we generate an optimal speed profile that with the input of the position of the train, and then the optimal speed in this position is become the speed set point for the ATO, and then the automatic train operation will do a speed control that given to the simulated nonlinear train dynamics. ATO is try to control the nonlinear train model using optimal speed profile generated using linear quadratic cost function. And then the simulation is using the case of tram in Valenciennes from point A to B with the distance of 1 kilometer, generating speed profile with time constraint under 80 seconds. This is the speed profile that generated with the model and the linear quadratic solvers. In this simulation, we will try 3 unplanned events, a use case. An unexpected event will be generated in the middle of the simulation. The first is train sudden stop in the middle of the operation. This is the profile from the station A to station B, and then in the middle of the operation, the train will stop, which is the velocity of the train will be a 0, and then there is a T that that increase because of the stop. And then the second scenario is a driver intervention. In this case, is try to reducing or change the control command of the ATO. We are using the block diagram that the speed command from the automatic train operation will be disturbed by a momentary disturbance, like a sudden brake or the speed lever will be reduced or increased by the driver. And then the last use case scenario is a train mechanical fault that we are representing in, we are changing the parameter of the simulated non-linear train dynamics. We will try in the simulated environment to see what is the phenomena, and we try to analyze, and then as the future work, we will try to solve the problem. After we try the first simulation, now we try to show the simulation without the disturbance or within the stable environment, the train operation will be smooth as planned. The differences in speed is obtained due to the non-linearity of the train dynamics, because the linear quadratic solver is a linear solver, so there will be slight differences between the planned trajectory and the control output. And then we try with the first scenario, which is the train sudden stop. The train will be late to arrive at the destination, even ATO already attempt to follow the trajectory. As we can see at the graph, at first there is some braking, maybe or maybe an emergency stop at the time of 30 seconds, and then the train will be stopped for a moment, around 5 seconds or 8 to 10 seconds, and then there is a recovery phase. So as we can see in the graphic, the train is attempting to follow the trajectory, because this is not a time, because even if this is a time profile, but at the position X, they will try to attempt to follow the trajectory. So it best to generate a new speed profile. However, it depends on the train's performance limit. So if the train is already hit the limit, the train will not obtain the optimal trajectory. The second, it is a second scenario, which is a driver intervention. So as we can see, there is a slight disturbance after the around 15 seconds to the 40 second. There is a disturbance phase, but the ATO will try to go back to the previous trajectory. That's why there's only a slight differences or slight disturbance in the graphic. But if we see that in the acceleration, this is a graphic of acceleration within in all time, there is a high jerk rate, which is a represent a high change of acceleration that we can that will affect comfortness of the train operation, that affect passenger or even the driver. So there is a shared control algorithm to try to reduce this jerk, because if the driver try to interfere, there is that algorithm that know that there is intervention from the driver, so the control will from the ATO will try to reduce their output, so the jerk will be as smooth as possible. The last scenario is we try to represent a mechanical fault. So we change the parameters of the mass and resistance by 40 seconds in the train's dynamics. But as you can see that there is no change in the performance, and there is no change in the train arrival. But the differences is as we can see, there is a slight differences in the acceleration profile. So it can be represented as there is a differences in the energy efficiency performance, because the acceleration is directly reflected in the traction force given to the train. So from the results, we can conclude that this method of the linear quadratic trajectory planning plus ATO during unexpected event have several key points. First, when faced with an unexpected stop during the operation, the algorithm fails to recover, making it difficult to ensure the train arrives on the time. Robust schedule planning is necessary to account for such unplanned events. High jerk rates occurred when adding an action signal intervention. Therefore, a shared control algorithm must be implemented if the driver intends to reduce speed in the middle of the operation. And the last, as long as operational anomalies do not cause the train to stop, it will adhere to the schedule and planned trajectory, but it will affect the energy consumed during train operation. thank you very much. This is my presentation. Thank you for listening, and thank you for coming to ICRAMET 2024. See you next.
Okay, same as before. If there's a question, you can type them in the chat box or raise your hand, please. Meanwhile, if there is a question, I have one question. Oh, no, there is one question, I think. Yes, from Akif Rahmatillah. Why did you keep using all QR with a quadratic cost function that is often used for linear plan models when the dynamic models in the study is non-linear? Maybe this is related with the conclusion itself. Please answer, Mr. Zaid Cahya.
Yes, thank you very much for your question. I will explain first that why we use the LQR, because as the linear quadratic is the most direct solver that have a fast implementation, but and the solver is quite direct because we need to evaluate how the fastest solution as it is. We use Pontiagram minimum principle to reduce the complexity, but we still need the real-time implementation. But even so, the linear quadratic solver still cannot make a real time. So that's why we just use the LQR solver for the plan trajectory, and then the ATO is just use the PID. Thank you very much. It is just because the computational issues. We tried to use the nonlinear solver, but the computational still high. Thank you very much.
Yeah. Is there any question? We have still, we can ask another question, I guess. If there's not, maybe I have a little question. Have you tried consider with this is, I mean, the algorithm itself, it will be using by the learning algorithm such as, or using the available API, such as TensorFlow. This is for learning process or what?
As this research, so we still still not consider a learning-based method. Because it is a part of my research in the OPHF, and we try to make an analytical solution or maybe a numerical one, but we still not reconsider like learning-based methods because we try to make it as real time as possible, but we will try to consider it in the future because this is still my first years in the university. We still have more time to do more exploring. Thank you very much.
Okay, thank you, Mr. Zaid Cahya, for enlightenment the answer. Okay, we will now move on to the next presentation. Our third speaker is Mr. Agus Wiono from BRIN Indonesia as well. We will start the video now, and I invite Mr. Agus Wiono to turning on the Zoom video and be ready for the question and answer session right after. Okay.
Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Today I would like to present our paper short with detailed high-level synthesis of EPGA-based chirp match filtering for synthetic aperture radar system. The outline of this presentation includes the first is introduction, then the second is methodology that contain the theory of chirp signal, match filtering, the use of match filtering with high-level synthesis HLS, and execution speed optimization for match filtering in FPGA using high-level synthesis. The next outline is the result and discussion, and in the last is conclusion. The background of this study are that we know synthetic aperture radar is remote sensing technology that operates under any weather condition or all time of day. The synthetic aperture radar uses chirp signal for range resolution. This chirp signal also applied in fields like automotive radar, communication system, and LiDAR technologies. In short, chirp signal measure a target distance and reflection intensity, with match filtering used to improve detection accuracy by reducing noise. Match filters are essential in signal processing for detecting pattern in noise environment, particularly in radar and sonar. Match filter used to detect signal-to-noise ratio, equate signal to them reference signal, and it's used for signal processing on SAR radar. FPGA used for implementation of match filter with complex hardware language like Verilog can perform multiple tasks simultaneously. The filter, like VirFilter, have been built using OpenGL, though high latency remains an issue when using LabVIEW on PC. By high-level synthesis tools, allowing algorithms to be written in high-level language like C, which are then automatically converted into hardware implementation, improving parallelism and design optimization. Each LS enables faster design cycle and better performance, making FPGA ideal for real-time signal processing application. The aim of this research is to develop an FPGA-based chirp signal match filtering system using high-level synthesis, HLS tools, and C programming to reduce programming complexity while delivering high-speed processing on FPGA. Methodology: chirp signal. The SAR system using a chirp signal. The chirp signal is generated as shown in equation 1. In the chirp signal, the frequency will change to a certain time duration. The speed of this change is called the chirp rate or beta. This chirp signal will be made as a reference signal for match filtering. Match filtering. Match filtering is a widely used technique in signal processing to enhance the detection of object reflection that may be obscured by noise. The equation of match filtering is shown in equation 3, where xt represents the received echo signal and h tau minus t is the reference chirp signal. Match filtering model using HLS. The match filter algorithm was implemented using high-level synthesis, starting with a description in the C programming language, followed by compilation and synthesis into Verilog. The match filtering algorithm injects the signal as shown in listing 1. To build a match filter program, it takes several steps, consists of 1. Loading the reference chirp signal into array memory coefficient. Then 2. Shift the register and loading a new received echo signal into last register. And 3. Performing element-wise multiplication between the echo signal in the register and reference chirp on the array C, followed by summing all the multiplication result. In the match filtering program, we do improvement of the match filtering algorithm performance, that is execution speed. The improvement is we doing several optimization that are first optimization using directive unroll on each LS, and second optimization using directive array partitioning unroll on each LS. For first optimization using directive unroll on each LS, this optimization is parallelization of the shift register loop, allowing a simultaneous data entry and parallelization of multiplication operation between the echo signal and the reference chirp signal, like on figure 2.8 in below. And next, second optimization using directive repartition and unroll on each LS shown on figure 2b. This optimization is partitioning of the shift register array, allowing all segments to be processed in less clock cycle, combined with loop unrolling optimization for maximum parallelization. The match filter needs a reference signal in the form of a chip signal according to equation 1 and 2. The parameter of the reference chirp signal are frequency sampling 250 MHz, time with chirp 1 microsecond, chirp type is symmetric with bandwidth plus minus 75 MHz. the figure 4 shows the graph of the chirp signal after generated. Echo signal for test. The test of match filtering design it has been created the echo signal shown on figure 5. The echo signal generated by octave with added some chirp signal with different delay. The combination of chirp signal assumed a reflection signal of several objects. The echo signal included noise used to see the effectiveness of the match filter design. Implementation on FPGA by using high-level synthesis, HLS match filtering software has been synthesized and generated to IP block library. Implementation of match filter in FPGA following the diagram block as in figure 3. The 250 MHz clock source is used on the design system. 1024 echo signal samples are inputted in the input match filtering block, and the output signal is connected to integrated logic analyzer. With this integrated logic analyzer, the output of the match filter can be displayed and stored. In this table 2, the comparison of the result of the match filtering optimization implemented in FPGA. When not using optimization at all, the match filtering process takes 507 cycles, and for 1024 sample echo data takes 2535 microseconds. In the first optimization require a program execution for 249 cycles, and for 1024 echo data sample require 1245 microseconds. And the second optimization require the execution of the program only 3 cycles, and for 1024 echo data sample require 16 microseconds. In terms of FPGA resource, the unoptimized match filter algorithm use the least resource due to repetitive processes. The final optimized version require more resource than the unoptimized version, but still fewer than the first optimization. This indicates that proper optimization can improve FPGA resource efficiency. The figure 6 shows match filter result. The match filter implemented on FPGA with those generated by Octave give the output pattern from both implementations are similar, with high intensity at the 2 locations where the chirp signal echo is detected. The chirp signal is accurately detected despite the presence of noise in the echo signal. The result of the match filter implementation on FPGA shown in figure 6a for second optimization. The latency in FPGA calculated use integrated logic analyzer gave 4096 cycles from 1024 sample data. In terms of absolute time on the FPGA, the optimization takes 16 microseconds. The match filter result using Octave version shown in figure 6b. The match filter latency on Octave calculate use tick and talk syntax where give time duration of process. This process in Octave take 15 milliseconds. So from this result, it can be known that match filter process speed on FPGA is 937 times faster than the Octave version running on the PC. Conclusion: the FPGA-based implementation of match filtering for chirp signal utilizing high-level synthesis can streamline the design process. By employing C language for the match filtering algorithm, optimizing the design through parallel execution, substantial performance improvement were realized. The proposed approach proved capable of efficient optimizing match filter on FPGA, achieve a processing speed of 3 clock cycles, and require only 16 microseconds to handle 1024 data samples in the final optimized version. The result is 937 times faster than performing the same task in Octave on a PC. This finding highlights that HLS offers an effective and efficient solution for implementing high-performance signal processing on FPGA, making the design both faster and easier to develop and optimize. Further research is design a match filter use HLS method applied to parallel ring compression and azimuth compression for near real-time synthetic aperture radar processing in FPGA. This is reference for our research, and thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mr. Agus. It's very informative. There's two questions from Mr. Iman Firmansah. One question. The first question is, what kind of FPGA tools did you use to program the FPGA? The second question is, how fast the frequency clock for the ARM CPU connected to FPGA logic? Please answer the question, please.
Thank you for the question, Mr. Iman Firmansah. The kind of FPGA tool where I use to programming the FPGA is the ceiling HLS for the what is the name? Ceiling ELSL for the programming the FPGA. The programming the FPGA, we not using the ARM CPU, so the clock of CPU is not needed in the programming, because with ESL we can generate the IP library, and we can use the IP library to programming with Vivado. So the ARM CPU is not needed. Maybe enough from me. Thank you.
Okay, thank you for the answer. If Mr. Iman is still not enough, maybe we can discuss for more in the background. Okay, because the time is very strict, and we came to the fourth speaker. Moving forward, we have our fourth presentation by Mr. Sahrul Hamidi, representing University of Waterloo, Canada. Let's watch the video, and then Mr. Hamidi, please be standby, and video Zoom is keeping on, and he will be available to answer your question right after the video.
Hello everyone, my name is Sahrul Hamidi, and the topic of my presentation is modeling and analysis of spatial and temporal land clutter statistics in SAR imaging based on MSTAR data. I'm going to start off with the goal of the paper. I'll then describe the dataset that I have used in this paper, which is MSTAR dataset. I'll then start talking about the statistical analysis, both temporal and spatial. And after that, I'll discuss the target detection in land clutter, and I'll then conclude the presentation. Well, the goal of the paper is to analyze both statistical and temporal, basically statistical properties of the land clutter. And then based on that analysis, I'll then try to perform CFAR-based target detection. Well, the dataset that I've used is MSTAR dataset. It has been collected in spotlight mode at X-band, and I don't do any image reconstruction here. The image has already been created. All I do is just I'm using the basically images that have already been formed, and I use them to analyze the background clutter, and then I want to perform target detection. The only thing actually we need to know is that the images, when they have created these images, they have created it from different angles. So when I analyze basically the temporal part of the paper, I will address, basically it's automatically is going to address the aspect angle as well, which means each image basically has been taken from a different aspect angle. So when we perform the temporal analysis, it contains different aspect angles as well. So for the temporal analysis, I just focus on some specific pixels. We have 1,417 images, and we use all of them as different realizations in order to be able to perform the temporal analysis that we are looking after. So in order to perform the temporal statistical analysis, I chose several different pixels. The pixels have been chosen to be far away from the target. Target is mainly in the middle of the image. And one of the pixels is the top left pixel. And in order to perform the statistical analysis, I used all 1,417 realizations of this pixel. As you can see from the bottom left, we have the estimated histogram, and then I used Weibull, log normal, and gamma plus Rayleigh distributions in order to see which one of them can fit the histogram of the image better. So the goodness of fit measure here is based on Kalbeck-Leibler divergence metric, and I calculated the KL distance for every single one of those estimated PDFs with respect to the histogram. And as you can see from the right-hand side of the slide, we have those numbers which basically show that the Weibull distribution function is the best fit here with the lowest value for the KL distance. Another pixel that I chose in order to perform the statistical analysis, the temporal statistical analysis, is the one actually that I have shown it here on the bottom right. And I did the same analysis again. As you can see, we have the true histogram plus the estimated PDFs. And then I calculated the KL distance for all of those estimated PDFs. It's quite clear that from the KL distances that, again, Weibull distribution has the lowest KL distance, which means is the best fit for the data that we are basically considering here. And the last analysis for the temporal statistical part is based on several pixels, is around 400, close to 450 pixels that I chose from the bottom right of the image. And I performed the exact same analysis here. And on the left-hand side, I have shown the KL distance for all these pixels. And based on what we can see from the graph, again, Weibull distribution with the lowest KL distance is the best basically fit for the temporal statistical properties of the land clutter here. After Weibull, as you can see, Rayleigh is the best fit, and then we have gamma, and finally log normal. So the temporal statistical analysis for the MS star data shows that the best fit for the land clutter for this data set is Weibull distribution. Next, I want to concentrate on the spatial statistical analysis. And for that, I just focus on one image. So you can perform this analysis for every single image separately. And I focus on the area inside the red rectangle. So this area basically is far away from the target, which means we can make sure that all the pixels that we have, they represent the energy from the land clutter and not the target. And when we perform the statistical analysis for this spatial part, we use all those pixels. Again, we have the true histogram plus all the estimated PDFs. And then we use the KL distance as our goodness of fit measure in order to see which distribution actually can fit the data better. And based on the KL distance that I have calculated, you can see that Rayleigh distribution has the lowest KL distance, which means Rayleigh is the best fit for the spatial statistical analysis for the background land clutter related to the MS star data set. After Rayleigh, still Weibull is the second best fit, and then we have gamma, and finally log normal. So the result of the spatial statistical analysis shows that Rayleigh distribution is the best fit. After performing the statistical analysis, we're going to use this information in order to be able to detect targets inside the land clutter. To perform the target detection, I have used constant false alarm rate technique. And we have the probability of false alarm, and we're going to relate it to the adaptive threshold. So CFAR basically is about creating an adaptive threshold and use that adaptive threshold in order to be able to detect the targets that have been buried inside the background land clutter. So the relationship between the PFA, probability of false alarm, and TA, the adaptive threshold, has been presented. And I performed 2D CFAR, and we have guard cells and training cells. In order to be able to detect the targets, we have two different hypotheses. One of them is H0 and another one H1. Null hypothesis basically says that the cell under test only contains the energy from the clutter. The alternative hypothesis, H1, is telling us that the cell under test contains the energy of the target as well. So T sub AW is the adaptive threshold for the Weibull distribution function or any other distribution function that you have, and mu hat is just the mean of the clutter inside those training cells. Mu C and sigma C are the mean and standard deviation for the background land clutter, which I have chosen basically, which I have calculated them based on the area inside that red rectangle. So after performing the detection based on the CFAR algorithm over several different data sets or several different images, the result, I have presented the result, and it looks like this. As we actually saw, the best fit when it comes to spatial statistical analysis is Rayleigh distribution. However, Weibull was also a good fit. It had the second lowest KL distance. So I used both of them, Rayleigh and Weibull, both together to perform the target detection for all these four images that you can see. The number of training cells and guard cells, I have mentioned them in the paper for each specific case. The probability of false alarm here is 10 to the minus 6. And all the details actually have been mentioned in the paper. And as you can see, we can clearly actually see that we have been able to remove the effect of the background clutter, and we have been able to retain the energy of the targets in every single of those images. So to conclude the presentation, I should say that I presented spatial and temporal statistical analysis for the land clutter for the MS star data. It's really important because I used MS star data, so this analysis is based on that data set. I presented everything in detail. And then I used KL distance as a goodness of fit measure in order to see which distribution is the best fit when it comes to spatial or temporal statistical analysis. We saw that Rayleigh is the best one when it comes to the spatial and statistical properties of the land clutter, and Weibull is the best when it comes to the temporal statistical properties of the land clutter. At the end, I performed target detection based on the constant false alarm rates algorithm, CFAR-based detection over the MS star data, and I presented the results. Thank you so much for your attention. If you have any question, please feel free to ask me. Thanks.
Okay, thank you, Mr. Hamidi. There is one question from Mr. Iman Firmansah. How fast the execution time to compute a single frame of synthetic aperture radar image? Right, Mr. Iman? Okay, thank you. Please answer the question.
Sure. Thank you so much for the question. Oh, actually, as I mentioned in the presentation, I didn't perform image formation myself. So the images have already been created. I just downloaded them from the websites, which is related to the MS star data. So the image formation has already been done, actually. I didn't do image formation. If you mean actually how fast it takes for me to perform the statistical analysis, I didn't really calculate any timing here. I didn't measure the timing for this one. But as to the images that I presented, as I said in the presentation, the images have already been created. I just downloaded the images from the MS star basically website, and I have cited the website itself in the paper. If you're interested, you can just go and download those images for yourself. They're available actually for everyone to download and use.
Okay, Mr. Iman, I hope it is answering your question. Okay, thank you, Mr. Hamidi, for your valuable contribution. We appreciate it. There's
Thank you so
a
much.
certain kind of a approach for learning a spatial and temporal land clutter modeling, right? Okay, we came to the fifth speaker. To conclude our session, I'm excited to introduce our fifth and final speaker, Herr Edgar Jirosek is von Technische Universität Wien. We'll play the video now, and Herr Jirosek, please stand by and turning the Zoom video on, and be ready for a brief question and answer.
Hello, everyone. My name is Edgar Jirosek, and the title of my presentation, my paper, is Deriving Effects of IQ Imbalance on Phase and Amplitude Noise in Radars. Right, so to get started, I'll start with a short introduction to motivate the paper and the problem. We'll then proceed to a signal and system model that I'll be using in what follows afterwards, which are the theoretical derivations of expressions for phase and amplitude noise that we'll be looking at. I will then proceed to explain the way that the simulations were carried out, and then I will then follow up with presenting the results and a discussion. And in particular, we're going to be comparing simulations and theoretical results. Right, so the issue that the focus of the issue that we're looking at is phase sensitivity in radars. So what we see in the top left, this is let's say you sample a sinusoidal continuous wave signal and you sample it at the carrier frequency. You'd expect in a noiseless case, you will always receive the same point in the IQ plane. But due to noise, you will have some you'll have some noise, but in particular in a radar, due to local oscillator phase noise, you'll have this kind of it's going to look more like this instead of just a round dot due to the phase noise and local oscillator. And this is a particular nuisance because you want to be able to precisely detect noise when you want to track really small movements that are smaller than a wavelength, for example. So this is also a critical issue for issues like vital sign detection. What we're going to be looking at in this paper is how does this phase noise combine with other hardware effects that we don't want, which is in particular IQ imbalance. And another third physical effect that I'm going to be, so we have a small illustration of the IQ imbalance right in the top right. And the third effect that is also going to be considered here is the range correlation effect in radars. So just a small spoiler here, but I'm going to get into more detail on that later. Right, so our signal and system model is the following. You can see on the top right, so this is really just a very simple system. We just transmit some pure sine wave, right? So we have this cosine term, carrier frequency, time, and we have the phase noise term, phi. And then this just passes through a one-tap channel, which is essentially equivalent to a decluttered channel where you're just tracking the target. And then you receive this, you mix it with, you basically mix it with the cosine, with the sine wave from the local oscillator, and then you basically get the get a second harmonic term, and you get some zero IF component as well, right? And then you use this. Then you use your low-pass filters to filter out the second-order harmonics. This is how it would look like in an ideal receiver. However, if you have IQ imbalance, it looks more like this. So this is the most common model that you would use. The Q branch is amplified by a factor of G compared to a factor of 1 in the I branch. And the phase shift between the Q and the I branch are not pi half, right? So you don't have sine and cosine, but instead you have this parameter psi, which is your phase imbalance constant, right? So in the ideal case, you have G equals 1 and psi equals 0. And this is basically your received signal. So you have we have our differential phase. So this is basically just the result of up and down conversion. And we have some additional phase term because of the delay in the channel. Right. And so Right, so this is the other effect that I already mentioned. This is range correlation. Basically, what is happening is we use the same oscillator for up and for down conversion, and if we subtract the phase noise term by a time shifted copy of itself, right? Time shifted by this time delay constant TD, and then you take a look at the power spectral density. You will see the following sort of distortion, right? So you see if you have a if the blue curve is the local oscillator phase noise curve, and you take this take these phase noise samples, you subtract the time shifted copy, and then you take a look at the power spectrum, then you get this orange curve, right? So this is basically this formulation for sine squared times pi times delay time times this offset frequency times the original power spectrum. Right, and so the question is now, taking all of these effects into consideration, what is the resulting phase and amplitude noise of the receiver if we combine all these effects? And so if we have no IQ imbalance, you can see that that all our points lie closely on this on a circle, which is deformed to a different kind of curve. It looks like an ellipse, right? It's this blue curve here, and now the question is, okay, so let's form a circle around this our distorted samples, and the question is now, how do we describe the phase and amplitude with respect to this new circle that we established here. Right, the assumptions that we're making is that the noise is relatively small, so we can do a small angular approximation, which essentially means that we're using a first order Taylor series. Right, so the first effect is phase noise scaling, right? So the delta phi, this is our differential phase noise term that we would get in an ideal IQ mixer, and this alpha is our received phase noise term for the case that we have an IQ mixer which suffers from phase and gain imbalance. And it turns out, so if we make this first order Taylor series expansion, we get two expressions. We get alpha naught, we get this mean angle here, which is non-zero even if the mean differential phase is zero. So this is one result of IQI, of IQ imbalance, and the other constant is this d alpha, which is this phase noise scaling term. And where it shows up is if you want to calculate the power spectrum or the autocorrelation of your received of the phase noise in the receiver in your that you get if your mixer suffers from IQ imbalance, then you get these then you get this S alpha, right? So this is your power spectrum, and this is so it basically it's d alpha squared times the power spectral density in the undistorted case, plus this alpha naught squared, which is this kind of DC component, if you will. Somewhat similar to that, we have a phase noise to amplitude noise conversion. This is an important detail to consider, that we now have noise in the amplitude due to IQI, which would not appear if there was no IQI. And here again, analogous to the derivations of the phase noise, we basically, we have this first order Taylor series again, and you can see we have this DC component, so to say, and we have some constant that scales with the power spectral density of the phase in the undistorted case. Right, we can then proceed to also write down equations for spectra of the total noise that we receive, and we can normalize this to the carrier. So if we normalize it to the carrier, of course, this A naught, this mean amplitude cancels. So this does not show up here in the normalized power spectra. Right, just a short word on these simulations. How are they carried out? So we sweep the parameters G and psi. We leave some of these parameters constant, so the carrier frequency, sampling frequency, and so on. And what we do is we generate a vector phi k that resembles the that follows the power spectral density of a local oscillator of a state-of-the-art receiver, which we measured in a lab. And then we basically just use these two equations here. So we take this phase noise vector, we delay it by n taps. That's how we get a differential phase noise, and then we use this equation here basically to resemble the system to get the received samples from which we can calculate the angle and the amplitude. And then we use Welch's power spectrum, Welch's method to calculate the power spectrum of the received signal. Right, and the result is, as you can see here, the IQI basically distorts the phase and amplitude noise in a, so it distorts the phase noise and converts some of the phase noise to amplitude noise linearly. The total, right, so you can see another figure. So the noise in the phase noise between simulation and theory is below -15 dB, and in the absolute worst case, but it's typically around -20 dB. Yeah. So you can see here an example, right? So this is the phase noise in the undistorted case, and here we have our error terms for the phase noise and for the total noise. So they're at least 15 dB below our phase noise curve, right? Yeah, and with that, I want to thank you for your attentions and happy to answer any questions. Thank you.
Okay, Dankeschön, Herr Jirosek. We still have 2 minutes left. I guess 1 or 2 questions. There is one question, another from Mr. Iman Firmansyah in the chat box. As you can see, he said that I'm interested in IQ imbalance. Could you please elaborate the hardware employed to measure it? Please answer the question.
Do you mind if I share my screen in order to use an image in my slides as a guide here?
This is the last session, so please.
Okay.
Okay.
I will go ahead.
Yeah.
Yeah. Okay. Yeah. So I think it was this slide, and I think unfortunately I noticed that I think my head was in the way here. Right. So basically, so for the purpose of this paper, we didn't measure the IQ imbalance of any particular receiver. But one method that you can always apply is, let's say you just generate some sinusoidal signal and then you receive it. In an ideal receiver, the point would always lie on this on the unit circle or some constant times the unit circle, right? Some scaled version of it, and IQI then deforms the measurement to this kind of ellipse here. The way I did it, I don't know if this is the most common method, is you delay the received sinusoidal signal by different points, so that you make sure that you have different you have various different points on this trajectory. That will all now this orange curve is a very extreme case, by the way, I should add. So in reality, this is really just an illustration to show just kind of the concept, right? In reality, it would be much more like the blue circle. And once that is done, you can use these equations here. So once you have several data points, you can essentially use this system of equations, which basically, I mean, this is unfortunately a nonlinear system of equations, but then you can use some least squares estimation to estimate these two parameters, g and psi. So that's one method of doing it. Yeah. Yeah, I don't know if this does this answer your question sufficiently, or?
Yeah. Okay, thank you. One quick question. Also, I'm a little bit curious. In the page 14, I have a question.
Yeah.
In the simulation that you are telling this, what kind of the key parameters that phase noise PSD that you use for the state-of-the-art transceiver, and then how do these parameters compare to the typical real-world system?
So I'm not sure what you mean by the parameters of the PSD.
Yes.
Did I understand you correctly? So,
Yeah.
I mean, the PSD is really just this exact curve that we measured, and we then interpolated it over, I think, literally 100 million frequencies in order to generate a vector that contains all of these. I mean, you can parameterize this PSD with a series of power law curves, right? So at a few of these segments, you can approximate this curve as a slope that decreases with so that is proportional to 1 over the frequency squared. So that might be what's in these two regions, but it didn't parameterize the PSD per se. I just I used a different algorithm to generate the samples that follow this PSD, this exact PSD.
Okay. Okay. Thank you. Thank you for your very interesting insights. We really appreciate it. Okay, as we come to the end of our session, I would like to thank all our speakers for their excellent presentation and for being available for question and answer. I also want to thank our audience for your active participation. Please check the conference program for the upcoming session and feel free to continue engaging with the research and discussion throughout ICRAMET. Have a wonderful day. Guten Morgen for schönes Feierabend. Schönes Feierabend. And thank you once again for joining our session. See you tomorrow.
Thank you. Excellent pronunciation, by the way.
Ja, ich bin noch 4 Jahre in Deutschland.
Oh, wirklich? Okay.
Ja.
Wow, okay.
With the completion of the parallel session 5 and 6, now we have reached the end of the ICRAMET